the study, and we have got a major values that hydrophobicity, the single bond should be increased so that there might be chances the activity should get enhanced. The next study was a docking study in which we have gone for a Moligro virtual docker. This is the PDB we have selected 3NGU, which is a structure of Leishmania nucleoside diphosphate kinase, which is a complex with an ADP. And this enzyme took a very important part in this host cell integrity. So nowadays it has become a very important and interesting target for the drug discovery. The very first was the validation of the model. In the validation of the model, we have redocked the co-crystallized ligand. And we have found that both the ligands have been interacted with an RMSD value of 0.7, which should be less than 3 angstrom value. Now, this is a very interesting what we have received. What we have received in our study, there are two interesting points we have received. The very first, that the first 222 compounds of the series has shown the same dog square with a IC50 value, means from a lower to the higher, and we have got the same result with the docking also. And the second interesting part is that the very first compound 3BC and 6AB, the first compound is from the training set, the second one is from the predicted set with the least IC50 value. So yes, we are going into some of the right pathway we have selected. This is the interactions, and we have found that both the compounds bind with the active amino acids, and this is the distance. Distance is less than 3.5 angstrom, which is acceptable for the study. At the last, we have developed a structure activity relationship, and we have found if in the ring B, we will add the electron donating group, the enhanced activity might enhance. At the R3 region of the bulky group, hydrophobic, but it should be non-aromatic by the equation, and with the docking study, the activity might increase. The R1, what the scientists have given, what the authors have proposed, that is, we have found that, yeah, that is very good for the activity. So that is the very first phase of the study we have completed. These are the references, and thank you very much. In the second phase, we have designed some of the compounds, and we are synthesizing. We have already designed some 42 compounds, and we are synthesizing the compounds for the next Leishmania's activities, so that to validate our SCAD model with a synthesis part also. Thank you very much, sir.
Thank you, sir. Sir, I have one question in this aspect. Please, why you have chosen QSAR model, not any other models?
Sir, actually, nowadays, what the morally speaking, computational is one of my part which I do work on. And why I have selected this, sir, before this, I have done the same work with the sulfonam and analogs, and we have synthesized a derivative with the help of QSAR and docking. But that was for a chronic myelogenous leukemia, and we have got a very good result. We're about to patent that compounds in the process also. And this is the QSAR study which I have done for many compounds, and I find, yes, the results are getting it to some appropriate reason. And the second most important, in place of directly synthesizing the compounds, I have got at least an idea from that, yeah, we can go with this structure activity with the help of QSAR and docking. And QSAR is one of the best for getting the structure activity relationships by the 2D and 3D descriptors. So that's the one reason why I have selected it.
Yes, thank you. And the second question is, have you studied the interaction between proteins and such isoxazole systems?
Sorry, sir, I couldn't. Please.
Have you studied the interaction between protein and such isoxazole systems?
Yes, sir, we have. This is the isoxazole, which has been already reported by the 3BC, which is the most potent compound, and we found that they bind at the active site, and they show the same interaction as the ADP, the most active site. Second, we have designed some 42 compounds, and we have docked them also to the same active site. That is my phase 2 part, as because there is only 10 minutes, so I haven't shown that part. Okay. And in that also, we have found that our compounds bind with the active amino acids. As you can see, there are the major amino acids in this part.
Yes.
Both the compounds bind with the active amino acids.
Okay. Okay. Thank you. Is there any question from Dr. Jha? Dr. Jha, Dr. Shatadru Jha.
It's a nice presentation. I don't have any questions.
Thank you, sir. Thank you very much.
Okay, sir. Thank you. Thank you.
Yeah.
Shall I stop the screen sharing?
Yes,
screen,
yes.
Okay.
Yes.
Thank you very much.
Okay. So the second participant of this morning session is Dr. Alina Thapa. OPA, please.
Yes, good morning,
please go
sir.
ahead. Good morning. Please go ahead.
I hope my screen is visible and I am
Yes,
clearly
yes,
audible.
yes, yes, yes.
Okay. Okay, good morning, everyone. I'm Alina Thapa, and now I will start my presentation. Our work is titled as Comparative Theoretical Study of quinazolinone derivatives in different solvents and gas phase based on DFT calculations. And it was done under the guidance of Dr. Joydeep Biswas in SMIT as Master's Major Project. This work is not sophisticated, yet very simple, which can assist in considering or designing a new quinazolinone derivatives to meet their demands for specific application. Beforehand, I would like to thank our project guide, Dr. Joydeep Biswas, for his guidance, SMIT and ACT, TIFR Mumbai for this wonderful opportunity. I would like to start by giving a brief work description and some theoretical background. In this work, 5 quinazolinone derivatives are computationally studied in 5 different phases or solvents as gas, chloroform, acetone, methanol, and DMSO. The displayed numbers are the respective dielectric constants values, and most of the calculations are done considering it. DFT, B3LYP, 631G, DP are the computational inputs used together with STRF, TDFT, and solvation. Observations and discussions are done on different reactivity parameters, but for today, I would just like to discuss on geometrical parameters, electronic energy and polarizability, FMO, MEP, ESP, TDA, and UV-Vis spectroscopy. Density functional theory in short DFT is the theory developed by Perry Hornbach, Walter Kohn, and Lou Sham in 1964, and its practical application was developed in 1965, and even Nobel Prize in Chemistry was awarded to Walter Kohn in 1998. It is a computational quantum mechanics modeling method and is generally electron density dependent. Gaussian 09W programming was used, which provides different methods and basis sets and desired jobs for computational calculations. And DFT is mentioned. DFT is one of them. So quinazolinone, we have considered 5 different derivatives of quinazolinone, and they differ in the substitution of one of the hydrogen in their aromatic benzene ring. Like first molecule has no substitution, followed by substitution with orthochloro, parachloro, paramethoxy group, and para-nitro group. Quinazolinone derivatives are preferably chosen due to their versatile useful nature in pharmacology as antituberculars, anti-Parkinson's, anti-cancer, antihelminthics, insecticidals, etc. These are the 3D and 2D skeletal structures of the derivative. And for my further discussion, I'll be designating them as D1, D2, D3, D4, and D5. Moving on to results and discussions. In yesterday's session, we all heard the discussions made on molecular electrostatic potential, and I'd also like to briefly discuss on it. MEP, it provides an information about the polarity of a molecule where color coding convention is used ranging from red to blue. Red indicates most electronegative potential, while blue, most electropositive potential. The charged region of a molecule are variably visualized by ESP, and like MEP, it helps in visualizing electrophilic and nucleophilic reaction sites and helps predict hydrogen bonding interactions as well. TDA may also be defined as the distance of closest approach or the region within which molecules from outside won't penetrate or interfere. So together, they give this pictorial demonstration of the active regions concerning the atom's reactivity in a molecule. Even though some of these things can be predicted without the need of computation, but computation gives a detailed approximate numerical values, which really adds in the precise observation. And it was observed that the values increased with the increase in dielectric constant value. Moving on to molecular geometry, electronic energy, and polarizability. 2 graphs are plotted taking bond length of carbon nitrogen and carbon oxygen against dielectric constant values. And it was observed that with the increase in dielectric constant value, carbon nitrogen bond length decreases while carbon oxygen bond length increases in all the derivatives. And consequently, the bond angles also deviate due to the fact that functional group of a molecule are generally responsible for the reactivity. Discussions were made on these two preferably, while observing for electronic energy and polarizability against dielectric constant, D4 and D5 show the highest and the lowest electronic energy respectively, with its high deviation in D3. Polarizability of all derivatives is clearly observed to increase with the increasing dielectric constant value. This observation, polarizability itself, explains for the deviations in electrostatic potentials and molecular geometries discussed earlier. These are the electronic energy order and polarizability order. Like said before, D5 showed the highest energy. It is substituted by methoxy group, while D4, which is substituted by nitro group, so the lowest electronic energy order, and the polarizability order are displayed as well. Moving on to FMO, frontal molecular orbital. As we all know, HOMO-LUMO analysis plays a crucial role in giving insight into molecules' stability and reactivity. The figure shows the location of electron density of HOMO and LUMO orbitals in a molecule. It was observed that HOMO-LUMO energy gap and excitation energy is decreased in D5, which is substituted by nitro group, while it is increased with the rest of the derivatives with increasing dielectric constant value. Again, these are the orders. D3 show the highest LUMO energy gap, while D5 show the lowest energy gap. UV-Vis characterization is the last observation that I'll be discussing for today. These are the UV-Vis plot of different derivatives in different phases under consideration. Hyperchromic shift is observed in all derivatives which indicates the increase in its intensity, or say charge delocalization or polarizability, with the increasing dielectric constant value. Hypsochromic shift in D3 indicated increase in its excitation energy and stability, while betachromic shift in D5 indicated its decrease in its excitation energy and thus increase in its reactivity. An increase in its lambda max value, or increase in the lambda max value of D5 also speaks for the same. So in conclusion, D3 and D5 showed the maximum influence, which showed their higher tendency of solute-solvent interaction. Stability of derivatives under study increased in all the derivatives except for D5, where its reactivity is observed to increase. D5 and D2 respectively showed the lowest and the highest energy gap in solvent DMSO, while D5 and D1 are respectively observed to be the most reactive and the most stable quinazolinone derivatives under study in gas and solvent DMSO. These are some of the references. Thank you very much.
Will present it, madam. I have just one query. Am I audible to you?
Yes.
Have you ever synthesized this compound, or you are just doing these physical studies, characterization studies? Have you ever synthesized?
No, we have not synthesized. We have just done this comparative theoretical study.
Okay. And my second question is that, is there any significant fluorescence have you observed from these compounds?
Significant what, sir?
Have you observed any fluorescence? Have you studied any fluorescence study on these compounds?
No, sir, we have not done that.
Okay. Thank you.
Alina, it's a nice presentation. Can you go back to the UV?
Thank you, sir.
Yeah, it's nice presentation. Now you tell me that why your intensity is increasing when you are, because that is not visible. DMSO you are giving, no? Solvent DMSO. Is your intensity is increasing or decreasing?
Yes, sir. It is increasing, sir.
Intensity is increasing.
Yes, sir.
Yeah. Can you tell me why this intensity is increasing?
Sir, because it was observed that with the increase in dielectric constant value, and DMSO has the highest dielectric constant value among the solvents that we have considered, polarizability is observed to increase, or say it's a charge delocalization, which indicates the increase in stability, and therefore increase in its intensity, sir.
Okay, it's true. Then DMSO, you are telling how your charge is delocalized. Rather
So-
than methanol being present in methanol, and
Yes, sir.
DMSO is aprotic solvent.
Yes, sir.
It's an aprotic solvent. It is not a protic solvent. So how an aprotic solvent we can enhance your intensity in as compared to methanol?
Okay. Sir, in our theoretical study, we found that the DMSO has the highest dielectric constant value, and you are correct that it is aprotic solvent. It is polar aprotic solvent, which has highest dielectric constant of 46.68. And since we are doing this computational study, and like we just put an input of these numerical values, and they give us this output, and it is all based on the numerical value, that is dielectric constant value. And obviously when we are doing reactions or synthesis with traditional methods in laboratory, obviously I believe that we can observe we can observe those deviations, like we can observe
Yeah.
those.
Thank you. Thanks a lot.
Thank you, sir.
Hmm.
Sir, should I stop my screen? Or
Yes.
stop sharing?
Dr. Nilesh Jadhav, are you present? Dr. Nilesh Jadhav, OP19. Dr. Jadhav.
Sir,
Dr. Nilesh, yes.
Sir, I can go. We can go to the next person.
Okay.
We'll repeat again. Okay.
Okay, sir. Okay, sir.
Call him again.
Okay, sir. Dr. Satish.
Sir,
Amudala, are you present?
good morning, sir.
Yes. So
Yeah.
please go ahead.
Sir, is it visible?
Yes, your screen is visible.
Thank you, sir. Good morning, everybody. This is Satish. I'm a research scholar under the supervision of Dr. M. Jyoti Garu, Department of Chemistry, Mahatma Gandhi University. So I'm going to talk about design and synthesis in vitro anti-cancer activity and docking studies of 3-benzofuran 2-allyl, 1-paratolulyl, 1-pyrazole thiazole hybrids. So this is our contents. So I am going to first one, that is introduction. Pyrazoles and their variously substituted derivatives are important biological agents. They are used as an anti-tumor, antibacterial, antifungal, antiviral, and also analgesic agents. Also, thiazoles are important class of heterocyclic compounds. So they can act as antimicrobial drugs, antifungal drugs, anti-retroviral drugs, and anti-neoplastic drugs. So in continuation to our interest in the chemical and pharmacological properties of pyrazole and thiazole derivatives, we report here in a facile synthetic strategy for preparation of some new thiazole derivatives linked to pyrazolamide. This is the basic concept of my synthesis. So, the biological synthesized products will be reported in extended work. Now, let's move on the next topic. This is my objects and aims. By viewing above facts, we were planning to synthesize the biological potent of pyrazole thiazole hybrids.
Just sorry to interrupt. Satish, Dr. Satish, can you little bit enhance your slide so that because it is too small. Can you enlarge your slide? Yeah, little bit.
Okay, sir.
Yeah, at least. Yeah.
Okay.
Please continue.
Okay. So all my derivatives screened to anti-cancer activity against to human cancer cell lines like that. That is MCF7, A549, and HeLa, and I'm also studying molecular docking studies of my molecule, a correlation of in vitro anti-cancer activity results with molecular docking studies by the uh, target EGFR. So, so this is my experimental section. The compound one reacts with two in the presence of a pyridine catalyst to maintain the low temperature conditions and mild conditions. Also stirring the reaction mixture, we got a compound 3. So again, compound 3 cyclized to convert into a intermediate, that is compound 4, in the presence of different reaction conditions. And 4, the compound, intermediate compound, cyclized intermediate, the react with semi-carboxide and alpha bromoketones to present a ethyl alcohol and reflux the 4 to 6 hours to we got a my target molecule, my synthesized molecule, that is uh, thiazole hybrid, pyrazole thiazole hybrids are derivatives. So by using a one pot synthesis, I'm done the one pot synthesis. So this is the result and the proton NMR spectrum of my molecule. So this is NH protonate 12.16 ppm and CH double bond and protonate 8.07, and pyrazole C3 carbon is at 7.90 ppm and thiazole C4 protonate 6.69. Remaining all these protons are lies between 7.88 to 7.32 ppm. So this is my C13 NMR spectrum of my molecule. So here it is. Thiazole C2 carbonate 169.9 pm and C4 is the at 106.87 ppm, and pyrazole C5 carbonate 156.30 ppm and imine carbonate 147 ppm. So remaining all these lies between 13.98 to 110.47 ppm. So this is the C13 NMR spectrum of my molecule. These are the mass spectrum of my molecule. That is the chemical formula is C27 H19N5OS. This is the my mass spectrum of a compound, my synthesized compound. These are the derivatives. These are the derivatives of my pyrazole thiazole compounds. So I am going to biological studies and molecular docking studies. That is anti-cancer activity of my molecule. So these are the series of my synthesized molecules. Here it is. The all these compounds screened with anti-cancer activity against human cancer cell lines, that is MCF7 and A549 and HeLa. So among all these compounds, the 7D and 7H, 7D and 7H has a excellent anti-cancer activity. Remaining compounds are having poor activity. So this is the 7D and 7H is the good one. This is the molecular docking studies of my synthesized molecules. So here 7D and 7H having lower binding energies. So these are the two compounds. These are the two molecules are well supported to the theoretical data. Theoretical data. So these are the molecular docking studies of my molecules. So these are the docking pose, the best docking pose of my compound. So this is a docking compound picture. And finally, let me conclude this presentation. So we have synthesized a series of pyrazole thiazole hybrids. The compounds 7D and H have the excellent anti-cancer activity against growth of the human cancer cell lines. So the lowest binding energies of for 7D and 7H, that is minus 11.03 kilocalories per mole and minus 11.19 kilocalories per mole, respectively, in molecular docking experiments against target EGFR. And the molecular docking results are well supported by in vitro anti-cancer activity. These promising results will help in the design and development of new drugs based on these derivatives. So that's the end my presentation. I hope you enjoyed it. Thank you very much for listening my presentation. Thanking you, sir. Thank you everyone.
Thank you, Dr. Shethish.
Sir.
Well presented. I have one query. Have you started any complexation study using such type of ligands with any transition metal ions?
No, sir.
Okay. Okay. Okay.
Okay, sir.
Thank you. Dr. Jha,
Please,
is it
next.
okay? Okay.
Yeah,
okay.
yeah. Next candidate, Bimal Chetri.
Bimal Chetri.
Hello.
Yeah, Bimal, you please start.
So is my slide visible, sir?
No.
Yes, now it is visible. Please proceed.
Yeah, Bimal, no voice is coming.
Hello.
Yeah.
Yes, sir. Sir, is my voice audible, sir?
Yes, yes.
Okay, sir. Good morning, everyone. Sir, my name is Bimal Chetri. I'm a research scholar from Sikkim Manipal Institute of Technology. My topic today is a fissile synthesis of anthraquinone imidazole 611 dione derivative using molecular shapes. Anthraquinone imidazole dione is a polycyclic compound having a basic skeleton as shown in figure, where R may be alkyl group or an aryl group. The electronic states of this molecule are singlet N2 pi star, singlet pi to pi star, triplet N2 pi star, and triplet pi to pi star. And unsubstituted anthraquinone have 4 pi to pi star absorption band where wavelength differ from 220 to 350 nanometer, and one n to pi star band gap that is little longer in wavelength 400 nanometer, and its emission band of fluorescence appear between 480 to 850 nanometer. This molecule has a wide biological application in anti-cancer, anti-tumor, antimicrobial, anti-malarial activity, etc. The literature methods or literature surveys done are Paying et al. Prepared anthraquinone imidazole derivative using a tetrahydrofuran and potassium carbonate refluxing for 12 hours. The synthesized molecule yield was 70 to 75%, and the final yield was 50 to 90%, which was uh, the final yield of a prepared molecule was about 45 to 50%. Uh, the molecule uh, has ability to sense a fluorine ion, which can be tuned by electron push-pull property by the substituent in a phenyl para position. Uh, the the literature under literature method is the Bhattacharya et al. Synthesized a molecule using a nitrobenzene and 130 degrees centigrade for 8 hours refluxing. The solvent used for oxidizing solvent was nitrobenzene itself. And this molecule also showed a selective sensing for cyanide and fluoride ion. Another was the Ganguly et al. Synthesized a molecule anthraimidazole derivative using ethanol, acetic acid, and reflux for 4 hours. The trifluoroacetic acid acts as an oxidizing agent, and the yield of the product was 52%, and it has a good detection of cysteine in a biological activity. And another was Simon et al. Synthesized anthraimidazole based molecule in presence of acetic acid and sodium acetate. The time required for the reaction was just 1 hour in presence of reflux. And and acetic acid acts as an oxidizing agent here. The limitation of this literature was the reaction takes longer time for its completion and low or to moderate yield, and it requires high temperature and toxic solvents. The synthetic scheme we prepared was uh, a 1,2-diamino anthraquinone is reacted with substituted aldehyde in presence of DMF dimethyl formamide and molecular shifts in 60 degrees centigrade for 2 to 3 hours. The desired product was formed. The subsequent the synthesized product as is given here. There are numerous 10 molecules synthesized with this scheme. The UV visible, sorry, 1H NMR of the one of the molecule is given here. It shows a peak around 6 to 8.5, which is as expected for this molecule of molecule. The IR data of the molecule as shown here depicts that the carbonyl group in 1720, the NO staging around 1300, and an NH staging around 1550 to 1650, and one at around 3300. And the molecular sensing of molecule was done, which depicted that it has a good sensing properties, for fluoride, phosphate, and azide ions. And the conclusion here is the molecule prepared was very efficient, and the synthesis of anthraquinone imidazole derivative using molecular shifts. The reagents used in this synthesis was very cheaper, and the condition was moderate. And the versatile application in the field of drug designing and biological activity can be done with the molecule, and the molecule also acts as a chemosensor. I would like to express my special thanks and gratitude to NCCT, ICRTC CE organizer for giving me the opportunity to present my paper. Also, a sincere thanks to Dr. Satadru Jha for his continuous motivation and support throughout my work. Thank you.
Thank you, Bimal. It is a very good work Can you please tell me that what are the advantages you have observed while doing these reactions using molecular sieves?
Yes, sir. So as I said earlier, the synthesis of this molecule and the imidazole derivative was done with in high temperature, and the reaction takes around 16 to 20 hours, and also the yield of the product was very low, around
It's
50
low.
to 60%.
Yes. Yes.
Therefore, sir, our method of synthesizing a product using molecular sieve and DMF is at 60 degree and for 2 to 3 hours, and the
Time
yield of the
required
final
is
product
also less, but the yield is also increasing.
is the yield
80
was
to
also
90%.
increasing.
Yes. Okay.
Yes, sir.
Thank you.
Thank
Very
you,
good
sir.
work. Thank you. Dr. Jha, can we move to the next participant?
Yes.
Dr. Pradeep Simpi, are you present? Pradeep Simpi. Pradeep Simpi, are you present?
Sir, we will call again. Okay.
Okay, sir.
Next
Okay, sir.
candidate we go.
Okay, sir. Dr. Linsha Prakashan. Linsha Prakashan. Nurendra Chetri. Nurendra Chetri. Dr.
Narendra?
Nilesh.
Yes, sir. Good morning, sir.
Okay,
Yeah.
okay.
Narendra, please continue.
So is my slide visible, sir?
Not yet. Not yet.
Now, sir. Is it visible, sir?
Yes. Fine.
First of all, good morning to everyone. I'm Nurendra Chetri, pursuing my PhD on SMIT, that is Sikkim Municipal Institute of Technology. And my topic, this presentation is the effect of beta blocker drug on the gel to liquid crystal phase transitions of DDOAB vesicle dispersion. And firstly, I would like to give a brief introduction of my work and the effect of two surface active beta blocker drug molecule, propranolol drug molecule and ethanol on the thermotropic base behavior of dimethyl dioctadecyl ammonium bromide DDOB have been investigated by differential scanning calorimetry. DDOB is the synthetic surfactant with a mixing of water. It gives a structure which is similar to the biological cell membrane above the gel liquid crystalline transition temperature. The architecture of this artificial membrane is simpler than the cell membrane. And this is the biological cell membrane, which is seen in this figure. It is composed of various parts like surface proteins, cytoplasm, the glycolipids, the protein channel, glycoproteins, carbohydrates, and this membrane is made up of the hydrophilic head and hydrophobic tail, that is the phospholiquid molecules. And this cell membrane is very complex as seen here, and these interactions with the drug molecule is very complex. And in order to minimize this complexity, the synthetic surfactant is used as a dimethyl dioctadecyl ammonium bromide to make a bilayer artificial membrane. And this membrane is very much similar to the biological cell membrane. And this bilayer is composed of a surfactant with a head group and a tail group. And these bilayers shown in the right side of this picture is very simpler as the biological cell membrane, and the interactions will be very easier for us to interact with the beta blocker drug molecules as they share many of their similarities with this cell membrane. Like the phospholipiid molecules have the hydrophilic and the hydrophobic part, and whereas this surfactant also do composed of hydrophilic head and the hydrophobic tail. And this figure showing bilayers and the individual units of the surfactant forming the bilayers, the folding of the bilayers due to hydrophobic interactions forms the vesicles. And this spherical shell shown here is the vesicles, and these vesicles are formed above the phase transition temperature, and it is called the gel to liquid crystalline phase transition temperature. It is one of the most important feature of forming of vesicles. One of the most striking properties of vesicle forming surfactants in solution, such as cationic quaternary ammonium series of double chain dimethyl ammonium bromide, is the gel to liquid crystalline transition temperature. And in this figure shows the vesicles forming surfactants both in gel and in liquid crystalline phase. And this gel phase is in solid like state where the interaction is very rare and it's even not possible. But if we raise the temperature above the transition phase temperature, it forms the liquid crystalline phase transition. And in below the transition temperature, the surfactant are poorly soluble in water, and this cannot spontaneously assemble to form a vesicle. And in this biological membrane, the phase transition temperature is very important for ensuring that the membrane has the correct fluidity and permeability for its particular application. The gel to liquid crystalline phase temperature has been studied by differential scanning calorimetry, as shown in this figure. This figure represents the DSC thermogram of 5 millimolar aqueous DDOAB dispersion during heating and cooling cycle. DDOAB in an aqueous solution, when on heating, gives the two peaks, that is one at 36 degrees centigrade and other at 45.2 degrees centigrade. And this 36 degrees centigrade shows the vesicle contact or the interactions, and the peak at 45.2 degrees centigrade shows the main gel to liquid crystalline phase temperature. And on these interactions, we have interacted the beta blocking drug, looking at their the degree of lipophilicity. The propranolol and atenolol is selected in this, looking at their hydrophilic and the hydrophobic one. The hydrophobic is the propranolol, which we can see in this figure. It is the basic structure of propranolol, and and the least lipophilic is the atenol, or the highly hydrophilic is, or we can call it as highly hydrophilic, that is the atenol. Here is the structure of this atenol. It is a basic structure of atenolol, and it would be very interesting to compare the effect of these two beta blocker molecules on the phase transitions of DDOAB. And now when when the ethanol is added to the surfactant, that is DDOAB, what it happens is that we can clearly see in this graph, the thermogram graph, that is the heat versus temperature. What it happens is at mid DDOAB, there is a two peak that I have stated earlier, that is at 36 degree and 45.2 degrees centigrade. And as and when the ethanol concentration is increased, there is the decrease in the transition phase temperature. And and at concentration below 1.0, we can see there is the disorderliness of the surfactant chain, which decreases the transition temperature. And at above 1.0 mm, the peak broadens. And the peak is broadens and the temperature range of phase transition widens, and also many extrema also appears in the neighborhood of the main transition temperature. This clearly shows that vesicles also contains various types of domains, which is some rich in ethanol. And when the same thing, the surfactant is interacted with the concentrations of propanol, what it happens is here also at neat DDOAB, there is the two peaks, and and when the concentration is increased of propanol, sorry, what it happens is it also lowers the transition phase temperature and also broadens the peak, or the broad peak is absorbed. And when comparing this propanol with ethanol, what it happens is the lowering of temperature is also very high at propanol, and and also the broadening of peak is also very large in propanol. The effect of 0.5 millimolar and 0.1 millimolar propanol on the main transition temperature is comparable to the phase transition shift, which lowers this concentration without increasing the gel to gel liquid crystalline phase transition temperature. Unlike ethanol, propanol also cause pre-transition peak at 36 degrees centigrade. This is due to the vesicle interactions, and this propanol when added, it will form a peak at 36 degrees centigrade even at the least concentration. And this is due to the hydrophobicity and the concentrations of the added drug molecules. It not only affects the transition temperatures of DDOAB, but also the shape of the peak corresponding to the phase transitions. And this direct gel to gel liquid crystalline phase transition temperature may be predicted because the pre-transition disappeared at the lowest propanol. And this is the work I have carried out, and there are many other works to be carried out with the spectroscopic technique. And thank you all.
Thank you, Narendra. Very good work.
Thank you, sir.
Anyone have any questions? Please ask. I am requesting audience, please ask if you have any questions. Mitra sir?
Yes, sir. Yes.
So we can repeat again the Dr.
Yes, sir.
Nilesh
Yes, sir.
Jadhav. Dr. Nilesh, are you here? Dr. Nilesh Jadhav. Dr. Pradeep Simpi.
Dr. Pradeep Shimpi, are you here? OP22. Dr. Linsha, are you here? OP23. Sir, I think that
Yeah.
Dr. Jadhav, Dr. Pradeep, and Dr. Linsha, they are not present.
Yes.
Yes.
So Nayan sir, can you conclude here?
Yes, sir. Please, you can conclude, sir.
Yeah.
Okay.
So thank you all participants for your nice presentations. So it is the time to hand it over the session to Aswin Basnet. Aswin, please carry over.
Thank you, sir.
Thank you.
Since we are ahead of the schedule and we have invited top session 4 of the conference scheduled at 10:30 a.m. I think Nayan sir would like to say something.
Okay, thank you, Asin. I would like to thank Dr. Amrit Mitra and Dr. Satatru Jha for sharing the session. I think out of 8-9 papers, 3 are absent. Now we have the next invited talk at 10:30. Dr. Venkat Narayan will be joining from USA. I hope sir has already joined. Sir, am I audible? Dr. Venkat Narayan.
Hello, can you hear me?
Yes, sir. Yes, sir. Yes.
Yes, I'm joined and I was listening to the talks. Very interesting talks.
Okay, sir. Sir, we'll start at 10:30 as per IST. I think in your place now it is 10 or 11 p.m. I guess.
It's 10:30 here, 10:30 p.m.
I request you to wait another half an hour.
No
since
problem.
We have given
No,
the
no,
time as
no.
10:30 to the participants.
Yeah, no problems.
Prabhu sir, are you online?
Yes, I am online.
Sir, Venkat Narayan sir has joined.
Yeah, I would like to speak to Venkat Narayan. He's my student from Wilson College. Hello, Venkat.
Hello, sir. How are you?
Venkat, how are you?
I'm doing very well. Got your note.
Can I see you? I can't see you.
Oh, you can't see me. Wait, I had blocked the video. Now, can you see me now?
1 minute. Yes, I can see you. Venkat, how are you?
I'm doing well. And thank you for this opportunity to participate in this
Pleasure.
conference.
Yeah. Unfortunately, I may be missing your talk because I have got to work with my nephew's residence.
Yeah, you told me. Yeah.
I'm there with you in spirit. So how are things, Venkat?
Things are okay. I mean, obviously it's challenging with all this COVID and everything, but it's hopefully it's improving and things will be better next year.
Okay, fine. How is the family?
Family is all doing very well. Thank you.
Okay.
And I look forward to seeing you. I'm coming in February. I'm coming to India.
Good.
And so probably I'll plan a trip to Mumbai around March.
Do come. I spoke to the head of the department in Wilson.
Yes, sir.
Parbat, also my PhD student.
Yes.
He is joining the lecture. And we were thinking of having you in Wilson for a day and fully you could give some talk on your work.
Oh, it'll be my pleasure. It'll be
Yes.
my pleasure.
So Dr. Parbat will be joining your lecture and
Okay.
possibly will talk also. Okay.
Look forward to it. Thank you very much.
Okay. All the best. All the
Thank you,
best.
sir.
Yeah. Thank you.
Good morning, sir. Good morning, Prabhu, sir.
Good morning, ma'am. Good morning.
So very interesting talks we had in the morning.
Yes, I listened to some of them.
Yeah.
Very frontier work is going on.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
Proud of
And that,
people.
yeah. And next talk is also very important, very interesting.
Yes.
That your student will be delivering.
Narayan was in my first BSc batch way back in 1974-73, I think.
Oh, great, great.
Brilliant.
It's a pleasure for a teacher if the
Brilliant.
student gives a talk. Yeah.
Lot of work in polymer chemistry. A very good speaker,
Yes, sir.
as you will
Yes.
soon see. Really,
Yes, sir. Yes. Yes.
that he is giving a talk in your NCCT.
Yeah. Yeah. One of my colleague is also delivering talk tomorrow, sir. Ilyas Ali.
Oh, yeah, yeah, yeah. Okay.
Yeah, he is. And one of my colleague is also giving talk. Manas Kanti gave. He's working from Ravi Shankar University tomorrow.
Yeah, Ilyas Ali is in US, I believe.
He is in US, and one of my colleague Manas Kanti Dev, he is in Ravi Shankar University.
Okay.
Raipur, Pandit Ravi Shankar University. Yes. And few of our students are also presenting papers.
Well,
PhD students. Yes.
Alina Thapa's paper today morning.
Yes, sir.
Your institute. I am SMIT.
Yeah.
Right?
Yeah. DFT. She might have presented in DFT, sir. I've missed her presentation.
Top.
Yeah. Yeah.
Very confident and good work. Congratulations.
Yes, sir. Yes, sir. Yes, sir. Yes. And this person is also from our SMIT, Noren Thapa. Noren, last speaker.
Okay.
Noren.
Okay.
Thapa hai ki kya hai? Noren. Noren. He is also from SMIT. Yeah.
Very nice.
Okay, very nice. Okay. Thank you, sir.
Dr. Utpal from Tezpur Central University. I think you have also joined. I saw your name.
Yeah, Dr. Utpal has joined.
Utpal Bora.
Yeah.
Please unmute.
Good morning, good morning, sir.
Good morning.
Good morning.
Your talk is just after Dr. Venkat Narayan. It is approximately 11:10.
Okay.
And tomorrow, as Madam has mentioned, Dr. Ilyas, you may be knowing him. Dr. Ilyas completed his PhD from Tezpur Central University under Professor Doloi. I think.
Yes, I know him. Yes, I know.
I think Professor Doloi still is in Tezpur University, right?
Yes, he's still here.
Okay. He completed his PhD from there. Then he joined in GE Bangalore.
Yes,
then he
I
has
know
shifted to US. Then he has shifted to another company now. Last, I think, 15 years plus, nearly 15 years he is in US. He will be joining tomorrow.
Okay. I will definitely inform our Dolo sir.
Okay. Please inform. Yeah.
Okay.
Just 2 days back, he called me also that he will join positively.
Okay.
Welcome, Dr. Utpal Bora.
Yes, sir.
You in NCCT.
Yes, I am in Tezpur University.
Yeah. Looking forward to your lecture.
Thank you, sir.
अरे वो है
क्या यार
Yeah, I have seen one message. Dr. Linsa Prakasan, you are present now?
Yes, sir.
Okay, you are joining exactly at 10. Okay, you can definitely present. Let me call you. You want to present your paper, right?
Yes, sir.
Yeah, we have time. You can present. Just you share your screen. Let me ask the chairperson.
Hello. Sir, should I start?
Yes, you can start. Please go ahead.
Okay.
But you, if possible, please keep your presentation in PPT mode, presentation mode. Yeah, please go ahead.
Okay. Okay. Good morning, everyone. So my topic is like we have developed the play and learn chemistry using valency cards of element, a novel learning and assessment technique for teaching the periodic table. So myself, I'm Linsha Prakashan. I'm presenting the paper, and my co-authors are Jogita and Anjali Jaiswal. Okay. So basically, the periodic table is the most considered most carrier among the children of younger age group, basically from 8th standard to 10th standard, and it comes in the curriculum. So we have developed a novel play and learn methods. The main objective are to memorize the 36 elements, symbols, atomic number, electronic configuration, and properties. So, and the basic aim of play and learn is to provide the right kind of challenge which the students feel motivated to take the challenge of learning new and difficult basic concepts of science. So these are the three objectives, like how elements are grouped together as per the outer electronic configuration, and how outer electronic configuration decides the valency and chemical behavior. So this is the card that is developed in which the 36 elements are properly arranged, and it has atomic number, electronic configuration, the symbol, valency, groups, chemical properties, and chemical behavior. So it's this card, like there are 10 games developed. So these are the 10 games, out of which every game there is a concept behind it. So if there are learning games as well as assessment games. The learning games consist like these are the games like More the Merrier, in which the child will play and learn the atomic number, name, and symbol. Then there is Less is More, Special Someone. Like this, there are many games, and apart from that, there are grouping games also. So the learning games, the main rule of these games are you have to tell the element name, symbol, and atomic number once the card is open. This is like the traditional card games by which the child can learn by playing itself. So these are the learning games. So the child has to play continuously. Now we took samples. These are there are 45 students, in which initially we gave them a test paper where they have to fill in the names and numbers of the elements. So this is the first game. They have to write it down, and we conducted a play of 20 minutes. After the play, the scores were literally going high. Like the scores which the score improvement was around 33%. Initially what they scored and later what they scored, there was a huge difference just before 20 minutes play. And this is the assessment game 2, in which they have to fill in the electrons. So in the first, like they have to play this continuously. Like there are 1 attempt, 2 attempt, 3 attempt, and 4 attempt. In the first attempt, we saw that the scores were less, but it gradually increased in the play. So this is the test paper of one of the child who scored 18 on 18 in all the name, atomic number, and symbol. I'll just show you the video sample of the gameplay. Just a second.
Thank you, Linsa Prakasan.
Sir, 1 more minute, sir. I just wanted to show you my video.
Okay.
Atomic number 28. Atomic number 13. Electronic configuration of 16. Atomic number 4. Atomic number 23. Electronic configuration of carbon. Atomic number 20. Atomic number 12. Electronic.
So that's all. Thank you.
Okay, thank you for your nice presentation. Anyone having any question? Anyone having any question? Okay, if no, then thank you, Lincha, thank you.
Thank you, sir.
At the same time, another two presentation also left in the same session. Dr. Nilesh and Dr. Pradeep, are you present? Okay, then by after 10 minutes, we will start our invited talk. Thank you. Professor S.D. Samant, sir, are you present? Professor S.D. Samant. Professor Samant, are you present? Just 2 minutes. I hope Professor S.D. Samant absent. Sir, are you present? Professor S.D. Samant. Okay. Okay, then very good morning to one and all present. Now we are in invited talk session 4. I request Dr. Soumya Kanti Biswas and Dr. Manoranjan Pandey to share this session.
Very good morning, everyone. I welcome to our second day conference, session 4. Now we have two invited talks by two distinguished speakers in this session. Dr. Venkat S. Narayan, followed by Dr. Utpal Bora. Our first speaker of this session, Dr. Venkat S. Narayanan, is currently Principal Polymer Consultant in Anthara Technologies Consulting, LLC, McKinney, Texas, USA since 2018. Dr. Venkat S. Narayanan did his BSc in Chemistry, University of Bombay, India in 1975, and BSc Tech, Plastic Technology in University of Bombay in 1978. He obtained MSc in Tech, Plastic Technology from University of Bombay in 1981 and received PhD in Chemistry from Virginia Tech, Blacksburg, Virginia in 1994. He started his professional career as market development officer in Deccan Fiberglass Limited, Hyderabad, India, in 1981 and 1982. He was there. And then as entrepreneur and director in Bhaipak, India Private Limited, Madras, India, from 1982 to 1988. He pursued his postdoctoral research as research associate in the chemistry department of Virginia Tech, Blacksburg, Virginia in 1994-95. In his professional career, he has been associated in a number of R&Ds of different organizations. He served as senior research scientist in Innotech, Roanoke, Virginia in 1994, from 1995 to 1997, as manager materials and R&D in Innotech, Johnson & Johnson, Roanoke, from 1997 to 2000. Manager materials R&D in the Spectacle Lens Group, J&J Vision Care, Roanoke, from 2000 to 2005. As manager, polymer research, DUPI, orthopedics, Warsaw in from 2006 to 2011. And also the senior principal scientist in the same organization from 2011 to 2012. He was a research fellow in DUPI orthopedics from 2012 to 2018. And currently, he is as principal polymer consultant in Anthera Technologies Consulting, McKinney, Texas. His significant contribution is reflected in his publication as well. He has published 12 patents and 15 innovation disclosures with his contribution as primary and co-inventor. Also, he wrote books chapter and published research articles in reputed international journals. He has received awards and recognition for his contribution, such as Johnson Medal for Excellence in Science in 2013, the J&J Tugu Inspired Award in 2013, the J&J Standards of Leadership Award for Successful High Refractive Index Progressive Lens Project Implementation in 2003. He is a recipient of the Innotech Presidential Award for Work Ethics and Dedication in 1995. Today's topic of his talk, advances in hydrogel biomaterials. I request Dr. Venkatesh Narayanan to deliver talks. Thank you.
Thank you, sir. I'm going to see. I hope my screen is visible.
Yes, sir, it is visible.
Okay. So first of all, thank you very much for that kind introduction. It's my pleasure and privilege to give my talk today to this very distinguished set of scientists and teachers. So without much delay, I would like to get started on this. My topic today is advances in hydrogel biomaterials. And I thought this was an appropriate follow-up to the talk that I gave in last year's convention, where I talked about polymer blends. And this is a kind of a follow-up of that, and talking more specifically about certain polymer systems, which are hydrogels. So a brief introduction. What are hydrogels? Hydrogels are three-dimensional structures which are very high affinity for water, primarily because they are composed of hydrophilic polymers and copolymers. And these may be both natural. We know a lot of examples in naturally occurring hydrogel polymers, as well as many that have been customized by synthesis. These hydrogels can either be ionic, so they can be cationic hydrogels, anionic hydrogels, or even non-ionic or neutral, depending upon the kind of groups that are present along the polymer chain. They are also, another way of classifying them would be based on the morphology or the network architecture. And again, there are a number of ways it could be done. And we will look at it in a little more detail in a couple of slides. So these materials have a very high affinity for water, but they're not soluble. And this is because in the structure, they have a lot of chemical or physical crosslinks. Now, these crosslinks prevent the complete dissociation and breakdown of the chains. And as a result, they are not able to be soluble, but because of the high affinity, they can absorb a lot of water and therefore undergo significant swelling. So these materials, the physical crosslinks that are present, maybe because of chain entanglements. So these polymer chains are very long. And imagine if you wish, if you kind of, if you've done this at home, you take a lot of long wires and you put them all together in one box, you shake it up, after a while you go and try to take out one at a time. You will never be able to take it out cleanly because it will be all entangled with the other wires. And that's the same way here. Polymer chains get entangled. And when they get entangled, they lead to very interesting mechanical properties. So once they have a certain minimum molecular weight, they undergo this entanglement. And these are what are called physical crosslinks. Alternately, there could be crystalline domains or even some weak associations such as van der Waals forces and or hydrogen bonding. So all of these can contribute to a network structure where the dissociation is prevented and therefore solubilization is prevented. These hydrogels, because of these unique properties of high water affinity, excellent biocompatibility, and good mechanical viscoelastic properties, they have got a lot of attention in biomedical and pharmaceutical applications. So a lot of medical devices contain these hydrogels, and a lot of pharmaceutical applications, for especially for drug delivery, do that. And so there are a host of applications for these hydrogels, and we will talk a little bit more detail in the subsequent slides. Hydrogel classification. This gives you a good snapshot of the hydrogel, how they're classified. So you can see, you can look at it from different perspectives. If you're looking at it from a source, then they could be either natural or synthetic or even semi-synthetic, which is taking some natural materials and modifying them. Or they could be based on composition. So they could be a homopolymer, which means a polymer made from a single entity. So the repeat unit is always the same. Or it could be a copolymer, wherein you have multiple different chemical repeating units in the same structure. And I have talked about this in my previous talks, but maybe just to explain very quickly what IPNs are. IPNs are nothing but interpenetrating networks. And these polymer chains, sometimes they are grown in such a way that they do not have any chemical bonds between them. So two different polymers are grown simultaneously, such that they do not have any kind of link between them, but they are independent of each other, but they form a complete entangled structure, which is called an interpenetrating network. Alternately, you could define them by configuration as amorphous crystalline or semi-crystalline. And again, cross-linking as physical and chemical. And we have talked about the ionic. And alternately, you can look at it from the response of the material, whether it's a physical response, a chemical response, or a biochemical response. And we'll talk a little bit more in some of the examples that I will try to show. These could be either biodegradable or non-degradable. And again, they could be conventional materials, or they could be smart materials that respond to stimuli in specific ways. And these are very useful in applications such as biosensors and so on. Now, let's look at the microscopic morphology of polymer chains. So if you take this being a microscopic zoom view, then you can see that there are a lot of these chains that are forming like a network. And between these networks, you see that there are these red points which are denoting a chemical bond. So therefore, you have a chain like this and another chain like this, and they have a bond between them. So that becomes a fixed point where these two chains are locked together. Now, a multiple number of these locked points cause this whole network to become very immobile. And that is what gives these materials very unique mechanical and physical properties. In addition to these physical crosslinks, you could also have what I talked about earlier, when these chains get entwined in each other and they cause what's called entanglements. So you can have an entanglement point, which could also lead to contributing to the immobility of these chains. Similarly, you could also have some of these chains crossing each other, but they are very close to each other, but they do not have any bond between them. However, they could still have some van der Waals forces or hydrogen bonding, and that could also hold them together. So therefore, there are a number of ways in which you could create this kind of a network. And this network, then, when there is a solvent like water, these cannot break down like a normal solute would in a solvent and become dissociated at a molecular level, and therefore you get a clear solution. In this case, because of these chemical and physical crosslinks, this material is prevented from completely breaking down. As a result, it can only swell up, and all these empty spaces in between them, which is called the mesh size, would fill up with the solvent, in this case, water. So depending upon the mesh size, you could get a different degree of swelling. The other parameter that defines the mesh size is actually called the molecular weight between crosslinks, or MC. And MC is nothing but the average molecular weight of all these different molecular weights between two junction points, and that is computed as the molecular weight between crosslinks. So therefore, these parameters allow us to design and target specific mechanical properties and physical properties. Now let us look at a few examples of some standard or natural hydrogels. You know many of them, they are familiar: agar, gelatin, cartilage, chitosan, polysaccharides, and polypeptides. Then there are some interesting ones like hyaluronic acid, which I will talk about in some of the applications. Among the synthetic hydrogels, these are primarily polymers with a very high affinity to water, or what are called hydrophilic polymers, like polyvinyl alcohol, PVA, polyethylene oxide, PEO, or polyisopropyl or N-vinyl pyrrolidone, or hydroxyethyl methacrylate, and polypeptides. So these are materials that have polar groups in them extensively enough to cause some sort of an association with water, as a result of which they are very hydrophilic. In terms of the biomedical applications, there's a whole list of them, and this is not the full list, but at least some sample of areas in which these hydrogels are applied. They are applied, for example, in contact lenses and intraocular lenses. These are made of materials that are essentially hydrogels, especially the soft contact lenses. You can have wound dressings that can be made from these hydrogels. Hydrogels have a lot of use in tissue engineering and cartilage repair and replacement. They are used in drug delivery, hygiene products, and cosmetic skin treatment. And there are other applications that I've not talked about, like biosensors. Then there's a whole host of other applications in devices where they are used for diagnostics and so on. And in the interest of time, I won't be able to cover all of these, but I will try to cover as many as possible. Let's talk about contact lenses first. Currently, the contact lenses are made from hydrophilic polymers, which are essentially acrylates or acrylic derivatives like acrylamides. And these materials are then polymerized along with a hydrophobic material like a polydimethyl siloxane oligomer, which is also derivatized with a methacrylic or an acrylic functionality. Now, these acrylic functionalities or methacrylic functionalities, these are primarily double bonds, carbon-carbon double bonds, which can be triggered to react in the presence of either heat or UV radiation, whereby you get the carbon-carbon double bond breakage, generating free radicals, which can then continue to react. When you have multiple functionalities of these carbon-carbon double bonds in a single molecule, you can have more than one point of growth, and that's how you grow these polymer chains. And this mechanism is called free radical polymerization, as I'm sure most of you are very familiar with. But that's the mechanism that's used for all these materials to, you take a composition of some of these materials, and we'll talk a little bit more about this in the next slide. The acrylic monomers will provide the hydrophilicity or the water attraction ability to be able to swell in water. On the other hand, the silicone, which is hydrophobic, as you know, the silicone component or the polydimethyl siloxane component will actually provide some unique properties of oxygen permeability. If mechanical properties have to be further fine-tuned, then these are done so by adding or modifying the network by additional functionality materials. Let's look at some of these state-of-the-art materials. Now, there are a number of contact lenses available in the market today, but they're all essentially formulations or materials that are based on very similar components. So, for example, this is a N-vinyl pyrrolidone, and you can see this carbon-carbon double bond here, or a hydroxyethyl methacrylate, where again you see a carbon-carbon double bond, or dimethyl acrylamide, where you can see here again there is a carbon-carbon double bond here in this acrylic functionality. So these groups are responsible for undergoing free radical polymerization. And because of the presence of hydrophilic groups, like for example, the hydroxy group here, or the amide group here, or the lactam group here, the cyclic amide group here, these are all responsible for high affinity to water, and therefore these are all essentially very hydrophilic materials. And in addition to these materials, you could also think of a dimethyl siloxane oligomer or polymer, which has got, that is this material here, where you got a number of these repeat units. But at the end of it, it is functionalized with an acrylate. So therefore, these can also participate in the free radical polymerization along with these materials. Now, the interesting thing is, why do we have a hydrophobic material? Because polydimethyl siloxane is very hydrophobic. Why do we have this when we want a hydrophilic system or a hydrogel system? The answer is that these dimethyl siloxane materials have a very unique property. They have, by themselves, they have a lot of application in gas permeability because they have a very high degree of gas permeability. And therefore, they are used in a number of gas permeable membranes. For example, separation of oxygen from nitrogen, carbon dioxide from oxygen, and so on. So a lot of these gas separation membranes use polydimethyl siloxanes. Now, the relevance here is that the presence of these hydrophobic phases in the overall polymer gives you regions that are very highly oxygen permeable. So you may have heard the term in contact lenses called oxygen permeable lenses. So there are soft contact lenses, which are basically caused with just these materials, but there are also soft contact lenses with oxygen permeability, which is created by the presence of these materials. Now, the presence of this oxygen permeability is very important because what it does is when you have a prolonged period of use of these contact lenses, your eyes can get starved of oxygen. But because of the presence of this material, there is good permeability, so there's enough oxygen being fed to the eye through the lens, and that's why you get high degree of comfort. And so you can wear these lenses for a long time. Now, let's look at some of the advances. Without going into too many details, I want to talk about, we talked about the polymerization is generally a free radical polymerization. Free radical polymerization is typically a chain reaction, and therefore it's a very random process. On the other hand, there have been advances in chemistry to create what are called more controlled free radical polymerization through the processes called reverse addition fragment chain transfer, or RAFT, or atom transfer radical polymerization, ATRP. Now, these are unique mechanisms that allow you to regulate the way the free radical polymerization occurs, and due to which now you can have more controlled structures. So you can actually control the architecture, control the reaction by controlling the sequencing of addition of the different monomers that go into making the overall polymer. So if you want a longer chain of the polydimethyl siloxane, you add that into the system and allow it to polymerize, and then you add the other components and so on. So you can do all these things. You can play around with this, with these two mechanisms, RAFT and ATRP. Now, these are themselves topics of their own, and so I don't want to spend too much time on this, but I will be glad to share any kind of references on these if anybody is interested after the talk. Using these techniques, therefore, you can graft additional materials onto the main chain or to the hydroxyethyl methacrylate chain, which is the essence of the your hydrogel that's forming the contact lens. And as a result, you can get improved functionality. So for example, if you consider this is the main chain, you can have grafts done either on one end or two ends, or multiple grafts at a single point. The result is that now you modified the property of the hydrogel with an additional characteristic that is due to the side chain that has been grafted. So some of these are used for example, improving the antimicrobial action. So some of these can be actually help in release of any drugs that are added to the contact lens, or as you know, prolonged wear of these contact lenses can cause your eyes to get some protein deposition. And so, your lens gets dirty after a while. So you can actually add some specific grafts that will reduce this protein deposition. An example of an antimicrobial added is actually incorporating silver nanoparticles into the hydrogel lens to kind of provide resistance to any infection. Other modifications can be that you can graft a surfactant. As you know, when the contact lens is placed on the eye, the lens is in direct contact with the eye. And therefore, at the interface between the contact lens and the eye, there can be some friction and some surface tension. If now you chemically incorporate a surfactant is nothing but which has got hydrophilic and hydrophobic groups in the chain. If you put these moieties onto the hydrogel, now you have created a structure wherein there are hydrophobic and hydrophobic. The blue are the hydrophilic and the red are the hydrophobic. When this material is placed in the eye is a very highly aqueous environment. So the thermodynamics causes these hydrophilic chains to be oriented outward into the eye, while these hydrophobic chains are repelled from this, and therefore they are more concentrated within the hydrogel. The advantage of this is these hydrophobic chains could introduce some new properties to the hydrogels. On the other hand, these hydrophilic groups will cause a reduction in the surface tension at the interface between the eye and the lens, and also increase its comfort or wettability. And obviously that means that you feel less conscious of the contact lens in your eye because there is less friction as it slides across the eye when you blink. So these are some examples of advances that have now occurred in the field of contact lenses. Let us now talk about wound dressings. In wound dressings, as you know, there's been wound dressings have been around, hydrogels have been around for a long time in the in this area. For example, the alginate, the hyaluronan hydrogel, or the carboxylated agarose and tannic acid to regulate the pH at the infection, or chitosan, and other synthetic materials like the hydrophilic acrylics that we talked about, or polyvinyl alcohol or hyaluronic acid. This is a very interesting material, and we'll be talking a little more about that. So there are a number of materials that are already in use. And these are applied, as you know, as films. So they could be a thin film onto like a Band-Aid or any kind of covering. And so when it comes in contact with the wound, the hydrophilic nature allows it to, establish good contact and then function to address the wound healing. And how does that happen? The wound healing could be addressed by either the keratinocyte migration and proliferation. Now, keratinocyte, for those of you who are not familiar with that, these are materials that are agents for causing a regeneration at the epidermal layer. So your outer skin healing is actually facilitated by having a hydrogel that promotes migration and proliferation of keratinocytes. You could also get adhesion to occur and proliferation of fibroblast cells. These fibroblast cells, again, are those that promote cell growth. And obviously, when there is a wound, you have damaged cells, you have infected cells, and you want healthy cells to grow. And so you can promote that by using appropriate hydrogels. Or you can have agents that are added in a controlled release manner to create immobilized growth factor of these cells. And again, the other way is obviously to reconstruct the cell, especially for third-degree burns, where you actually kill a lot of cells. So there are a number of ways in which the wound healing can occur. And the other obvious reason for using hydrogels would be to act as a carrier for antibiotic and anti-infective drug release. Now, let's look at some of the advances. Let's see if I can. Okay. Now, some of the advances are, I think in one of the talks that I was listening today, somebody was talking about phase transition from a liquid to a liquid crystalline material. And so there are temperatures at which transitions can occur. Thermogels do pretty much the same thing. So one example is the poly N-isopropyl acrylamide, and here is a structure. This is a poly N-dimethyl acrylamide, and this one, I'm sorry, it's just isopropyl acrylamide, not dimethyl. This material has got a very unique property in that when it is introduced into the body, it's a liquid. So it's a solution or a miscible mixture with water, and it's got a relatively low viscosity that it can actually be injected into the body. So it's a liquid. But once it's in the body, it encounters the body temperature of 37 degrees, and guess what happens? This material immediately gels. It forms what's called a thermogel because it has got a phase transition temperature called the lower critical solution temperature, and that phase transition temperature is 32 degrees, which is very nice because you can keep it as a liquid, injectable liquid in a syringe, and you can administer it, and it immediately becomes a gel with a very high viscosity, and it fills up the wound space. So these thermogels are very useful, and this material is therefore very, very popular in a lot of hydrogel applications needed in the body. Alternately, there are systems that are copolymers of polyurethanes and dimethyl siloxanes, and these have interesting property of actually inducing electroactive, antimicrobial, and antioxidant performance. So here is a structure of a very generic structure. So this is your urethane structure. So this is your urethane repeat unit. So if you have a polymer with a number of these repeat units that is chemically linked to another polymer of dimethyl siloxane, Now you have a copolymer of these two materials, and they have these interesting properties, excuse me, depending upon the size, the length, and the distribution of these two polymers in the overall structure. You can get interesting electroactive, antimicrobial, or antioxidant performance. So a lot of work, not only in this area, but in other areas of biomedical applications, is not necessarily introducing new materials. Sometimes there is a new material introduced by chemical modification, but it's more tuning the properties of existing materials by altering the composition, altering the morphology, altering the network architecture to give you the properties you need as required in a specific application. Now, in the case of tissue engineering, as you know, tissue engineering is nothing but growing cells in areas where cells have been damaged and destroyed or compromised. And so hydrogels are used in tissue engineering because you know that the cells exist in an environment called the extracellular matrix. Now, the hydrogels can be supports for these because they are very similar to the properties of extracellular matrix, and so they could provide support for growth of new cells. These scaffolds are used in the regeneration of a number of areas like cardiac tissue, cartilage, bone. Now, one of the ways is that you take hyaluronic acid and cross-link it, and it can be used. And we'll talk a little bit more of this application in the next cell. Because hyaluronic acid is an essential component within the extracellular matrix. And therefore, using that itself to kind of cause cell adhesion, proliferation, or differentiation is very advantageous. So hydrogels are used in such applications as I said, scaffold materials. Now, but in order to do that, you have to condition these hydrogels so that they have good structural integrity or appropriate mechanical properties so that they can provide a stable platform for cell growth. Now, these could be biostable, meaning they could be in the body for a long time without undergoing any chemical change, or preferably we use what are called bioresorbable or biodegradable materials, which is introduced, and once its purpose is over, when you have created the cells, when you have completed the function, it can actually undergo decomposition over time and ultimately get excreted from the human body. There are a number of candidate hydrophilic polymers that are used in this manner, among the ones that I told you, like the polyethylene oxide based systems, or even some of the urethane based systems, they can be used. So what are the advances here? The first one is that nowadays tissue engineering is more popularly referred to as regenerative medicine, because the whole purpose of tissue engineering is to grow cells. Now, initially tissue engineering, a lot of the work was done in the laboratory, in your petri dishes, and therefore it was appropriate because these were all in vitro processes. However, now we have known enough of this to actually cause this kind of cell growth within the body or in vivo, and therefore now the term has evolved into regenerative medicine to describe this technology and surgical processes. Such regenerative medicine has actually evolved in a number of areas, including liver and intestine bioengineering, orthopedic bioengineering, renal and cardiac grafting. Now, these are areas where, due to a number of reasons, either due to some sickness or cancer, or things like smoking and drinking, excessive drinking, can cause damage to these components. And then those cells that are damaged can actually be regenerated by using some of the tissue engineering processes or regenerative medicine technology. So there's a lot of activity going on in this area. One example which has been done is the interesting material we talked about, the N-isopropyl acrylamide. But now it is made into a copolymer with polyethylene glycol. So these are what are called reversible hydrogels. And these now are commercially available for stem cell implantation, organ or tissue regeneration. And again, because of this PEG component, this will cause it to also eventually biodegrade. Another is that hyaluronic acid that I talked about, it can be actually cross-linked using UV light with controlled amount of UV light. And this cross-link systems now can create three-dimensional structures, support structures for cell culture. And one of the ways this is done is actually using 3D printing. Now, you are all familiar with 3D printing is becoming very, very popular. And so actually now they have started to do 3D printing of cells using this technology. So these are some areas where tissue engineering has shown growth and continues to grow. Let's talk about cartilage repair. Before we do that, let's look at the microstructure of a cartilage. Cartilage is a very interesting material. It's actually, it's a composite. It's what's called a true composite because it's not a single material. It's not a monolithic material, but it is actually a very composite, complex structure. On the surface of the cartilage, the material is very jelly-like and very smooth and very low friction. This is the surface that actually comes in contact with moving, is there in the interface of moving joints, like for example, the knee joint or the hip joint or the shoulder joint, where there's movement, and this provides lubrication so that there is easy movement. The middle zone is actually a little more transition from this extremely soft material, and this is actually called, I think, cancellous bone, cortical bone, and this will now be actually a little more rigid, and it supports the articulating surface material. And then as you go in, now you see these things start getting oriented. So they now start assuming mechanical property significance. So these now provide support structures for the overall structure. And as a result, this now gets more and more rigid. And then eventually you come to the bone, actual hard bone. Now therefore, this whole complex structure goes from a very soft to a very hard material through a number of different phases. So when we talk of cartilage replacement, it is not an easy task, because when you go to a patient with a damage in the cartilage, like for example, due to osteoarthritis, this is not only gone, but some of this is also gone. So if that is there, then you can't just put a single material on top. You have to somehow reconstruct this. And that's where the challenge comes. So we can think about having copolymers in multiple layers here. So you have a cartilage-like hydrated hydrogel right on the surface, which will be lubricious, and it will be compliant, it will be soft, and it will bear the pressure and the load of the moving joint. And then you have some transition where, you can actually go from this very soft structure to the hard structure that can be attached to the bone. And actually, this can either be a single or a gradient copolymer. The important thing is you see the imaginary dotted lines that I have shown here. They are separating the different zones. But ideally, what you want is you don't want a hard or a discontinuous transition. You want a more gradual gradient transition all the way through. And that's where the challenge lies in order to create systems that will be cartilage replacement. And therefore, this is the next frontier in copolymers where there's a lot of work going on. Let's talk about drug delivery. Now, drug delivery is something that's very obvious. You have drug delivery already in both oral and intravenous systems which use hydrogels. For example, most of the capsules that we now have for time release of the drugs, when we take it orally, these capsules are made up of hydrogel materials. So if you take a capsule and you have your hands wet with water and you try to touch it, after a while you'll see that outer surface will start dissolving. That's because it's a hydrogel. So these hydrogels are there to regulate how fast, instead of dumping all of the drug at the same time, it releases it over 7 or 8 hours. So time release capsules, as they're called. So we are already familiar with that. Now, the advances, there are a number of advances and the number of ways in which these drug release can be controlled. One good example is using this nitrosalicyl imine chitosan hydrogel, which is basically a reaction here between the salicylaldehyde with the chitosan, which has got these amine groups. The reaction of the aldehyde with the amine forms the imines, and you have this very intricate structure, which now can provide a sustained relief of release of these drugs in a number of local therapies. Another interesting system is a copolymer of polyethylene oxide and polypropylene oxide. These are called tri-block copolymers because you have a block of polyethylene oxide that's then linked to a block of polypropylene oxide, and then which is then linked to a block of polyethylene oxide. Depending upon the ratio of polyethylene oxide and polypropylene oxide, you will change the amphiphility of the material. Now, what do I mean by that? That polyethylene oxide is hydrophilic, while polypropylene oxide is relatively more hydrophobic. So by changing the balance, you can change the balance between the hydrophilic and the hydrophobic. And that would allow you to have a versatile material for both hydrophilic and hydrophobic drugs. So one example is that you load it with the drug tetramethylpyrazine, and they actually can regulate how much time it takes for depletion of the drug. And so these are very interesting systems again. So I would like to emphasize that while some of these materials are new materials generated through chemistry, really what you're trying to do is you're trying to design the system based upon what your need is. If it's drug delivery, do you want the drug to be, for example, there are some cases where you want a very rapid release of the drug, like a pain-killing drug. You want it to be released very quickly because you want to give immediate relief to the patient. So then you want it to be released within an hour. In other cases, that you're managing the pain somehow, but you want the antibiotic to be released over, say, 3 days, so that the infection can be prevented. In that case, again, you modify your hydrogel system that will act as a drug release. So there's, again, so much of thought has to go into designing materials based upon the functionality. Because of the amount of time, I'm already running close to the end of my talk. So therefore, I want to just wrap up with a few conclusions. Polymers and copolymers are available with hydrophilic groups that can yield hydrogels for biomedical applications. We've already seen a number of synthetic techniques. Hydrogels can be therefore customized for what properties we need to achieve. Similarly, increasing demands and technology developments have now caused us to create new and newer hydrogels. So with that, I would like to conclude my talk. And in final, I would like to acknowledge the organizers of the symposium for a chance to present to you. It is my pleasure and privilege to have participated in the symposium. And I would like to also thank Professor Bhattacharya, who's communicated with me very hard over the last few months to make sure that we get all this process done in order to talk. So once again, sir, thank you very much for your opportunity. And I will be remiss if I do not mention Professor Prabhu, who was my first teacher in physical chemistry and who taught me the fundamentals. And I'm where I am today. I can blame him for that. Thank you very much.
Thank you, sir. Now platform is open for question answer. We can accept few questions from audience, please. I think no questions. Okay, thank you, sir.
Thank you, Professor Bhattacharya. And as I said, that if there's any aspect of my talk that someone needs to talk, you have my contact information. I'll be glad to respond by email.
Thank you, sir. Thank you. Thank you, sir, for your excellent and informative, elaborate presentation on the advancement in the hydrogel biomaterials, which find applications in contact lens fabrication, wound dressing, tissue engineering, drug delivery. Sir, you have talked about the development of hydrogels via controlled free radical polymerization involving PVA, PEO, NVP, chitosan, PNI, PAA, these monomers. Also, this lecture covers the chemical modification of hydrogels employing surfactants to enhance the wettability and the lubricating properties. So, very nice presentation, sir. I wish a significant progress in your future research. Thank you, sir.
Thank you very much. It was a pleasure.
Thank you, sir. We'll be in touch.
Yes, thank you, sir.
Through email. And if possibly, if you come to India, I will try to meet, sir. Definitely.
Oh, it would be my pleasure. Thank you.
Okay. So now I want to hand over this platform to Professor Pandey, Professor M. Pandey. Thank you.
Okay. Good morning. Very good morning, Professor Prabhu, sir, an organizing committee member of NCCT 2021 and keynote speakers and all my participants. We like to take the permission from Utpal Bora sir to introduce about him. Sir?
Yes, sir, please.
Okay. Sir, we faculty from the chemistry department of SMIT would like to welcome you and like to introduce about you among our participants. So I'll give you some small brief about you. Dr. Bora sir, at present, he is Associate Professor in the Department of Chemical Science, Tezpur, Assam, India. He did his PhD from CSIR, Northeast Institute of Science and Technology, Jorhat, in 2005 under the supervision of Dr. Ramesh C. Barwa. And he also did his JSPS postdoctoral research fellowship from Gifu Pharmaceutical University, Gifu, Japan in 2007 with Professor Hiranao Sajiki. In 2008, he joined as Associate Scientific Manager in Syngene International Limited, Bicon, Bangalore. Before joining the Tezpur University, he served to the Department of Chemistry, Dibrugarh University, Assam, as Assistant Professor between the period of 2008 and 2013. At Tezpur University, he is working on the development of various routes of cross-coupling, oxidation, and carbon-hydrogen activation reactions for the synthesis and fictionalization of potentially bioactive heterocyclic molecules of pharmaceutical importance. He has been awarded with the JSPS Postdoctoral Research Fellowship by Japan Society for the Promotion of Science during the period of 2005 to 2007. He also awarded with INSA Visiting Fellowship in 2012 by Indian National Science Academy. He also awarded with the JSPS Bridge Fellowship by Japan Society for Promotion of Science 2013 and DBT Overseas Association by Department of Biotechnology, Government of India in 2017. He has co-authored in more than 100 papers, peer reviews, internationally reputed journal, and his research area on catalysis, synthetic methodologies, and green chemistry. I am very happy to invite you as keynote speaker to address your topic on a study of alternative cyanide sources to the synthesis of aryl nitrite. So I would like to start your topic and enlighten to us with your knowledge. Thank you, sir.
Thank you, sir, for your nice introduction. I would also like to thank Professor Nayan Kamal Bhattacharya for his invitation to deliver my lecture here in this conference. Okay. So today I will be talking about the study of the alternative cyanide sources to the synthesis of aryl nitriles. Actually, basically my talk will be of two parts. One is somehow general type for our students, and in that way I will justify my work. So why I have to work this type of chemistry, and as well as in the later part I would like to emphasize on our developments on the alternative cyanide sources. So in our previous lecture, Professor Venkat Narayan elaborated, and from his talk we have understood that his chemistry is directly related to mankind. That means the use of contact lens. So he doing his research, and that has a direct applicability in the humankind, because I can also use that contact lens. Arthritis key is a problem. Pain in the knee is a very problem for our aged people. So that things are there. So people understand that this work has very meaningful for our society or people. But as a chemist, so why we need to synthesize different organic molecules? So why we invest so much time, money, energy in designing new synthetic routes or synthetic methodologies and catalysis? So that we should understand. Okay. So before going to that main things, I just want to elaborate that many people in this world have problems with different bacteria, parasites, virus, fungi, etc. And recently we all are under attack from the COVID-19 virus. So that means we are having some disease. All people at different time we have facing different diseases. So disease can be divided into two parts. Some is infectious disease like COVID-19, because you can see that COVID can be infectious from one person to another. So now we are so much careful that we have to maintain the social distancing. We have to wear the mask so that that virus cannot attack us. Similarly, bacteria, malaria parasite, fungi, these things can attack us, and we may be attacked by different diseases. Similarly, some other non-infectious diseases are also there. Maybe body part wear out, like so heart attack, stroke, cataract, etc. So there may be some harmful thing can come to our body, which may have some problem for us, like allergies, asthma, some poison may be there, some snake bite may be there, so smoking is a problem. So these diseases caused by entering some harmful material to our body. There are some things also. Our body in India, we can see the many people are under malnutrition. They have anemic. Okay, these are the problems of the people. So common people, and some people have the problem in their birth also. So to overcome these all diseases, whether either it is an infectious disease or it is a non-infectious disease, we need some medicine. Interestingly, most of the medicines containing heterocyclic compound. Heterocyclic compounds means either oxygen, nitrogen, or sulfur. And basically we chemists are trying to synthesize this type of molecule. We want to develop easy route for this, for the development of different molecules. That's why we need to do synthesis. And it is completely related to the medicinal chemistry when we deal with the heterocyclic compound. Now, what is medicinal chemistry? So it is you can see this molecule, it is a paracetamol, everybody use, and even nowadays during the COVID period, when we use when we have some fever, we have this medicine is prescribed to us. And if you see the synthetic route of this molecule, you can see that we can easily prepare this molecule in a undergraduate lab. Just starting from the phenol, we can do this nitration reaction, we can get two products, then we can do reaction, and then we can do a acetylation reaction and everything this product. So still people are using this paracetamol under different brand name and get relief from pain or fever. Similarly, it is another very important but very cheap drug molecule is aspirin. You can see this molecule also we can synthesize even in the undergraduate lab. During our BSc laboratory also we synthesize this molecule, and you can see just acetylation of this product will give this.
Dr. Bora, just your slide is not changing. Can you check once?
Is it changing now? Is it okay?
Not changing.
Okay.
Pandey sir, is it changing in your system? Since it is constant in my system.
It is not changing. It is fixed one.
Just can you reach here once?
Yes, yes. Okay.
Now it is okay. Now it is okay.
Now it is okay?
Yes, yes, yes.
I think see PPT mode, if he will keep, that is better, sir.
Now it is okay?
Can you keep it in PPT mode?
Please go to the PPT mode. Yeah, then I think.
No, it is in the PPT mode only.
Okay. Anyway, yeah, please go ahead.
So is it now, have you seen it now?
Yeah,
Yes,
now
yes,
it is slide 7.
It is now changing?
And now it is showing the slide number 7.
Slide number 7. Okay.
Please click.
Now actually it is in 8. Now it is?
It's still 7.
It is 7. Now I have changed it to 8. So is it, so have you seen it?
No, no.
Okay.
I think please stop sharing and
new share. Okay, I will do.
Yeah, yeah.
Is it okay now?
Yes.
Is it okay?
Yes.
Yeah.
Okay. Okay. So
now 7 number, how people know that these molecules can be used. That slide is in front of us.
Yes, yes. Now it is okay. I come to
Yes,
slide number 8. It's okay.
Yeah.
Okay. So now, so already we know that these two are very important drug molecule. So in that way, how people know that these two are very important drug? So that means in laboratory we use we synthesize different molecules, but from the thousands of molecules, how we can know that this molecule will be a appropriate drug for this type of diseases? So that means we have to think who will prepare how you allow. So I have synthesized this molecule. Who will allow? Who will regulate that this is a drug molecule? So all these things are coming under medicinal chemistry. Even medicinal chemists also see the issue of the safety issues, whether this drug has toxicity or not, the possibility of improvement of the quality. So these things are there. Now you can see that there is a link between organic chemistry and medicinal chemistry. So after biological evolution, that this type of molecule may be useful for this type of drug. You can do it by computational studies or different studies. Then some new target molecule has been identified, and this target molecule has been synthesized by the organic chemist. That means organic chemist has to synthesize a target molecule, and then that target molecule again go for biological evolution. So if some molecule shows the potentiality of the drug, but it is somehow toxic, then we have to again modify the structure. So that part is done by the organic chemist. So that is the link between organic chemistry and medicinal chemistry through this circle. Okay. That means to get the lead molecule, organic chemist has a role. Now let us come to our main topic. So why I just with this background that why we need some organic molecules, why we have to develop some synthetic methods. This can be seen that why the cyanation is important. So if we start this cyanide molecule, alkyl cyanide, so this can be converted to different compounds. Suppose this we can convert it to the ketone, we can convert it to the pyridines, we can convert to the aldehydes, we can convert it to the thiazoles, we can convert it to the amides, we can convert it to the triazoles, we can convert easily to the carboxylic acid, we can convert to the tetrazoles, and also we can convert it to the oxazole molecule. That means if we have a good cyanide molecules or alkyl cyanide or alkyl nitrile molecule, then we can prepare different molecules, even it may be heterocycle or other functional moieties. So these molecules has a very important part, maybe in the pharmaceutical sector, maybe in the agrochemicals, maybe in the drug molecules, or maybe in the functional materials, or even in the natural products. These are available. So here I show some one or three molecules which have some role as a medicine prepared from the or having the cyanide group or nitrile group in its structure. This drug is saxagliptin is used for the type 2 diabetic. This is used for the HIV infection, and this is anti-cancer agent. That means all these molecules have cyanide molecules in its core structure. That means CN group has also a role in the activity of this molecule. Moreover, so if we we develop some easy method so that we can incorporate cyanide group in this molecule, then that medicine, that synthesis of this medicine will be more easy. Now, all of us know that traditionally we prepare cyanide from the Saint-Meyer reaction, which is discovered in 1884. This is started from the aniline, then it is the diazonium salt is prepared at 0 degrees centigrade, and with the copper cyanide molecule, this nitrile, so benzyl nitrile or this cyanating compound is synthesized. And this method, although some very useful or traditionally used, even we synthesize it in our many undergraduate laboratory courses, it has some limitation. Stoichiometric use of the toxic metal cyanide, diazonium salts are very unstable, violently explosive, and undergo rapid decomposition, and higher reaction temperature is required. So additionally, another method is the Rosenman-Von reaction, which is discovered in 1914, where from alkyl halide, bromide or iodide with copper cyanide at 150 to 250 degree, that cyanation reaction can be carried out. So these reactions also have some limitations. So it is a toxic material which has to be used as a cyanide source. Use of high boiling solvents make the purification product difficult, and high reaction temperature is required. So at this point of time, I would like to share that now people are talking about the sustainable development goals. So all these methods which is used for the preparation of these cyanide molecules previously is not useful, do not provide us that sustainable development goals. So from that point of view, we have to develop some new cyanating sources, okay, in the line with the sustainable development goal. So how we can synthesize this? So these are the alternative cyanide sources previously used. So most commonly used earlier part, and all these are you can consider it as some toxic. For example, hydrogen cyanide, potassium cyanide is very toxic molecule. Sodium cyanide also toxic. So zinc cyanide, potassium thiocyanide, trimethyl thiocyanide. So these molecules are used previously, but it is not so much safe. And gradually, people come to the alternative cyanation sources like acetonitrile, which is used as a solvent in many organic reactions. That compound can also be used as a source for the CN group. Similarly, benzyl cyanide, trimethyl cyanide, this NCTS. So these all are butyl thiocyanate, benzyl thiocyanate, DDQ, CH3, HCN, AIBN. So these are organic sources of the cyanation reaction. So using these organic sources, we can do the cyanation reaction. These are also effective cyanating agent, but these are relatively toxic. So these are organic cyanide sources, relatively more acceptable, means toxicity is gradually decreasing. People are doing that decrease in the toxicity level. And so another people are also able to develop different cyanating sources by combining different two organic sources. That means if we combine dimethyl formamide and ammonia, dimethyl formamide or ammonium iodide, this ammonium bicarbonate plus DMSO, urea, DMSO, or nitromethane. So these are relatively so stable or safe nitrile source. You can see from DMF, carbon sources come, and for ammonia, nitrogen sources come, and we get the CN. Similarly, this is the same thing. Here also DMF provides the carbon source, and ammonium iodide provide the nitrogen source. So here DMSO provide the carbon source, and this ammonia provide the nitrogen source. Similarly, from urea, nitrogen is coming, so DMSO giving the carbon source, and this nitromethane can also be used for this cyanation reaction. So gradually, people are able to develop less toxic cyanating sources. So now what kind of substrates can be cyanated? You can see these alkyl halides, thioethers, N-heterocycles, aryl boronic acids, electron-rich arenes, all are there. This can be cyanated to give this product. Suppose this alkyl halide, we can cyanate to get this product. This can be a this is a directing group. We can directly insert the cyanide group here, this nitrile group here, or alkyl alkene, we can the cyanation at this point. Even for the indole molecule, cyanation can be done at the C3 position. So using these cyanating sources. So now our first experiment, actually we are doing this reaction using this alkyl halide and using nitromethane as a cyanating sources, and eventually we were able to do the cyanation reaction. Actually, this reaction is very interesting because initially we are not aiming to synthesize this benzyl nitrile or aryl nitrile. Our aim was to do CH activation here and prepare insert this group here. So eventually we want to prepare benzyl nitro compound, but we end up after all NMR, IR, mass analysis, we end up with this this cyanating this alkyl benzyl cyan compound. So that means benzonitrate. So in this process, that although result is not at per our expected line, but we are very excited to have this result, and we do further research, and we found that we were able to generate in situ reduction of copper 2 to copper 1, which eventually do the reaction. This is a very non-toxic and cheap CN source. We have do some computational studies also, and as I mentioned, we have done different optimization reactions, and then we found that this is the best possible condition using this copper nitrate source, DMSO as a solvent, using this nitromethane, and we use the ligand 5 mole % phenolphthalein ligand is used, and we get this base condition. And based on this available base condition, we do the reaction with different substrates. You can see here and that copper nitrate is used as a catalyst, 5 mole %. 110 phenolphthalein is also used as a ligand. This is very important. And then potassium carbonate is used as a base, the solvent BMSO, we get this product. So this general general aryl halides and iodide and bromide, we prepare different cyanide or nitrile compounds, and even this type of system also we can use for the cyanation reaction. Similarly, pyridine can also be done cyanated with this reaction system. And we have also studied some mechanistic studies of this reaction, and we found that this formation of this copper phenolphthalein complex from the HRMS data, and then we also studied the oxidation state of the reaction at the start of the reaction and the end of the reaction. We found that actually the in situ reduction of the copper 2 complex to copper 1 complex has done the reaction. So these are from UV studies. We probed the complexation, and also the oxidation state is studied by this EPR and this cyclic multigram. We propose this mechanistic route, although it is a very tentative route, but best possible we can explain this reaction with this mechanism. This 3 parts basically. In A, that complex is reduced to the copper from copper 2 state to copper 1 state with this nitromethane, and then this in the cycle B, you will find that this from this nitromethane under the reaction scheme, we get ACN. Actually, the ACN is the cyanation source, which is generated from the nitromethane. These all are possible route. First, the base is abstracted 1 proton, then dehydration takes place from this step, species 2. Then this oxide is formed, which with the help of water, this species 4 is formed. Then With this copper catalysis, this HCN is liberated, and then in the cycle C, this iodo compound, so aryl iodide, come with the oxidative addition step here, then ligand exchange takes place at this point, and this complex was formed, and then ultimately the reductive elimination give this cyanation product. We have also studied the theoretical study for support of this molecule or support of this proposed rules. And in our next work, we use this steric ammonium nitrate as a cyanating source in presence of DMF. That means DMF gives the carbon source, and then this steric ammonium nitrate give the nitrogen source. And what is advantage of this reaction? Usually you can see that all the aryl halides, aryl boronic acid, organosilans, etc. Require metal and solvent plus nitrogen source, ligand, additive, oxygen in balloon. But here we found that CAN is doing all these things. Okay, can be used as a nitrogen source, can be used as a ligand or additive, what you can say, or can do the oxidation part also during the course of the reaction. Now again, like previous cases, we do the different optimization reactions, and we found that the copper triplet in presence of DMF, in presence of a base, we get the best results from these studies. And again, we try to optimize the equivalent required for the CAN and the copper triplet, and we found that 30 mole percent of copper triplet is important for this reaction, and 1.5 equivalent CAN is very important for this reaction. And again, we do a lot of substrate studies in this using this protocol. We carried out different reactions. You can see these are general aryl halides, iodide and bromide, both we have tried, and we were able to do the cyanation reaction. And some complex structure or heterocyclic structure like pyridine, this thio compound, these all are can be applied under this reaction condition. Even in indole, you can do this cyanation reaction. We have used a lot of reactions to probe the mechanism and role of our different reagents we used. First, we found that without copper, the reaction did not proceed. This is CAN, and this no reaction take place. And then we use the substrate, that means toluyl iodide, 4-toluyl iodide, 4-methoxyiodide, and CAN. Even the reaction can be carried out with the help of palladium, but yield is less, and also the palladium is expensive. Therefore, we did not go with the palladium. Then nickel can also be used under this reaction condition, but yield is less, and we concentrate on the copper. So instead of CAN, we can use cerium chloride. So we found that no reaction is happening without any nitrogen source. Here only ceric chloride is used, no nitrogen source is given, and at that point no reaction was observed. And we even get result using other nitrogen sources. So this ammonium sulfate can be used under this reaction condition, but yield is relatively less. And without any nitrogen source, the reaction did not take place. And this reaction can be carried out under nitrogen atmosphere also. That means CAN has a role as an oxidant also. We can prove this from this reaction, which is carried out under nitrogen atmosphere. Similarly, we also investigate the role of the potassium carbonate, and we found that the reaction did not proceed well with KCl. That means potassium carbonate has a also some significant role in this reaction. So this is the proposed mechanism. Can with the help of potassium carbonate, this is formed, this complex is formed, and this is the counter ion which is stabilized by potassium. Then this decomposes to ammonia. Okay, then this ammonia react with DMF, and then DMF and ammonia can form this cyanide ion, CN ion, and with the help of this catalytic cycle. And then this methoxy compound, pour methoxy iodide inserted in the catalytic cycle, then insertion is going on, then ligand exchange take place, then this is intermediate is formed. With the reductive elimination, we get this product. Okay, and we have also tried to understand whether that the carbon is come from the DMF or other sources. So we found that this level experiment did not give the result. Okay, so I would like to conclude both the strategy like this, a simple and is accessible copper salt we use for both the methodologies. Homogeneous catalyst in both methodologies suppress the disadvantage in the preparation of handling of the modified metal catalysis. New combination is developed, CAN and DMF, and CAN and CN is both can be utilized to minimize the toxicity of the cyanide sources. Lots of substrate, variety of substrate can be carried out with this reaction protocol. And we were able to publish this paper in EJOC, and this is recently accepted in Organic and Biomolecular Chemistry. So all these are our helping hand. Professor Sajiki's research group in the Gifu Pharmaceutical University, we have collaborated with them for this reaction. So that's financial support from DST, SCRB, CSIR, UGC, and Tezpur University are gratefully acknowledged. So all this work which I presented is done my research scholars. These are now current member. And this Rakhi Soikia has done both the cyanation reaction. Okay. So with this, I would like to conclude my talk. I think within the time, stipulated time, I can conclude it. So thank you. I'm again thankful to Professor Bhattacharya for his invitation and giving me chance to share my research work with all of you. Thank you.
Thank you, sir. Thank you, Bora sir, for enlightening the lecture on the alternative cyanide source for synthesis of aryl nitrite and the reaction mechanism. Now the floor is open for question and answer. Does anyone have a question for Dr. Bora sir? Any question? Any doubt? Or if anyone want to know about the some mechanism? No. I think the no question is coming from anyone. So here we like to say the thanks to Bora sir, as he shared the knowledge about the medicinal chemistry as well as the role of organic chemist in the area of medicinal chemistry. As well as you nicely shared the importance of cyanation and application of nitrile and cyanide groups for the development of the anti-cancer chemicals. You also nicely explained the alternative source of cyanide, how to shift the use of high toxic sources to low toxic sources. And you nicely explained the reaction mechanism when you use the low toxic sources. And I hope that will helpful for the further research work to the interested person. Thank you, all of you. So I would like to close this session. Thank you. Nan, sir.
Yeah, Dr. Utpal, thank you for accepting our invitation and for your nice presentation in this conference. Definitely participants are benefited. And I look forward in future also you please join with us maybe in offline mode, we hope.
Sure.
And when I come to Assam, definitely if Terspur side we will meet.
You never visit. You never visit us. Please visit us sometime.
I would like to visit your university, and I think last around 15-20 years we have not met, right? I would like to visit.
So please, when you come to your home, Jorhat, just if you not come by flight, then please visit us.
Okay. Thank you so much. Thank you. Handing over to Ashwin.
Thank you, sir. We will now begin the fourth session, technical session of the conference. This session will be chaired by Professor N.K. Bhattacharya, SMIT, and Dr. Joydeep Biswas, SMIT. I would request both to kindly take over the session.
Thank you, Ashwin. I think let us wait 1 minute since our time we have given as from 12 noon. I hope presenters are already joined in the meeting. In this session, we have 7 papers. This is technical session 4. I welcome all the participants and all the delegates to this session. After this, next session will also be from 1:10 to 2:20. That is technical session 5. I request presenters to be ready for the presentation in the next session also. Okay, let us start. May I request paper number 25, OP25, Mr. K.D. Badave. If you are present, you can come forward to present your paper. Mr. K.D. Badave. If not, let us move ahead. Mr. Vivekanand B. Jadhav. Mr. Vivekanand B. Jadhav.
Yes, sir, I am present.
Okay, please continue. You can share your slide. Your time is 10 minutes. I request to conclude before the given time.
Yeah, I will try my level best.
Please.
Yeah. So, sir, the screen is visible. Hello.
Yeah, it is visible. You may continue.
Yeah, so very good afternoon, one and all. Myself, Dr. Vivekanand Jadhav,
If
assistant.
possible, make it the PPT mode.
Okay. So, good afternoon, one and all. Myself, Dr. Vivekanand Jadhav, Assistant Professor in Chemistry from Sri Muktadan College, Gangapur, from District Aurangabad, Maharashtra. And today's topic for my oral presentation is silica-supported phosphorus pentoxide as an efficient and recyclable catalyst for the synthesis of bispyrrole derivative in aqueous conditions. So, as per the literature survey,
can you make it full screen, Dr. Vivekanand? Can you make it full screen?
Yes, sir. Already I have made it full screen only from my side.
Okay. Anyway, go ahead. Go ahead. Go ahead.
Yeah. So from the literature surveys, we observe that there are some pyrazole containing important drug molecules are there, and that contains pyrazole structures which is having some potent biological activities. And it is observed that nitrogen containing not only pyrazole, bispyrazoles, and some related drug molecules are there. They are having some potent biological activity. That activities may consider that they are bactericides, fungicides are there. They are some anti-inflammatory, analgesic, and they are having some many more potent activities are there. In this, one of the most prominent activities that they are used for the treatments of Parkinson's and Alzheimer's diseases also. So, inspired by this, all findings and all these biological activities and earlier reports, we observed that during the synthesis of this pyrazole or bispyrazole-like compounds, there are some.
Dr. Vivekanand.
Yes.
We are not, your slides are not moving at all.
Yeah, it is on first slide only. Okay. Yeah. Now it is moving. So no, I am now on the next slide now.
No, I think if you share it, first switch off and then reshare it, then it is possible. Otherwise, it always comes the problem.
Yeah. Once again, I will reshare.
Now it is okay. Changing.
Okay, na? Okay.
Yeah, okay, fine. Continue.
So the basic idea behind this methodology is that we want to check whether additional pyridyl moiety can enhance the biological activity profile of the newly synthesized molecule, that is the bispyrrole. Again, we want to explore the activity profile that behind the reported activity, whether this bispyrrole molecules may possess some additional biological activity. Again, during this study, we want to study whether we can synthesize some drug lead candidate molecule which can be used as a future drug molecule. So this is the basic outline of this. My proposed scheme is that we are using some different various substituted aromatic aldehyde, and we are using some commercially available pyrazole compounds, and we are treating this with silica supported phosphorus pentoxide in ethanol water at 80 degrees Celsius temperature so that we can get bispyrazoles. And for this to achieve this, what we are doing, we are using some different parameters we are using, and in the first case we are using in model reaction as we are treating benzaldehyde with 1 millimole with taking 2 moles of pyrazoles, and we are using screening in different solvents, different catalysts in different mole percentage of catalyst. Again, we are taking different temperature conditions also. This is this first basic slides of my presentation. In this, we have first taken screening of solvent, and this for screening of solvent, we have taken some with previous assumption directly, which started with ethanol water, so that it will be more soluble and the reaction will be more faster. And we have performed this reaction on firstly on room temperature, and suddenly what we thought that if we increase the temperature of the reaction, so there might be some reduction in reaction time. That's why we have taken the same solvent system, reaction systems, and we have treated this reaction at 50 degree, 80 degree and 100 degrees Celsius temperature, and we observe that the reaction is moving smoothly within a 30 minutes of time whenever there is a more electron withdrawing substituents, and we are getting a very good yield of amount like at 50 degrees Celsius temperature, at 90, 80 degree 90%, and 100 degree there is not some substantial increase in the yield of the product. After that, as I told, we have done some screening of temperature and we observe that the reaction is moving very nicely, giving 90% of yield of product at 80 degrees Celsius temperature itself. So we assume that the reaction performs well within 30 minutes of time at 80 degrees Celsius of reaction of time as compared to 50 and 100 degrees Celsius of temperature. After that, what we have done, we have checked it percentage mole of the silica supported phosphorus pentoxide compound catalyst, sorry. So we observe that when we take 0, 5, 10 and 20 mole percent of catalyst, we observe that only 10 more percent of the catalyst was sufficient to carry out the conversion. If you take 5%, it is giving only 52% of yield, but the reaction duration was very long. And if you take like 10%, it is giving 90% of yield. And if you take 20%, it is giving only 91% of yield. That means if you take the reaction condition at a higher mole percentage, there is having only 1 or 2% of increase in yield of the product. So these are the some of the prime NMR structures of the compound that we have synthesis. We have taken 3-nitrobenzaldehyde and we have formed this bispyrrole compound. This is the NMR that we have taken at initial stage.
This slide is not moving.
Yeah, it is moving, sir. It is slowly moving actually. Now it is moving.
No, not at all. It is in the first slide only after the intro. That is the basic idea behind this methodology. I think some problem.
Yes. Now
you can try once, otherwise go ahead.
Yeah, actually now I am at the end of this slide, conclusion slide now. I am actually sure. Yeah, once I will check. Now it is moving.
Yes, now it is moving.
Yeah, so means without presentation mode only it is moving. So anyhow, this is the brief idea, that is I have taken this mole percentage of this catalyst, in which I have taken different mole percent of this catalyst like 5, 10 and 20 mole percent of catalyst. And in this, as I told, that at the 10 mole percent itself, it is showing a good amount of, that is 90% of it. And this is some of the major characterization that I have done with 3-nitrobenzaldehyde. I have taken the NMR. I have also taken the mass spectrum of that 3-nitrobenzaldehyde bispyrrole compound, and this is the 13C NMR of that compound. Again, in addition to this 3-nitrobenzaldehyde, I have taken some electron donating benzaldehyde, that is paramethyl benzaldehyde. Again, electron withdrawing or semi-electron withdrawing, that is parafluorobenzaldehyde compound. So I have taken around 12 to 14 compounds, but as a representative, I have shown only 3 to 4 compounds in this my particular slide. So in conclusion, thus to conclude, we are successful in synthesizing and developing a newer approach to performing a two-component synthesis of pharmaceutical valued bispyrrole and its derivative by recruitment of silica-supported phosphorus pentoxide. Further, we are successful in exploring catalytic activity of this silica-supported phosphorus pentoxide, which is a cheap, mild, environmental, benign, non-toxic and recyclable catalyst. In this particular methodology, we have not tested its recyclability, frankly speaking, but it is a recyclable catalyst, as it is evident from the literature. Again, the present protocol has many advantages over the existing approaches that we include, like use of cheap and non-toxic catalyst. Operational simplicity is there. Just we have to filter. Again, it is giving higher yield of the product with the shorter reaction of time in ethanol water system. Finally, I would like to acknowledge some of the people who really inspire during performing these particular methods. In this, first is our Honorable Principal Dr. Iman Sir from our college. And I would like to thank the site Chandigarh for NMR analysis of compounds. And again, I would like to thank all the organizing committee members from Department of Chemistry, Sikkim Manipal Institute of Technology for organizing such a nice and wonderful conference. And I am ready if you have any questions.
Okay, thanks, Mr. Vivekanand, for your nice talk, and thanks for finishing it up in time. So the house is open for questions, query. Anyone having any question? Just 2 or 3 short questions. Okay, if there are no questions, thanks, Mr. Vivekanand, for your talk.
Yeah, thank you.
Can you please unshare your?
Yeah.
Yeah. So the next presenter, OP27, Hanmant K. Kasralikar. Are you there, sir?
Yes, sir. Yes, sir.
Okay, please share your screen and you may continue.
Thank you, sir. Thank you. Good morning to all of you. My present, I am audible, sir. Hello.
Yeah, it's okay.
Yes, okay. My presentation topic is the synthesis of chrominochromins using L-proline based thiourea organocatalyst and their anti-HIV activities.
Excuse me, can you just increase your sound or you come little closer to your screen?
Yes, sir. Yes, sir. Yes, sir. Now, here we have used the organometallic complexes, organometallic catalyst for the synthesis of chrominochromins. In first section, we have synthesized the organocatalyst, that is 1,2-dihydro 1-phenyl 5-S-pyrrolidine 1,2,4-triazole thiones. In short, we call it as DPPTT. We synthesize this thiourea-based organocatalyst from the Bock protected L-proline. This is converted into corresponding acyl chlorides on treatment with the sulfonyl chloride, and this acyl chloride is converted into corresponding, that is isocyanide group, and this isocyanide on treatment with the phenylhydrazine, it will use the corresponding this type of triazoles, and this triazole or this type of thiourea based, that is the triazole ring, is again deprotected when this Bock protected thiazole compounds, that is with the methylene dichloride trifluoroacetic acid, it is to be heated or stirred for 1 hour. The deprotection of this Bock takes place, and it is converted to corresponding, that is thiourea L-proline based, that is thiourea L-proline based thiourea catalyst, and we have applied this catalyst for the synthesis of use this type of organocatalyst for the synthesis of 1 minute, sir. Slide is not moving. Just I will take back.
Excuse me, you are having any technical problem?
Yes, sir. Slide is not moving. I'm sharing slide.
And can
again,
you
sir.
check? Can you check your? Can you check your audio also sound?
Okay, sir. Okay, sir.
Hello.
Yes, sir.
Yes, you please continue.
Yes, sir.
Hello.
Okay, without power.
Yes, yes, yes.
Yeah, you
Yes,
present.
this is the.
Yeah, it is visible.
Yes, sir. Audible, sir? I'm audible?
Yeah, yeah, audible. Continue.
Yes, yes, sir. Okay, now this is the organocatalyst which we have to use for the synthesis of organ, that is the chromino-chromine molecules. Okay. Then this is the proton NMR spectra for this thiourea-based L-purulin organocatalyst. This is the C13 NMR spectra for the same organocatalyst, and this is the MS for the synthesized organocatalyst, which we have to use for the synthesis of its chrominochromes. And this is the HPLC, which we have used for the separation of the two isomers, which is to be obtained from the L-purulin for the synthesis of this thiourea-based organocatalyst. Here in this case, in the section 2, we have synthesized these chrominochromes by using this type of chrominochromes by using the thiourea-based L-purulin organocatalyst. These chrominochromes have different types of applications. They have the medicinal as well as the pharmaceutical applications, including as anti-HIV, anti-cancers, antifungals, antibacterial, and anticoagulant activities. By taking into consideration all the applications of these chromine compounds, and by using such type of literature procedures or synthetic methods which we earlier used, we have used this organocatalyst first time for the synthesis of the corresponding chromino-chromine derivatives. For the synthesis of these chromino-chromine derivatives, we have used the salicylaldehyde with, that is, quinoline, and this one it is to be treated with the indole as well as the barbituric acid. When we use this type of substrate molecules in ethyl alcohol, and we have add the DPPTT as a catalyst, and if it is to be replaced for 12 to 14 hours, then we will get the corresponding the chromino-chromine derivatives. Once we have used the indole as a carbon nucleophile for the formation of these chromino-chromine derivatives, and in the second case we have used, that is, the barbituric acid as a carbon nucleophile for the synthesis of the chromino-chromine derivatives. Okay, these are the certain, it is the optimization of catalyst and the solvent that we have used for the preparation of the chromino-chromine derivatives. We have used the different types of catalysts, and it is observed that the whatever may be the DPPTD catalyst that we have synthesized, it gives a very good aid with a minimum time in ethyl alcohol and within only the 10 mole% of the catalyst, and we will get the 90% yield by taking into consideration this optimization of the catalyst and solvent for the preparation of chromino-chromine derivatives. We synthesize the different types of chromino-chromine derivatives by using the indole and barbituric acid as a nucleophiles with the corresponding salicylaldehyde and the quinolines. Here we will get this type of that is the we have obtained the 17 derivatives of chrominochromes, and after that these are the derivatives of chrominochromes that we have obtained from using the thiourea-based L-protein organocatalyst. Okay, this is the NMR IR spectra of the chromino-chromine derivatives. This is this NMR spectra of the corresponding synthesized derivative. It is the C13 NMR of the compound, and this is the GCMS of the synthesized chromino-chromine derivatives. Now here, this synthesized compounds, the chrominochromine derivatives which we have synthesized, we have used it for the molecular docking studies as an reverse transcriptase inhibitors. The reverse transcriptase inhibitors are of three types. That is, one is nucleoside analog reverse transcriptase inhibitor. Then second one is nucleotide analog reverse transcriptase inhibitor. And third one is non-nucleoside reverse transcriptase inhibitor. We have chosen this non-nucleoside reverse transcriptase inhibitor we have to use this type of an activity for the chrominochromine derivatives as an anti-HIV agents. Okay, then materials and methods which we have to use for this molecular docking is that the ligands were prepared by using the Lick prop. That is the Lick prop 2.5 and Schrodinger 2012. And the glide XP docking was used for the docking purpose. By taking this type of materials and methods, we have studied the binding interaction of these chromines with the different types of proteins. This is the reference that we have taken for the anti-HIV NNRTI. That is, rilviperin is one of the non-nucleotide reverse transcriptase inhibitors. And firstly, we have checked the active sites of this inhibitor for the binding sites of different types of proteins. And these are the active sites of HIV1 reverse transcriptase in complexes with, that is the rilviperin. That is, its trade name is EMC 278. It is the binding sites of the that is the rilviperin derivative or rilviperin, that is the drug, with the different types of proteins. Now, we have used the chrominochromine derivatives for the screening of or to study the binding interaction of these derivatives with the protein database. And this is the docking score of the synthesized chrominochromine derivatives. And it is observed that the derivative or the compound 4I, 4D and 4A, they are showing the more binding interactions with the protein, okay, comparative to the that is the reference drug rilviperin. This type of derivatives are used, or it is to be shown as an active as an anti-HIV non-nucleotide reverse transcriptase inhibitors. Okay, these are the binding sites or interactions of our most active novel chrominochromine derivatives. This is the two-dimensional view of binding interaction of the most active compounds that we have synthesized. That is, we have synthesized this type of compound and shown this type of interaction. And this is the three-dimensional view
Dr.
of the
Hanuman,
interaction of most
please
of
conclude.
Yes, sir.
Please
Yes, sir.
conclude.
Yes, sir. Yes, sir. Sir, 1 minute. Just 1 minute. Sir. Okay, this is then from this type of study, it shows that this study suggested that inhibitors possessing the pi-pi interaction with the aromatic side chain of its PHE 227 and trypsin 229 improve the inhibitor activity of reverse transcriptase. Okay, means this type of output which is to be extend the further, that is the research. And finally, we conclude that is, to the best of our knowledge, this is the first report that we have to use for the synthesis of chrominochromine derivatives. And these docking studies of these compounds, that is 4A, 4D and 4A, was around minus 10.40, minus 10.66 and minus 10.69. It shows that is, they shows this compound might have the potent reverse transcriptase inhibitor activities. And silico bonding studies suggested that the inhibitors possessing the pi-pi interaction with aromatic side chain of this PHE 227 and trypsin 229 improve the inhibitor activity for reverse transcriptase. Okay. Then lastly, I thanks to our principal, head of the department, as also the convener and co-convener and all organizing committee of Sikkim University, Manipal University, and to organize such type of an nice conference. And again, once I thanks to all. Thank you to all.
Okay, thank you, Dr. Hanmant. Any question from the house? Just one or two quick questions. Okay, if there are no questions, I'm thanking Dr. Hanmant for his nice presentation. Thank you.
Thank you. Thank you.
Okay, can you please unshare your screen?
Oh, okay.
The next presenter is OP28, Dr. Rahang Dale.
Yes, sir.
Yeah, please share your presentation and continue.
Yes, sir. So am I audible?
Yes, sir, you are audible. Continue, please.
Yes, sir. Yes, just a minute. Good day to all of you. Myself, Dr. Sanjeev Kumar Rangdal, Department of Chemistry, Jagat College, Goregaon. Today's topic is chelation ion exchange studies of pyragalol, pyruvate formaldehyde, organic copolymer resin, and its composite. Here, a copolymer is a large molecule composed of repeating structural units, typically connected by covalent chemical bond. Copolymer have played an important role for the beginning of life. Here, synthesis of PBF copolymer. The PBF copolymer was prepared by condensing pyragalol and pyruvate with formaldehyde in the presence of 2 molar HCl as a catalyst at 120 degrees Celsius in an oil bath for 5 hours. The cream-colored polymer obtained was washed with hot water and finally with ether to remove excess of acid monomer. The properly washed resin was dried, powdered, and then extracted with diethyl ether and then with petroleum ether to remove pyragalol pyruvate copolymer, which might be present along with the PBF copolymer. It is further purified by dissolving 10% NaOH and then filtered. The copolymer was then pre-precipitated by dropwise addition of 1:1, that is concentrated HCl and water with constant stirring and filtered. The method was repeated thrice. The resulting polymer sample was washed with boiling water and dried in a vacuum at room temperature. The purified copolymer was finely ground to pass through 300 mesh sieve and kept in vacuum over silica gel. The yield of the copolymer was found to be about 88%. Here, various techniques are used for characterization. The copolymer resin were subjected to elemental analysis for carbon, hydrogen, and nitrogen on elemental analyzers. Then electronic adsorption spectra of the copolymer in DMSO were recorded on Perkin-Elmer lambda 15 spectrophotometer, and infrared spectra of PBF copolymer were recorded on Perkin-Elmer spectrophotometer. In KBR pellets in the wave region of 4,000 to 400 centimeter inverse. Here, one proton NMR spectra were recorded on Brooker-Evans proton NMR spectrophotometer, and that is the DMSO D6 was used as solvent. Here, ion exchange property, the ion exchange properties of the PBF copolymer resin were determined by the batch equilibrium method. The ion exchange property of all the 4 resins have been studied. However, only one data of the PBF copolymer resin have been presented in this report. Here, the results of the batch equilibrium study carried out with the copolymer resin sample PBF are present in figure. From the study, with 5 metal ions under limited variations of experimental conditions, certain generalization may be made about the behavior of the copolymer sample. Effect of electrolytes on metal uptake. The copolymer that is 25 milligram was suspended in an electrolyte solution, and that is 25 ml of known concentration. The pH of the suspension was adjusted to the required value of the solution was stirred for a period of 24 hours at 25 degrees Celsius. To this suspension, 2 ml of 0.1 molar solution of the metal ion was added, and the pH was adjusted to the required value. The mixture was again stirred at 25 degrees Celsius for 24 hours and filtered. The copolymer was washed, and the filtrate and washing were obtained, were combined and estimated for the metal ion content by titration against standard ethylene diamine tetraacetic acid. A blank experiment was also carried out in the same manner without adding the polymer sample. The blank was again estimated for the metal ion content. The amount of metal ion taken up by the polymer in the presence of the given electrolyte of known concentrations. Results from the difference between the blank reading and the reading in the actual experiment. The experiment was repeated in the presence of several electrolytes. The effect of electrolyte and its ionic strength on metal uptake by copolymer was estimated at pH 5.5 for copper, nickel, cobalt, zinc, and at pH 3 for Fe3 positive. Using 4 different electrolytes with 5 different concentrations of each, we examined the influence of chlorate, nitrate, chloride, sulfate at various concentrations on the equilibrium of metal-resin interactions. Here, figure shows the amount of metal ion taken up by a given amount of copolymer depend on the nature of the concentration of the electrolyte present in the solution. In the presence of perchlorate, chloride, and nitrate ions, the uptake of Fe, copper, and nickel ions increases with increasing concentration of electrolytes, whereas in the presence of sulfate ion, the amount of the above mentioned ion taken up the copolymer decreases with increasing concentration of the electrolytes. Moreover, the uptake of cobalt and zinc ion increases with decreasing concentrations of the chloride, nitrate, perchlorate, and sulfate ions. This may be explained on the stability constant of the complexes with those metal ions. Here, rate of metal ion uptake. In order to estimate the time required to reach the state of equilibrium under the given experimental condition, a series of experiments of the type described above were carried out, in which the metal ion taken up by chelating resins was estimated from time to time at 25 degrees Celsius. It was assumed that under the given conditions, the state of equilibrium was established within 24 hours. Rate of metal uptake is expressed as percentage of the amount of metal ion taken up after a certain time related to that in the state of equilibrium. The rate of metal adsorption was determined to find out the shortest period of time for which equilibrium would be carried out while operating as close to equilibrium condition as possible. Here, figure shows the dependence of the rate of metal uptake on the nature of the metal. The rate refers to the change in the concentration of the metal ion in the aqueous solution which is in contact with the given polymer. The results show that the time taken for uptake of different metal ions at a given stage depend on the nature of the metal uptake under given condition. It was found that Fe, here Fe ions requires about 3 hours for the establishment of the equilibrium, whereas copper, nickel, cobalt, and zinc ions required about 5 hours. Thus, the rate of metal ion uptake follows the order Fe is greater than the copper, than the nickel, than the cobalt, and is equal to the zinc for PBF copolymer. Here, distribution ratio of metal at different pH. Here, the effect of pH on the amount of metal ion distributed between two phases can be explained by the results given in figure. The data on the distribution ratio as a function of pH indicate that the relative amount of metal ion taken up by the PBF copolymer increases with the increasing pH of the medium. The magnitude of the increase, however, is a different metal cations. The PBF copolymer resin take up Fe3 positive ions more selectively than any other metal ions, under this study. The order of distribution ratio metal ion measured in the pH range.
Dr. Rahangdale, please conclude.
Yes, sir. Yes, sir. Was 1 minute, sir. Thus, the result of such type of study are helpful in selecting the optimum pH for selective uptake of particular metal cations from mixture of different metal ions. For example, the result suggested that optimum pH 6 for separation of cobalt and nickel with distribution ratio D. That is the nickel respectively using the PBF copolymer. And here conclusion is that copolymer is PBF is selective chelating ion exchange polymer for certain metal ions. And the copolymer showed a higher yield selectivity for copper and Fe ions than the cobalt and nickel and zinc ions. Thanks to all of you. Also, thanks to organizer for giving me an opportunity for presentation. Thank you, sir.
Okay, thank you, Dr. Rahangdale, for your nice presentation. Now the house is open for 2 or 3 short questions. Anyone having any question, right? Please. Okay, if there are no questions, I'm thanking Dr. Rahangdale for his nice presentation. Thank you, sir.
Thank you, sir.
Okay, please unshare your screen.
Yes, sir.
The next presenter, OP29, Himanshu Gupta.
Yeah, good afternoon, all. I'm here.
Yeah, can you please share your screen?
Yeah. Is the screen visible, sir?
Yes, visible.
Okay.
Please continue.
So, a very good afternoon to all of you. The people present here, the chairperson of the observing the presentation. My topic for today presentation is kinetics and thermodynamic studies of the controlled oxidation of cinnamon alcohol by potassium persulfate as an oxidant in an acidic medium. Okay, with a gist of what I am going to do today. Okay, so the aim of the experiment is the kinetics of the oxidation of cinnamon alcohol by potassium persulfate in an acidic medium. This is the aim of the experiment. The things which I'll cover in the presentation is the introduction and the scope of kinetics, the materials that I have used for the experiment, the methods that was adopted, the reaction mechanism of the oxidation of cinnamon alcohol, and the various factors that affected and the various effect of these studies were made using alcohol, concentration, ionic strength, temperature. Certain inferences were made and references and the acknowledgement at the last. So introduction and the scope. The reaction kinetics is a study of a chemical reaction, as we all know, and the various factors that affects the rate of the reactions, such as the concentration of reactant, the ionic strength, the temperature, the solvent composition, and the catalyst. We consider kinetics as the most reliable tool to understand the reaction mechanism, and it also suggests the ways to optimize a chemical reaction. It's one of the most researched area of chemistry, especially in India. And also, according to the literature survey, it shows that there are several reports on the quantitative aspect of oxidation of alcohols to aldehyde or ketone, but there are very few reports that have been reported of the kinetics and the thermodynamic studies of the oxidation of alcohol. The inorganic oxidants are very rarely used for the oxidation of alcohol, and in India, the perfumery industry and the manufacturers uses the formulations, the methods, or alcohols in a larger scale. The material that was used for the prep or for the research was the cinnamon alcohol. Cinnamon alcohol is the naturally occurring unsaturated primary alcohol, which is extracted from the bark of the cinnamon tree. It's the most extensive, it has most extensive use in perfumery and deodorant formulation. The oxidant was potassium persulfate. in an acidic medium, and for the study of ionic strength, potassium sulfate was used. The method that was adopted. The kinetic studies was studied under the first order kinetic condition with respect to the oxidant, which is potassium persulfate, and the unreacted oxidant was estimated iodometrically using starch as an indicator at regular interval of time. The rate constant was determined from the linear first order plot of log of unreacted oxidant versus time, and the effect of ionic strength was studied on the oxidation rate to determine for using a potassium sulfate in a concentration range of 0.05 to 0.2 mole per dmK. The oxidation was studied under the temperature range of 308 to 318 Kelvin, and the various thermodynamic parameters were calculated using the Arrhenius plot. The thermodynamic parameters found out was the energy of activation, enthalpy change, free energy change, and the entropy change. The reaction mechanism: in an acidic medium, potassium persulfate rapidly forms peroxy disulfuric acid, which is a strong oxidizing agent and a strong acid. The oxidation of alcohol results into a formation of aldehyde and sulfuric acid. As we all know, it's a primary alcohol, so oxidation gives aldehyde. The aldehyde formation was tested using 2,4-DNP and was confirmed by the TLC. These were the observation tables that were made. Now, if you see the first part of the table, it is alcohol concentration, the second part is the oxidant, and the third part is the rate constant. In the few first observations, you will see that the concentration of alcohol is increasing. Keeping the concentration of oxidants constant, was found that the rate constant was increasing. When the concentration of alcohol was kept constant, increasing concentration of oxidant found that the rate of the reaction was decreasing. Effect of ionic strength on oxidation rate of cinnamon alcohol. This was studied using potassium sulfate, and when when the concentration was changing of potassium sulfate, it found that there was no effect on the rate constant of the cinnamon alcohol. The thermodynamic parameters that was calculated at various variations in temperature, keeping the temperature shifting, we found that the rate constant was increasing with the increasing temperature. Important inferences that were made. Rate constant of the oxidation increases with the temperature. The oxidation reaction was relatively slow. The equilibrium constant for the formation of the transient activated complex from the reactants increases with the temperature. Hence, the equilibrium constant is a function of temperature. Negative value of the entropy change indicated the reorientation of the solvent molecule around the activated complex formed during the oxidation reaction, due to which the vibrational rotational motions of the reaction system are curtailed. This results in decrease in entropy. The constant values of entropy of activation at all temperature indicates that the site of oxidation remains same at all temperature. The other inferences, as we already observed it from the observation, that was this: for cinnamon alcohol, the oxidation rate increases with the increasing concentration of the alcohol and decreases with the increasing concentration of the oxidant. The ionic strength has no effect on the oxidation rate due to involvement of non-ionic species, which is alcohol, in the reaction, and as suggested from the mechanism. The oxidation was accompanied by a decrease in the activation of entropy, that is the change in entropy. These are my few references. I would like to thank the principal and the management of the St. Xavier's College, my guide, Dr. Freddy Havaldar, Dr. D.V. Prabhu for constant guiding and motivation, and also the convener and the co-convener of the organizing committee who gave me the opportunity to present it in front of all of you. Thank you.
Okay, thank you, Mr. Himanshu, for finishing up in time. So the house is open for any question.
Good afternoon, sir. This is Shahid from Department of Chemistry.
Okay.
I want to ask a question to ma'am that she has explained that it was a nice presentation. Her work, that's kinetics, that obeys first order kinetics. So how did she come to the conclusion that the work, whatever she presented, just that follows the first order kinetics, not second order?
Okay, sir, can you just...
A good question. Thank you for the question. It was studied by various rate constant and substitution in the rate law equation and was found that the constant K value indicating that this is a first order kinetics.
Okay, thank you. Thank you.
Any other question?
Okay, any question from anyone? Okay, so thank you, Himanshu, for your nice presentation. So we'll move to the next presenter, right? OP30, Gujanan C. Upadhyay. Okay. Maybe he is not there. The next presenter, right? OP31, Dr. Monalisha Borua. Okay. She is also. We'll move to the first presenter, OP25, KD Badave.
Hello, am I audible?
Yes.
Yes, so I'll share my screen. Vengesh Same is here.
Okay,
Can I share my screen?
Yes, yeah, yes. Please share your screen.
Okay. Okay, so I hope my screen is visible.
Yeah, it is visible.
Okay, so I take my proceeding?
Yes, continue, sir.
Okay, thank you. Now at the outset, let me thank respected chairman, the committee, SMIT there, for giving me this opportunity to present my work. Now, first and foremost, I am from the Sardar Patel University, Vallabh Vidyanagar, and that is located in Gujarat.
Excuse me, sir, you are KD Badave, right?
Dave, D-A-V, Dave.
Okay, sir. Okay.
All right. Now I'll put my hypothesis and introduction together related with this work. My work I'm presenting here, that is related with this high energy materials. Now by definition, when we say high energy materials, so high energy materials are chemical species that suddenly decompose, releasing a large amount of heat and gases. And this sudden releases of heat and gases upon decomposition is used to provide the thrust to propel an object. So that is the main targeted application in which we are working, and my present work, part of the present work would be on that one. And my next presentation from my laboratory will be done by Ms. Rukshana Siraj. Again, she will do work on a different systems. She will be presenting our work subsequent to my presentation, and our third presentation from again my laboratory by Mr. Bhagwan Kamalia, but it is on the hydrogel. So this is what the contribution from our laboratory comes. Now the next very important part from my presentation is we are working on the system called 3-nitro-2-dihydro-1,2,4-triazole-5-1. And now onwards I will use word NTO. And the system called triazole-5-1, this is called TO. So I will use word NTO and TO during my presentation. So NTO stands for this chemical identity. That's what I have defined. Now, why we are having a much interest towards this NTO work, or why we selected NTO work for this presentation? The reason being, the NTO is one of such high energetic material used in a propellant and explosive application. So our application area is to develop a propellant and explosive application. Nowadays, studies are very carried out to replace very sensitive high energy materials like RDX and HEM by less sensitive materials like NTO. And this is what I'm discussing at this moment. So the HEM find application in rocket propellant, missiles, mining, pyrotechnics, like this way. Now NTO is less sensitive compared to other high energy energetic materials, along with high detonation velocity comparable to oxygen. Oxygen is a class of material called HMX. HMX everybody is knowing. And 135 tinitro, 135 triazine. This is known as the RDX. So as compared to HMX and RDX, this material is less sensitive, and sometimes these applications are needed where the high energy material all of a sudden releases the energy. But sometimes you have to release the energy in a controlled manner where the role of NTO comes into play. So this is our approach and approach to develop such with some of the controllable materials, and the modification in the decomposition of HEM, high energetic materials, can be done by downsizing HEM. Downsizing means converting into nanoscale high energetic materials. So that is achieved by us, the NTO and nano NTO being achieved by us. So NTO has very high activation energy. That is of the order of 322 to 368 kilojoule per mole. That could be attributed to higher stability of NTO. And the activation energy of NTO can be improved further by adding appropriate amount of additives. And these are the few references. Those who are interested related with this work, they can refer this to reference. Now, this is particularly for our work. The most widely used metal additives for HEM are a 3D transition series metals, because they are the transition series metal, and particularly the 3D transition metals are most studied because they can change their oxidation state during the decomposition process and can absorb intermediate products which release during the decomposition that accelerates the decomposition process. So that is the targeted application we are making here. The 3D transition metals and their derivatives are some of the most potential candidates for improving activation energy and thermal decomposition of NTO. So in this series, ferrites are metal oxides having general formula M. M stands for the metal in general, Fe2O4, and the ferrites are magnetic and they possess good catalytic activity for the enhancement of decomposition process of HEM. And further, the additives can be easily separated from mixture using a magnet. So separation process is at the same time easier. So various nano-sized ferrites are successfully utilized for improving thermal decomposition of HEM. The ferrites having a general formula like MFe2O4, where M may be a metal species, particularly +2 valence, like CO +2, Cu +2, Zn +2, etc. And of course, the transition metal having a various valences as well. So they are falling under the category of spinel ferrites. And once we are having a spinel ferrite, has two interstitial sites. One is a tetrahedral and another is an octahedral. In its crystal data structure, that may support a wide variety of cations. It has a capacity to incorporate various cations, which allows ferrites to have a wide range of characteristics. Other divalent metal can be substituted for the metal N, which resulting in a variety of spinel ferrites. In addition to the improving activation energy, the main task is to improve the activation energy. The ferrites are easily separated from HEM using the external magnet. So these are the relevant reference. This is the hypothesis. This is the background under which we have proceeded with our work. So now let me introduce you the experimental session, how we synthesize various compounds. This is our experimental protocol as a whole. The synthesis procedure for CCF, this is what we synthesize, is already reported by our group. You recall our paper of 2021, we have just recently published. And nitrate salts of like Fe+3, CO+2, Cu+2, these are all spinel, were dissolved in 100 ml distilled water in the appropriate ratio. The ratio in this case is a 0.5 is 5.2 mole ratios with continuous magnetic stirring. And to this, during the magnetic stirring, we added appropriate quantity of NaOH was added to obtain the black precipitate at the pH 12. The precipitates were filtered and dried in an oven at 60 degrees Celsius overnight, followed by the calcination at 500 degrees Celsius for 5 hours. This is the synthetic procedure. That's what already we have elaborated to you. And the NTO was synthesized in our laboratory using a two-step synthesis from HCl. One, the synthesis of TO from HCl, followed by nitration of TO to NTO. So TO converts into NTO. This paper is reported in 2021 by our group, and the detailed procedure one can find. I will provide you the reference, and in the abstract already we have reported this reference. The next job is to reduction or downsizing of NTO, and downsizing of NTO is obtained by solvent anti-solvent method, which was reported by Lee et al. In 2013 paper. But briefly, what the protocol we used here, we sonicated the solution of NTO in a tetrahydrofuran solvent, which was poured in a beaker containing exit as a solvent using a syringe while maintaining the temperature below 0 degrees Celsius. Because it's so volatile, so it is a very precondition that the 0 degree temperature is to be maintained, and the obtained white precipitate were filtered and dried overnight at 60 degrees Celsius to produce nano NTO. So these are the two methods. NTO we have synthesized by co-precipitation method, and here the solvent anti-solvent method we have used to synthesize nano NTO. So 95% by weight NTO powder was mixed with the 5% weight of the CCF. This is POCU ZN system called CCF system to give the NTO CCF, and similarly we prepared other metal halides following this route. So I think this is what the synthetic protocol we have synthesized by this method. Now let me come to what treatment we have given. So usually we follow the thermal treatment in order to have whatever thermal analysis we are having. We follow isoconversional method. And these are the listed equations, like these are all well-known plane wall was our method, Kissinger, Alsharu's and Sandro's method, and this is iterative FW. So this is the series of 5 different methods we use to calculate various thermal parameters. And here, these are the terminology we have followed for the understanding, like M0, M infinity, and MT are initial, final, and the mass left at the end of the process with respect to time. Beta is a heating rate. Heating rate is very important, and we reported the heating rate degrees Celsius per minute. And temperature we represented in terms of the Kelvin. And EA, that is very important, is the activation energy. And we reported our activation energy data in kilojoule per mole. R is a universal gas constant. A is a pre-exponential, Rn is pre-exponential factor, and we reported per minute, where the G alpha represents mathematical function for the reaction mechanism. And Hx is the KAS equation that gives for the iterative KS, and Hx is calculated by using equation number 5, so that will give you value of EA by RT. So that is how, by using a series of expression from 1 to 5, we evaluated the different factors. And now this is our experimental outcome. This is what I have presented in the form of the results. Now results are interesting in a various sense. So this is the different method we followed, FWO, KS, and the iterative KS method we have followed. And that's how we calculated EA as a function of alpha. And finally, this is our story, what the results or what the outcome we are getting. Now outcome is very interesting. Here you can see this is the, we reported E for all these methods. This is the pre-exponential factor ln A we have calculated, and K we have calculated for different methods. So these are the results in presence of NTO. This is NTO and our system POCU ZNF. This is the NTO derivatives, and this is the respective nano NTO compound. So in the presence of nano, the results are interesting to watch here. So the value of EA and log A we have calculated at the various extent of conversion. Like the degree of alpha is varying from let's say 0.1 to 0.9. So with respect to the various factors of alpha, and these are the we have depicted into this figure you can see presently here, the calculated average activation energy for NTO using FWO FWO, KS and ITKS, you can see here, this is reported as 382.4, 375.8, and 393.4 and 393.3 kilojoules respectively. This all energy we have presented in kilojoule per mole. And log A value we have reported here. This is varying from 40.4, 41.0, 31.8, and 35.0 respectively. Now, in the presence of CCF, this is our model system here. So the average EA, you can see vis-a-vis in presence of catalyst, we are in a position to reduce the energy by factor of 2 kilojoule per mole. So that shows the clear whatever the catalyst we have prepared. So in presence of the catalyst, a significant amount of reduction in the energy we have reported. And similarly, the value of log A further decrease of the order of 1.523. So we can say that the CCF, this is our present system, is indeed acting as a catalyst for the thermal decomposition of N2O. So they reduce, they decompose the N2O, and in the case of nano NTO, the results are still very good as compared to NTO. So the average value we can see in this system varies from 460 to 481. So this is the 481 that can be reduced, and corresponding the log A value is reduced from 44 to 50. So these are the various results suggest that the CO/CU ZNF system synthesized by us affects positively the kinetics parameter of NTO and nano NTO. Further to that, the addition of CCF to nano NTO greatly decrease the activation energy. You can see vis-a-vis that decrease in the activation energy in presence of the nano NTO. So 461 to roughly 265 nano. So nano function working almost twofold. So we can say that in addition to the log A value, so the value of EA and log A are less for the nano NTO to CCF in comparison. Now let me put the final conclusion of our study. So we can conclude that in this case, the presence of 5% by mass, the system CO/CU ZNF was found to shift the decomposition of both NTO and nano NTO to a higher temperature value. But however, the overall time required for the completion of decomposition of NTO and nano NTO reduced in the presence of CO/CU ZNF catalyst. The second best thing is the activation energy of both NTO and nano NTO were reduced to 83 to 88 kilojoule per mole and 205 to 216 kilojoule per mole respectively. The value of LNA was also found to decrease in the presence of CO/CU ZNF catalyst, which shows that faster decomposition of NTO and nano NTO in presence of CO/CU ZNF. The rate of decomposition of NTO and nano NTO in presence of CO/CU ZNF increased by 950 and 36 times respectively. So the higher rate of decomposition and lower value of pre-exponential factor suggests that the faster decomposition can be achieved by NTO, nano NTO in the presence of the synthesized catalyst. So this could be because CO/CU ZNF provides a decomposition pathway that requires lower activation energy. So in presence of catalyst, a lower energy pathway can be achieved by NTO and nano NTO. So this is the interesting conclusion we can have. So this is the moderation can be done as compared to HMS and RDS. So these are the achieved results. Through this series of papers, we have already published this paper in 2001. And finally, that is the time for me to say thank you. So this is the acknowledgement. This work is a part of the project funded by Department of Science and Technology. This is the number. My co-authors are thankful for the Department of Science and Department of Chemistry as well for giving us the general assistance. And the Department of Physics has provided us the Raman and XRD analysis. The second part of the work being presented by a subsequent speaker. So I think with this point, I must say thank you to the management for giving us this opportunity. And if you have any question, now this is the time to raise your question, query you have any. Over to you, sir.
Hello.
Yes, sir.
What information you get from the Raman?
What information I have not presented my Raman data, but Raman data is so sensitive to what's really happening across the interface. So some of the data will be presented, but the Raman analysis is a very important tool particularly for the catalytic application in general. So it suggests that some of the activity being done on the interface, and whatever the outcome I have presented in terms of the NPO or nano activities further supports that through this Raman tool. So vibrational character being presented by our synthesized catalyst. This is the generalized information we can put. Of course, during the short amount of time, I have not presented my Raman data. So kinetic part I have presented to show you our broad objective, but this is what we can achieve with Raman.
Okay. Next one. Roxana is present.
Yes, sir.
Okay.
Shall I present, sir?
Yes, share your screen.
Okay, sir.
Gunil sir, 1 minute.
Yes.
Okay. Okay, then thank you all the presenters from paper number 25 to 31.
Sorry,
Yeah.
Sir.
Now the next session, that is technical session 5. I am handing over to Professor Gunule and Dr. Mojam Ali to share this session. Only there is one point, the paper number 32, OP32, Dr. Pragnesh,
yes,
he has presented in the earlier session. Actually, this name was in confusion with the paper number 25. Same, the title is similar. That's why he has also come forward and presented. Just after one slide, we came to know that this is paper number 32, not 25. That's why it is considered in this session only. And
sir, there is still some confusion.
Yes,
so,
sir.
Just now, paper number 32 was presented or 25?
32.
Okay,
now, your session will continue from paper number 33 onwards.
Yeah.
And if any one, that means from 30 and 31, they were absent during that time, but if they join, they should also be allowed. Paper number 30 and 31. I request both of you to consider paper 30 and 31. Just give one announcement. If they are present, please continue. I'm now handing over you.
Thank you, sir. Thank you, sir. Welcome, Professor Masudev, and we'll be chairing the session. In this session, we have 6 oral presentations. One is already done. So, sir, should we start now?
Yes, sir. We can start.
Okay, so we'll be calling oral presentation number 33.
Yes.
Roxana Siraj, are you present?
Yes, sir.
Okay, so you may go ahead with your presentation.
Okay, sir. So I'm sharing my presentation.
Yes, okay.
એટલે મારું લેપટોપ હેંગ થઈ ગયું છે. હું ચેક કરું છું. Hello, sir. Hello. Can I delay my presentation as I'm not able to share my slide currently?
Okay.
Can I give after some time?
Okay, no problem.
Okay.
So we request Oral presentation number 34.
Yes, sir.
એટલે લેપટોપ હેંગ થઈ ગયો છે
Yes, sir. I am present, sir.
Okay, so you can upload and start now.
Okay, sir. I will share.
Okay.
Sir, my screen is visible, sir.
Yes.
Good afternoon to all, sir.
Go from full screen.
Okay, sir.
It's okay now. Yes, yes. Okay, start.
Yes, sir. Yes, sir. Myself, Amol Manke, Assistant Professor in Department of Chemistry, Pratap College, Amalne. I am going to present my research work, which having the title Energy Saving Approach for Ultrasonic Synthesis of 4H Chromium. And my research work is guided by the S.R. Patel sir, which is also Assistant Professor at Chopra. We all of know about the heterocyclic compounds, it having the wide applications and wide range of modern publications. Near about 1/3 modern publications are belonging from the heterocyclic chemistry. We also know the heterocycles are present in wide variety of drugs, vitamins, natural products, biomolecules, and biological active compounds. So I select the topic from the heterocyclic chromonucleus. And this is the short introduction about the chromonucleus. They are biologically active compounds. They gave the antibacterial, antioxidant, antimicrobial, and antifungal activities. I follow the MCR methodologies, multi-component reactions. The applications and advantages of MCRs are it reduces the number of steps, it saves the time and energy, one pot synthesis, and it has the low expenditures. I follow this scheme in this paper. I synthesize the 2-amino-4-aryl 7-hydroxy 4H chromium 3-carbonitrile by using the 3 different routes. I put first conventional method. At that conventional method, I synthesize compound using at the reflux temperature by refluxing. By second route, our second route is the ultrasonication method at the 40 kilohertz frequency, and third route is the ultrasonication method but at the 25 kilohertz frequency. Both reactions are going at the 40 degree centigrade and is optimized temperature. Then we optimize the catalyst for the corresponding product, and we found that 0.2 gram of catalyst, sodium carbonate catalyst, is sufficient to conduct the reaction. While optimization, we did the reactions on the by the 3 routes. At 40 kilohertz, it shows that reaction is completed within the 15 to 20 minutes only. When we use the 25 kilohertz frequency, then we found that 10 to 12 minutes are required for the completion of the reaction. And by CV, means conventional method, we require the 180 minutes, means 3 hours. This is the advantage of this work, because ultrasonication gives the product within the 15 to 20 minutes. Then we did 7 reactions with the same product and by different routes: 40 kilohertz frequency, 25 kilohertz frequency, and conventional reflux conditions. These are the values of time and shows the yield of the product. Then we move towards the spectral data, and all the spectral data are well matches with the literature. We also we take the UV, IR, H1NMR, and C30 spectra. IR value of the OH which is present in our compound shows at 3423. Again, NH2 functional group is on our compound. It shows the value 3328. And cyanide group is also present in our compound. It shows the value 2189 per centimeter. H1NMR values are also confirmed because H4 proton is present there, which shows the value 4.62. I mentioned in the result and discussion. I will discuss there. But this is the spectral data. microbial activity we taken for that compound, and it shows the good zone of innovation in diameter. We also take the H2O2 scavenging activity, radical scavenging activity, and it also shows the moderate activity to the H2O2. Then we move towards our main aim, XRD. After taking the XRD, we found that all peaks appear at the same region, but only differs that when we prepare the compound using the ultrasonication, then it found that it gives the sharp peaks because while we conduct the reactions on 25 and 40 kilowatts by using ultrasonication, then it found that sharper peaks, means it is more, it peaks generated from the more crystalline peaks, more crystalline compound. That's why we found that from all the data it was shown that ultrasonically synthesized chromium have the more crystallinity than the conventionally synthesized chromiums. Then we move towards the TJ. After taking TJ also shows that ultrasonically synthesized compound was superior in quality than the conventionally synthesized compound. Here the heat flow versus heat flow endodown versus temperature graph shows the sharp decrease in case of ultrasonication, and there is a slow and constant decrease till the completion of the decomposition in case of the conventionally synthesized. Red is from the US1. Red line shows the US1. So, red line from US1 25 kilowatts. Blue line is from the US2 40 kilowatts, and black line is from the C1 conventionally. This sharp decrease, but in case of ultrasonically, there is a slow decomposition. Then we found that all this data indicates that ultrasonically synthesized product have high crystallinity over the conventionally synthesized product. Then we calculate the crystallinity and crystallite size by using the FWHM data, full width half maximum data, which we got from the XRD. And it found that crystallinity of the conventionally synthesized compound is 37.94, and ultrasonically synthesized compound having the greater crystallinity over the conventional method. Ultrasonication method using the 25 kilohertz frequency, 64% is the crystallinity of that product. While we do the reaction at 40 kilohertz, then it found that 63% crystallinity the compound having the product. And crystallite size is also lesser in case of the ultrasonically synthesized compound over the conventionally synthesized compound. Then we move towards the energy calculation. How much energy we can save from the by using the ultrasonication over the conventional method. And we found that after calculating, we got the first we calculate energy delivered during sonication method at 40 kilohertz, and it was found that 169.84 kilojoule per gram. Then we calculate the energy delivered during sonication at 25 kilohertz, and it found that 117.218 kilojoule per gram. Then we again calculate energy delivered during conventional method, and it was found that 2909.48 kilojoule per gram energy is utilized for conversion of the product. Then we calculate the percentage of energy saved at 40 kilohertz, and we found that 94% of energy can be saved when we use the ultrasonication at 40 kilohertz. Then we calculate the percentage of energy saved at 25 kilohertz, and we found that 95.97% of energy can be saved when we use the ultrasonication at the 25 kilohertz. We again did the comparison between the 40 kilohertz and 25 kilohertz frequency, and it was found that percentage of energy saved between 25 and 40 kilohertz is the 30.98% of energy can be saved when we use the 25 kilohertz frequency rather than the 40 kilohertz frequency. Result and discussion. The research begins with the optimization of reaction condition at different frequencies. 40 and 25 kilohertz frequency using the bath sonicator at different temperatures. But we use the 40° centigrade temperature because it got at that temperature reactions conducts smoothly, and it seems that ultrasonication was the superior method over conventional in order to time and energy saving. Here we use the simple, efficient and easily available, cheap and milder base sodium carbonate as a catalyst. Under the ultrasonication, different catalytic amount were used, but best result obtained at the 10 mole% of the catalyst. The time required for formation of 40 kilowatts is 5 to 20, and at 25 kilowatts frequency, the formation of product is completed within the 4 to 15 minutes. IR data, OH and NH2 frequency we got, and sino function is appear at the 2188 per centimeter. H1 data confirms 6.88 delta value confirms the functional group NH2, and 9.70 and 9.72 ppm attributed from the OH functional group. This data was confirmed when we show the NMR shows the H4 proton delta at the 4.62 ppm. The C13 NMR also confirms from the one singlet which appear at the 56.77 ppm for the C4 carbon atom. 102 ppm is from the C3 carbon atom, and sino functional group is appear at the 112 ppm. All the known compounds were identical in all physical and spectroscopic aspect with the literature. The last one slide is a conclusion. We found a green efficient and energy saving pathway to synthesize chromiums by using the ultrasound bath sonicator at different frequencies, 40 and 25 kilohertz. Here we utilize Na2CO3 cheap, readily available, milder catalyst. Several advantages over conventional methodology in terms of the operational simplicity, simple workup procedure, higher yield, shorter reaction time, and use of non-hazardous catalyst and solvent. We can save tremendous amount of energy when we carry out the reaction using ultrasound sonicator instead of conventional method. 94 to 96% of energy can be saved by using the ultrasound sonicator. The energy required to complete the reaction at 25 kilohertz is less than the required at 40 kilohertz. We can save up to 30% of energy when we carry out the reaction at the 25 kilohertz frequency rather than the 40 kilohertz. This is the short presentation of my research work. Thank you, Professor Gornole sir.
Hello. One question.
Thank you, sir. Yes, sir.
Can we use this cone nucleus for the application for antimicrobial, antifungal? And why?
Yes, sir. Yes, sir. We take antimicrobial activity. Actually, it is antibacterial because all microbes are bacteria. So, antibacterial activity has been taken by using the gram-positive and gram-negative bacteria. 2 gram-positive and 2 gram-negative bacteria are taken. Gram-positive and gram-negative bacteria, both bacteria are shows the zone of inhibition on the Petri dish plate.
Do you have performed the experiment?
Yes, sir.
Do you have performed these antimicrobial experiments?
No, sir. It is higher. We hire the services from the microbiology department.
Okay. And what you are getting information from the TGA?
From the TGA, I found that it having the greater crystallinity. The crystalline nature of the product is more while we do the reaction while we carry out the reaction using the ultrasonication. Because in the ultrasonication, there is a lot of energy has been generated within the reactants.
What about the thermal stability?
Thermogravimetric analysis.
Thermal stability.
There is a sharp.
Stable?
Yes, sir. The TGA graph shows that ultrasonically synthesized compound having the not sharp decrease. At that point, I mentioned when the conventionally product is sharp decrease slowly and sharp decomposition rate. but ultrasonically synthesized product having the not slowly, it is rapid decomposition of the product.
Hello, sir. Ali, sir, you can ask.
Okay, so the house is open for questions. If anyone has any questions, you may ask. Okay, so in absence of any questions, we will move to the next speaker. Okay, thank you.
Thank you, sir. Thank you, sir. Ali, sir. Gurnal, sir, thank you for giving me chance to present
Okay, so
in front of the great personalities. Thank you, sir.
We'll move to the next speaker. And the next oral presentation is OP 35, and it will be given by
Excuse me, sir.
Bhagwan Kamalia.
Hello.
Yes.
Yes, sir. Oral presentation 33. Ruxana Siraj is ready for the presentation.
And what about 35? Are you there? Bhagwan? Okay, then 33, you can go ahead.
Okay, sir. So I'm sharing my presentation.
Yeah.
So, are my slides visible?
Yes, this time it is visible.
Okay, sir. So today's my topic is synthesis and characterization of cobalt ferrite and its effect on the thermolysis of both micron size as well as nano size NTO. As my guide have already discussed about what are the experimental procedures. So in the previous work, we are focusing on how we can improve the thermal stability of NTO. As NTO is major constituent of propellant samples, and hence slight changes in its thermal stability can change drastically the burning rate effect of NTO containing propellant samples. So we are basically, our research group is focused on synthesis of ferrite based nanomaterials and their application for improving the thermolysis of both NTO as well as nano NTO. So first one is introduction. So NTO is basically a high energetic material. So what are high energetic materials? High energetic materials are chemical structures that contain large amount of energy. And when they undergo detonation or thermal decomposition, they release a large quantity of gases that can provide threshold for the propellant, as propellant are used for propellant object. So now, as high energetic material constitute 60 to 80% of propellant system, it means the slight changes can improve the burning performance of propellant system. So improvement in the decomposition temperature of burning characteristics. So how improvement can be done? So improvement can be done by nanosizing the existing high energetic materials such as NTO. Second one is formation of co-crystal with other high energetic materials, and third one is addition of additives such as nanomaterials. So what are nanomaterials? They have one dimension in the nanoscale that is basically lesser than the 100 nanometer size. So in the current work, we have synthesized metal ferrites. So M represent CO2 plus and Cu2 plus both in 0.5 and 0.5 molar ratio compared to Fe2, which is in 2 mole ratio. Now in the experimental session, we have synthesized TO basically means triacylon. So we have done we have condensed semi-carbazide hydrochloride with formic acid to form TO, which upon nitration provides NTO. Now nanosizing of NTO, as earlier discussed by guide, was done using solvent and non-solvent technique, in which saturated solution of NTO was prepared in tetrahydrofuran solvent, which was poured into non-solvent such as normal hexane to get the precipitates of nanosize NTO, which is represented in NTO. Synthesis of ferrite was basically done by dissolving metal nitrate salt. What metal nitrate salts were cobalt nitrate, copper nitrate, and iron nitrate. These were dissolved in appropriate quantity in water, followed by addition of 2 molar NaOH solution as an precipitating agent, which produces precipitates of metal hydroxide, which upon calcination provides metal ferrite system. Now further we have to compare the catalytic activity of synthesized cobalt copper ferrite on NTO and NNTO, we have mixed 5% by mass cobalt copper ferrite with NTO and NNTO respectively to produce NTO plus CuCO Fe2O4 salt and plus NNTO plus CuCO Fe2O4 salt. Now, these are the results. These are basically UV to confirm the structure of the NTO. As you can see, it's nano size NTO, which is represented by this violet type purple light, which absorb in lower wavelength region as compared to normal micron size NTO. This shift was reported that upon nano sizing, the material's UV band is usually decreased. Now, second one is similar effect were observed in the Raman spectrum. In Raman spectrum, what was happened that nano size NTO was observing at larger Raman shift values. So this could be attributed to nano sizing of NTO. Now, here are the XRD spectrum. XRD spectrum were used for the calculation of crystalline size of both NTO as well as cobalt copper ferrite, which were found to be 18 nanometer in case of cobalt copper ferrite and 38 nanometer in case of nano NTO, which confirms the size of both. Now, the thermal stability effect of both cobalt copper ferrite on NTO as well as on nano size NTO are represented in the figure. So as you can see, NTO decomposes at 259.45 degrees Celsius. When the catalyst was 5% catalyst was added, the decomposition of the NTO was increasing. Temperature was increasing. This means that it stabilizes NTO as in the absence of metal catalyst, the NTO was decomposed at lower temperature, but when a catalyst was added, its decomposition occurred at larger temperature values. Now, this means it usually stabilizes NTO composition. Now, similar results were obtained in case of NNTO. So, in case of NNTO, its decomposition temperature, which 256.32 degrees Celsius, was shifted to high temperature value in the presence of nanocatalyst, which is 264 degrees Celsius. Now, further from the TGDSC data, we have used a 3 isoconventional method to calculate the activation energy of the thermal decomposition process. So this is a graph of value of activation energy and log A value calculated using various FW, ITFW, KS and ITKS method. Now here are the corresponding results of effect of catalyst in the presence of cobalt copper ferrite. Now, as you can see, NTO activation energy is quite low as compared to nano NTO. It means that upon nano sizing, the activation energy of NTO was drastically increased. But when cobalt copper ferrite was added, the catalytic activity shows that its activation energy in the presence of catalyst was greatly reduced in case of NNTO. But as you can see, at micron size NTO, cobalt copper ferrite do not exhibit that much of decrement in activation energy as it was showing in case of NNTO plus CCF composition. Similarly, we have found the result of log A and activation energy. And here are the, as we earlier discussed on what was the effect of cobalt copper ferrite on the DSC peak temperature. This is basically exothermic decomposition peak temperature of both NTO and NNTO. Here are the conclusions of my research work. The nano size NTO as earlier discussed, the nano size NTO decomposes at lower temperature but increases the overall activation energy and pre-exponential factor of decomposition of NTO. The addition of cobalt copper ferrite decreases both thermal decomposition peak temperature as well as activation energy of NTO. Here in the graph, you cannot see that much decrement because the values are nearly close. As decrement was not that much large, it was around 2 kilojoule per mole, and that's why you cannot see it in the graph. Thermal decomposition parameter such as activation energy and pre-exponential factor of NTO's decomposition process can be improved by nanosizing NTO followed by addition of CCF additive. As you can see, that this particular composition exhibited great effect as compared to micron size plus catalyst additive. So here are my acknowledgements. Thank you.
Okay. Hello. How you by which method you have synthesized the ferrite?
Sir, using the wet chemical method, which is co-precipitation method, employing NaOH as a precipitating agent.
And how you know it is in a nano size?
Using a solvent and non-solvent technique, which was basically we have prepared saturated solution of NTO in tetrahydrofuran solvent and followed by addition of it in normal hexane solvent, which is basically act as a non-solvent or anti-solvent. And therefore, by adding a tetrahydrofuran solution of NTO in normal hexane, we get precipitates of nano NTO.
What is the size of the particle?
So in case of NNTO, we have achieved, as per Exardis-Serres equation, we have achieved 38 nanometer size of NTO.
And at what temperature calcination you have carried out?
Sorry, sir.
Calcination you have carried out, na? What is the
Yes,
temperature
sir.
for
At 500 degrees Celsius for 5 hours.
Okay, sir.
Okay, thank you for the presentation. And okay, so if anyone has any questions related with the presentation, you may ask.
Stop करो.
Okay, so there are no questions related to the presentation. Okay, thank you for the presentation. Now we'll be moving to the next presenter. And okay, so oral presentation number 35. Are you there? Bhagwan? Okay, 36. Oral presentation number 37.
Sunil, backward.
Hello.
Yes, yes.
Sir, 35 oral presentation. I'm here. Hello.
Okay, so Bhagwan Kamalia, so
Yes.
your presentation is OP 35, right?
Yes, sir.
Okay, so you may start with the presentation. So you have 10 minutes.
Okay, sir. I'm
Okay,
saying.
all the best.
Thank you. Hello.
Yes. No, it's not visible. Have you uploaded the slide?
Okay, sir. Okay.
Okay.
Hello, Bhagwan, share your screen.
I'm visible, sir.
Yes.
Yes. You go to the full screen.
Hello. I'm visible, sir.
Okay, yeah, go ahead.
Yes. Okay, sir. Sir, myself, Bhagwan P. Kamalia, and my research topic, the presentation, synthesis and characterization of gum gatti cross-linking poly and isopropyl acrylamide co-acrylic acid with cobalt ferrite nanoparticle hydrogel for metformin hydrochloride drug removal from aqueous solution. My guide is Professor Dr. P.N. Dave, sir, and research scholar, Department of Chemistry, Sardar Patel University. Synthesis outline, synthesis and characterization, this result and discussion. I have preparation of a cobalt ferrite nanoparticle The ferrite nanoparticles were prepared by the chemical co-precipitate method and reported in the aqueous solution of 0.2 molar nitrate, cobalt nitrate and 0.4 molar ferrite nitrate solution and dissolved in 100 ml of distilled water. This solution was mixed and followed by the drop-wise addition of 0.2 molar NaOH solution and rigorous stirring gave the complete precipitate of metal hydroxide. The pH resin 11 to 12. The residue of metal hydroxide was washed with distilled water and several times made them free of nitrate ion and kept at 60 degrees Celsius in hot air oven in 24 hours and died then. They were calcinated at 300 degrees Celsius about 5 hours. And other preparation nanocomposite hydrogel. First of all, the precipitate of nanocomposite hydrogel was carried out by free radical copolymerization solution. The biopolymer monomer 0.5 gram of gum gatti dissolved in double distilled water 8 ml overnight and describe the amount of cobalt ferrite nanoparticle and disperse in distilled water 2 ml with 40 minutes sonic acid. After that, then these two solutions were mixed in 100 ml beaker, stir and magnetic stir and 250 rpm. Then the 40 milligram APA started to polymerization process. Then reaction mix temperature was maintained at 60 degrees Celsius and further addition of 40 milligram of methylene bicyclenamide MBA was added in as cross linker, continuous stirring and last step and other mixture of monomer and isopropyl acrylamide 2 gram and other acrylic acid 1 ml and slowly to constant stirring. The reaction was allowed to 3 hours in hot air oven without disturbance. After 3 hours, the response of product was cool at room temperature. This reported in table, a poly and isopropyl acrylamide and polyacrylic acid was removed the ocular extraction acetone for 3 to 4 hours. Further, the remaining trace homopolymer separate and dip in cobalt nanoparticle. The 24 hours. Finally, the synthesized cobalt addition of nanoparticle and without addition of nanoparticle, this nanocomposite hydrogel is 50 degrees Celsius and hot air over and further the dye pulverized on powder form. Schematic diagram of hydrogel preparation. First of all, gum gatti plus H2O and overnight, and then after reaction of anisopropyl acrylic acid, APS and MBA, and temperature was maintained at 60 degrees Celsius, and cobalt ferrite nanoparticle is addition and 3 hours. Then after the dyeing, the hydrogel addition of hydrogel nanoparticle and without nanoparticle GNSCH0 and GNCH3. FTI data. First of all, pure gum gatti data is figure 1 and the nanocomposite hydrogel with without addition of nanoparticle and further the nanoparticle preparation of nanoparticle and addition of nanocomposite hydrogel. And the XRD data, the first of all nanoparticle CF cobalt ferrite and addition pure gum gatti and nanocomposite hydrogel and without nanocomposite hydrogel. The first of all, gum gatti is the peak amorphous material, 18.57 2 theta value. And the addition of nanoparticle, the slight change of 80.57 to 19.81. And without addition of nanocomposite hydrogel, 20.19. And a TGA data, first of all, cobalt ferrite nanoparticle, the TGA data, then gum gatti is 3-step decomposition and nanocomposite hydrogel 3 component. First of all, 100 to 20 degrees Celsius, the water molecule removed and other carbohydrate bond is break and stable of nanoparticle composite addition, the thermal stability increase without addition of nanocomposite hydrogel. And AFM data, cobalt ferrite 59 nanometer pore size and gum gatti 73 nanometer and without addition of nanocomposite hydrogel 55 nanometer, addition of nanocomposite hydrogel 99 nanometer. same data. Swelling property. The gum gatti nanocomposite hydrolase without addition of 0, the swelling property is 66, and addition of nanoparticle 10 milligram, so swelling property is the increase. Further 20 milligram increase and 30 milligram increase, but 30 to 40 milligram will be a decrease in swelling property. 40 milligram, 50 milligram to 60 milligram. And other metformin removal of adsorption amount of condition influence. The adsorption of metformin nanocomposite hydrogel in base system. The operation condition were investigated. Concentration 25 to 250 milligram per liter. Adsorption dose 5 to 100 milligram, and temperature 25 to 55 degrees Celsius. Contact time of 24 hours, and the solution of pH 2 to 12, which is adjusted by the solution of NaOH and HCl. First of all, effect of adsorption dose 100 milligram per liter metformin solution, pH 6 and volume 50 ml. Adsorption dose 5 to 100. And second, variation of adsorption dose. The adsorption dose is constant, but variation of metformin solution. And third, effect of initial adsorption dose, metformin solution will be constant, and pH is variation. Effect of temperature. Metformin solution adsorption dose will be constant, pH constant, and temperature is variation. First of all, adsorption of removal, adsorption dose variation 5 to 100 milligram. So one by one, adsorption property. The 40 milligram of adsorption, a high removal efficiency, and then initial concentration variation. 25 to 250 milligram per liter. 100 ppm removal efficiency 68.9%, and then pH variation 2 to 12, but approx 8 pH the removal efficiency will be high, and then temperature 20 to 55, removal efficiency metformin 62.50 degrees Celsius. A synthesis of free radical conclusion. Gum gatti, and this particle is FTR, XRD, same PGA, and swelling property. Measure and prove the synthesis of hydrogel. And this material used the absorption of metformin hydrochloride drug, removal of aqueous solution using UV spectrophotometer, and the nanocomposite hydrogel using the wastewater treatment. Thank you. Hello.
Hello.
Ah, sir.
You have performed number of experiments, and the material useful for the wastewater treatment of water. Okay, now. And so, what is the? You also said shown about the same. What is the importance of same in your work?
Yes, sir.
Yes. What is the importance of this in your work? Hello.
Hello.
What is the importance of same in your research work? Hello.
Sir. Same is more
Definitions of the same.
morphology of nanocomposite hydrogel.
Okay. Is it useful in the work?
Yes, sir. Yes, sir.
How you can? What is the importance of this same? You have. Nanocomposite hydrogel you have made, and also you have taken these same images of different magnifications. So what is the importance related to your applications or your research work? Do you know?
No, sir. No idea.
Okay. So go through the papers, okay? It gives the morphology, but how it is useful to your material now. So go through that,
Yes, sir.
you should have
Yes.
to mention why you are taking
Okay.
this same and like that. Okay. It is
Okay.
it depends. It gives the particle size, and also you are performing the experiment. Adsorption, desorption, both are there, na?
Yes. Yes.
So it depends on the particle size. Okay.
Okay. Thank you, sir.
Go through different papers. So many papers are there. Okay.
Yes. Yes. Yes.
Okay,
Thank
sir.
you. Thank you for the presentation.
Okay. Thank you, sir.
Okay, so if anyone has any questions related to the presentation, you may ask. Okay, so we don't have any questions for the time being. Okay, so we will move to the next presenter for this session, and we will move to presentation number 36, OP number 36, oral presentation 36. Are you there?
36. A Gaikwad.
A. Gaikwad.
Sunil Gaikwad is present, sir. SV Gaikwad.
Yes, then Sunil, you get ready so you can go with the presentation. Yours
Okay,
is OP number 37, right?
37. Yes, sir.
Okay, then all the best.
Yeah, thank you, sir.
Okay, go ahead.
My screen are visible?
Yes, yes.
Yes, sir. Okay.
Yes, sir. Yes, sir. But yes, sir. Yes, sir. It's visible.
It's visible?
Mm-hmm.
Now it is okay, no, sir?
Yes, sir. It's visible. Okay.
Okay, sir. Good afternoon, one and all. I'm Dr. Sunil V. Gaikwad. I'm going to present my research work, which is carried out during my PhD. Right now, I'm working as an assistant professor in Dr. D.Y. Patil, Women's College, Pimpri, Pune. My research topic is iodine DMS to catalyze chemoselective oxidative aromatization, dealylation, and non-dealylation of the aryl-allyl ether of the tetrahydro beta carbonyl. As we know that the tetrahydro beta carbonyl, they have the different sources in our day-to-day life. We use the mushroom in our day-to-day life. We use the tomatoes, and we know the passiflora. That is in India, it is called as Krishna Kamla. These are the some sources of the beta carbonyl, that is tetrahydro beta carbonyl, as well as the aromatic beta carbonyl. And we know that they have the broad range of the biological activity of the tetrahydro beta carbonyl, as well as beta carbonyl with the substituted beta carbonyl, or the O-allyl beta carbonyl, or the triazole, tetrazoles, and many more. And we have the amide linkage also. These are the some important biological active beta carbonyl. They are having the anti-cancer, antibacterial, and mostly anti-malarial properties. Our origin of the problem is research problem is, as per the literature survey, the functional group transformation is a very much important in the game in the organic chemistry. And allele group is one of the protecting and deprotecting group for they can usually use it for the phenols, alcohol, acids, and the amines. Okay, as per the literature, in the some reported method, they use the iodine in DMS or H plus for the dealylation of the phenol, or dealylation of the this acid group, and dealylation followed by the dehydrogenation of the dihydroxylone derivative. Our the objective was main objective was this in this method is to develop such a method. Here in this method, the aromatization will happens simultaneously. There is a no dealylation of the tetrahydro beta carbonyl, followed by there is aromatization with the dealylation of this O allele protected tetrahydro beta carbonyl. According to that, we move towards to develop our methodology and initially we prepared our starting material from the simple benzaldehyde. That benzaldehyde having a OH group at various position, that is protected by using the our allele group reflects that in the presence of the K2CO3 in the acetone, we will get O allele protected aldehyde, and that O allele protected aldehyde is treated with our appropriate tryptophan, or the tryptophan methyl ester it is reflux in the ammonium chloride. It is one of the milder acid in the methanol solvent. As we know that the methanol solvent is act as a greener solvent also, and we will get a substitute. We will get a various type of the tetrahydro beta carboline with 80 to 95% of yield, and that tetrahydro beta carb O allele substituted tetrahydro beta carboline we have used for the new methodology. This is the optimization table for the aromatization with a dealylation and aromatization with a non-dealylation. Initially, what we have done is we have used a 10 mole % of the iodine, and we have treated this O-allyl substituted tetrahydro beta carboline without oxidant at room temperature. There is no formation of the 6A, that is O-allyl substituted beta carboline with aromatization and when we increase the molar percentage of the molecular iodine 20, 25 and 30, 35 with the increasing in the temperature to 60, 80 and 90 degrees Celsius with the varying time, then we found that there is a aromatization with no dealylation of that O protected tetrahydro beta carboline. And when we increase the molar percentage of the iodine, that is 75 to 100 moles percent, in the presence of the external oxidant, that is H2O2 at 90 degrees Celsius, within the 4 hours, we will find that there is a formation of the, that is there is aromatization of the tetrahydro beta carboline, but there is no dealylation. Okay, and then we change the oxidant, that we added the HCl in the reaction mixture when we use a 25 to 50 mole percent of the iodine, and addition of the 2 to 3 drop of HCl at 90 or the 100 degrees Celsius, we will get aromatization with a dealylation. Okay, in this methodology, we the novelty is that there is aromatization with a no dealylation by using the iodine with the external oxidant. With the help of that developed methodology, we have synthesized a series of the aromatic beta carboline with O allele substituted, and that is when we treated this tetrahydro beta carboline with the iodine DMSO, we will get that series of that we synthesize a series of the O allele substituted aromatic beta carboline and O allele non O allele, that is a free hydroxy group aromatic beta carboline. And these are the some examples we have synthesized having the different substrate at 3 and 4 position, and we have applied this our development methodology for the synthesis of the O allele substituted, that is a flavanone also, and the same methodology we have applied at a low, when we applied at a low temperature, when we treated this tetrahydro beta carboline with a acid group, that is at C3 position, if there is acid group, and then at a lower temperature there is no decarboxylation, but there is aromatization with a no dealylation occur when we treated this iodine DMSO in a H2O2. Opposite to that, that is when we use the iodine DMSO in H+, there is a dealylation with the no decarboxylation. That papers we have already published in the Chemistry Select in the 2019, and this is a proposed mechanism for the aromatization with a dealylation, where as we know that the DMSO, there is a formation of the I2 with the molecular iodine, with regeneration of the iodine with when we treated the DMSO in the H+. The proposed mechanism, there is the iodine, it forms the iodine intermediate, that is a 3-member ring. That 3-member ring, this 3-member ring will be stabilized by this DMSO, that is a solvated complex, and this solvated complex may be, that is helpful for the dealylation of the tetrahydro beta carboline and for aromatization, and we will get this aromatic product with the dealylation, because this is a common mechanism, and we will get in the various literature. And what we have, our new report is for the aromatization with a no dealylation. What will happen here? Here the oxide, there is a formation of the free radicals. As we know that when the peroxide, when we add it in the I2, then there is a formation of the peroxide radical, and there is a single electron transfer mechanism. what will happen here at the N2 position, there is a formation of the free radicals, and this free radical, it form the carbocations, and that carbocation single electron transfer mechanism, it form the N-iodo tetrahydro beta carbolene, and this we know that that N-iodo tetrahydro beta carbolene subsequently undergo the dehydrohalogenation, and it will get the dihydro beta carbolene, and that dihydro beta carbolene again is undergo the free radical mechanism, and there is a formation of the free radicals at C4 position, and this C4 position again the single electron transfer mechanism second, and there is a formation of the that is a coal-based product, that is iodine at the C4 position, and then we know that when the iodine at the alpha beta to the carboxylic acid, it undergo the, when we heat it at above the 60 degrees Celsius, it undergo the dehydrogenation and followed by the decarboxylation. This is our the proposed mechanism for the aromatization followed by the decarboxylation and no dealylation. And in this method, we have developed a novel method for the selective oxidative aromatization with a no dealylation of the O-allyl tetrahydro beta carbolene by using the iodine in the DMSO H2O2. The preference of this method is tolerate the O-allyl group of the tetrahydro beta carbolene. The operational simplicity and economically variable of this method justify the further study of this reaction. Besides this, we have developed a simple protocol subsequence procedure for the selective O-allyl dealylation and the aromatization of the substituted O-allyl tetrahydro beta carbolene using the iodine in a DMSO H+. This is also the one of the metal-free method. Milder condition, operational simplicity, and low temperature reaction are the silence feature that render this protocol to be the better alternative to the regular organic synthesis. We have published this work in the Journal of the Heterocyclic Compounds in the March 2021. And again, I would like to thank Department of Chemistry, Sikkim Manipal Institute Technology in the collaboration with Association of the Chemistry Teacher and Homi Baba Center for the Science and Education, TFRMB, for giving us this wonderful opportunity to present our the research work. And I would like to thank the principal, Dr. Ranjit Patil sir of the Dr. D.Y. Patil ACS Women's College, Pimpri. They have given us to carry out our research in the college. Thank you very much, sir. If you have any question, please, I will take it.
Okay, thank you, Dr. Gaikwad, for the presentation. It was a nice presentation, and such a vast amount of work you were able to present in such a short time. Okay, so it was a good one. In fact, we are thankful to you all for presenting your work in this conference also. Okay, thank you. Yes, sir. Okay, now, Professor Vasudev, if you have any questions, you may ask.
Okay, we can go for next.
Vasudev sir, if any question, please ask, sir.
No, you have presented good. Very good
Yeah.
presentation, and you have synthesized very good compounds for the heterocyclic compounds. Okay.
Yes, sir. Yes, sir. Actually, we have developed this methodology. This methodology very useful for the functional group transformation. When we have to use, we can protect one of the hydroxy group or the alcohol group. Usually, when we use a DMSO in iodine in H+, and when we use a simply DMSO in iodine, when we carry out such reaction, there is 100% dealylation. But when we use iodine in H2O and in a DMSO, we can carry out the dehydrogenation and aromatization on the any functional group, any molecule that is a heterocyclic compound without dealylation. Means that is one of the novel report, sir.
Nice presentation. Okay,
yeah,
next one.
Thank you, sir. Thank you very much, sir. Yes.
Okay, so if there are any questions, you may go ahead with your questions. Okay, so in absence of any questions, we will move forward with our next presentation. The next presentation is oral presentation number 38. and it will be given by Lavina. Are you there?
Yes, sir, I'm there, sir. Am I audible?
Yeah, you can go ahead.
Okay, thank you, sir. Sir, is my screen visible?
Yeah.
Yes, yes.
Okay. Is it clearly visible now?
Yeah, it's clear.
Okay. Thank you, sir. Good afternoon, one and all present here in this session. As I'm Lavina Vijay Jagtap. I'm a TYBSc student of Dr. D.Y. Patil Arts, Commerce and Science Women's College, Pimpri, that is in Pune. Today I'm going to present my research paper, and my topic is mild and efficient ammonium chloride catalyzed greener synthesis of tetrahydrobeta-carboline. So basically, what is tetrahydrobeta-carboline? These are the necessary scaffolds having several bioreactive agents that properties. Today we know that tetrahydrobeta-carboline has wide range of bioelectrical activity such as antiviral, anti-cancer, anti-protozoal, antagonistic, and atropine receptor. So some of the bioreactive tetrahydrobeta-carboline, like here in the slide, we can see the various types of compounds. That is the terephthalate, tetrahydrohermine, harmacine, etc. So these are the biological active tetrahydrobeta-carboline. These are the alkaloids. So next we'll see what is the greener solvent. So basically, the greener solvents are usually used in enzyme-assisted extraction methodology, where the solvents with lower toxicity has various compounds. So here we can see the advantages of the greener solvents, that is the water, methanol, acetone, ethanol. So basically, they are less toxic. They have less toxicity, so they dissolve easily. So what are the advantages of greener solvent? Based upon the principle of green chemistry, there are a list of solvents such as water, acetone, PEG, DMSO, DMF, etc., and ammonia. So by using the greener solvents, we can synthesize various heterocyclic derivatives that include the antimicrobial, anti-cancer, antifungal, antiviral, antioxidant, then anti-tubercular, etc. Here we can see the green solvent, the green chemistry solvent, that is in Frenchman condensation, Wittig condensation. All these were the syntheses which were done before. So the aromatizing, the oxidation, you know all these methods. So basically, the main aim of my research paper is the origin of a research. So here we can see on the left hand side, we have done the reaction for the tetrahydrobeta-carboline, that is in presence of ACOH, TFA, PTAC. So in presence of water, L-tartaric acid, trichloro-135 triazine PCT. So this was first researched, and now which I am going to present today is the ammonium chloride, that is the NH4Cl in presence of MgSO4, that is the magnesium sulfate, in presence of the methanol at 60 degrees Celsius at 4 hours. So in the magnesium sulfate, the main use of this sulfate is it absorbs water molecules. So here we can see the reaction is formed. Then after that, we'll get the tetrahydrobeta-carboline. That is therefore the development of easy, economical, and conventional methods of synthesis of tetrahydrobeta-carboline is exceeding beneficial. So we have done this research on this in our chemistry lab also. My sir, Dr. Sunil Gaikwad, who had presented before, he helped us and he has also done that reaction. So based on the developed of Pichter-Spengler methodology, by using NH4Cl, that is the ammonium chloride, we have synthesized a series of tetrahydrobeta-carboline. That is, we get various types of yields, that is 3A of 85%, 3B of 87%, 3C of 85% again, then 3D of 89 and 3E of 90%. So it depends upon the structure also how much yield it is giving to us. As the reaction, there are different structures that are formed in every reaction. As you can see in the presentation also, it minute changes also affects the yield, like how much it will give us the yield. And the next, we'll see the mechanism in detail. So the reaction which we are working on or we have worked on. So the first, we'll dissociate the NH4Cl in NH4 minus and NH4 plus and Cl minus. So on the basis of the above results as reported in this structure, the literature we proposed a possible reaction for mechanism for NH4Cl promoted. So in this, the Picter-Spengler reaction of the tryptamine and aldehyde, that is of A and B, the ammonium chloride, a mild acid, can be activated in the carbonyl group in the presence of hydrogen bonding to enhance the nucleophile attack of amines in A. So we can see there is the attack of the hydrogen. We can see the bond also. Then the first step involves the formation of the imine intermediate in D. In D, we can see this is the intermediate form in presence of the shift base to the nucleophile attack of the amines, followed by the dehydration, that is the removal of water, reaction of the electron-rich tryptamine. Then A, we can see in A with the aldehyde and B in presence of an acidic catalyst, the imine intermediate undergoes a 6-endo-Fig crystallization and gives the product E, which is also catalyzed by an acidic catalyst to produce a product G. So this is the final product which we have worked upon or we have synthesized the compound, that is the tetrahydro-beta-carbonyl. So this is the end of my presentation, and in conclusion, it is the utilizing ammonium chloride as the catalyst. Like different types of catalysts were also used, but we have used the easy ammonium chloride as a catalyst as in anhydrous condition for the Pictet-Spengler reaction between the tryptamine and the aldehyde, could afford the tetrahydro-beta-carbonyls in high yield. The important features of these present protocol is a simple reaction to produce and work, simple reaction procedure and workup. So it doesn't take a lot of time and we can do it in short span of time also, and it is done very quickly. So the catalyst is water soluble and easily removed after the workup. So the catalyst which we have used is NH4Cl, that is an ammonium chloride. It can be easily soluble in water also. So this was the compound which we used while performing the reaction, and it's a mild reaction condition in operation simplicity. Means mild means in very easy method we have done this reaction and it is a quick reaction, so it gives us more yields also, and no column purification for offered very good yield. So as I told you also, a very good yield is also obtained after doing such a simple and easy reaction using the catalyst of the ammonium chloride to form the tetrahydro-beta-carbonyl. So thank you everyone. Thank you for the Department of Chemistry of Sikkim Manipal Institute of Technology in collaboration with the Association of Chemistry Teachers, care of Homi Bhabha Center of Science Education, Mumbai, India. And I also thank our principal of Dr. D.Y. Patil Arts, Commerce and Science Women's College, Pimpri, that is Dr. Ranjit Patil sir, and my guide and who has helped me in all this presentation, Dr. Sunil Gaikwad, who had presented before. We have worked on this, and so he gave me the opportunity to present myself. So thank you each one of you here.
Okay.
Yes.
Let me know what are the conditions for Pictet-Spengler reaction. Do you know?
Yes, Pictet-Spengler reaction in which
what are the conditions?
Pictet-Spengler reaction in which the beta-aryl ethylamine undergoes a condensation. Means condensation is done there in this reaction in presence of aldehyde and ketone.
Okay, show me the mechanism in which A and B is adding. You are adding reacting. What is the condensation there?
Condensation reaction. Okay. In that reaction, it is not synthesized, but it mainly undergoes the condensation reaction.
Okay.
Yes, sir.
But how much time take for the synthesis?
For the synthesis, the minimum time is of 4 hours, like 3.5, 4 hours, sir. Because it's a slow reaction and it takes a bit of time also.
Okay.
Yes, sir.
Okay. So
Means mainly the compounds of the NH4 minus and NH4 plus and Cl minus. These are the two compounds, these are the two molecules which are combined to form a single molecule, that is NH4Cl, and which acts in that reaction which we have performed. So that is mainly the condensation.
Okay.
Yes, sir.
As a catalyst.
Sorry?
You have used only one, no? Ammonium
Yes,
chloride.
we have used only one, yes, because there are various also, but as we have performed various.
You have to
Yes.
compare also. Okay.
Sorry?
You have taken an ammonium chloride. Also, you can take another one and then compare your results. Which one is better?
Yes,
Okay.
yes, we are going to try for that also, but this was a simple reaction and we had all the compounds also, so we have tried on this, the research, sir.
Okay, sir.
My sir has
Yeah,
done
Lavina,
all
thank
the
you for
Welcome,
the presentation.
Welcome, sir.
Okay, so I think we have come to the end of the presentation, and if anyone is left.
Sir, hello, sir. Ali, sir.
Yes, sir. Yes, sir.
Presentation number 30 and 31, sir told, no?
Yes, sir. So if 30 and 31 is there, so you may join. Oral presentation 30, 31, and 36. 36 is also not there. K.A. Gaikwad. Okay, oral presentation 30, oral presentation 31, and oral presentation 36. If you are there, then you may go ahead with the presentation. Sir, I don't think they are.
They are not present, yeah. All the three posters. Speaker, no? 36, 31, 30. Not present, okay.
Okay. So, sir, we should hand over the session to.
Yes, we can. Yes. No one is there, no?
Yes.
Okay. Hello, sir. Nayan, sir.
Yes, sir. Thank you. Thank you, sir.
We are absent. Okay. Not present.
Okay. Okay, sir.
OP 30, 31, and 36.
Got it, sir. Recorded.
1, 2, 3, 4, 5 have given the presentation.
Yes, sir.
Okay.
So we are exactly in time, and it's 1
Thank
minute.
Thank you so much, Professor Gurnele sir and Dr. Ali sir. Thank you. Now we will move ahead, but 10 minutes late. Participants are requested to wait maybe another 10 minutes. But by the time, I think our next speaker, Professor Claudia, has joined. Am I audible, Professor Claudia? I think you have joined.
Good morning to you.
Good afternoon.
Can you hear me?
In India, it is now good afternoon.
Okay.
How are you?
I'm quite fine. I'm all alone in university because university is closed because we've got the holiday season. And this is the week where almost everybody is on holidays and not at university. So it's a bit cold in here because the heating is turned down.
Claudia, it's Dr. Brijesh Pare.
Hi, nice to see you.
Claudia. Yeah, it's cold here also. At my place, it is almost 8 degrees.
It's the same in Germany. And it's foggy, you can see.
Okay.
It's all
so you are
foggy
most
out.
welcome. Thank you.
Thank you.
And such a time, it's the last week of December.
Yes.
Really very critical. And you are in the university, thank you. So nice of you.
You're welcome. Okay. So, pardon?
Hello, Pare sir. Good afternoon.
Yes. Hello, Dr. Gurnale.
Yeah.
Yeah, hello. Yeah, how are you?
Fine, sir.
Yeah. I'm in the college.
You are in the college?
Yeah.
Okay.
So we've got 10 more minutes left, right?
Yeah.
All right.
Professor Claudia.
Yes.
How is the situation of Corona there in Germany?
Well, we've got the Omicron variety of the virus, but it hasn't really hit us that bad yet. Right now, we have some limitations concerning numbers of people that can gather together, but still schools are open and university is in a somewhat hybrid modus. So we've got streamed lectures, but practicals in our labs. So it's a mixture.
Okay. Here in India, of course, the Omicron crisis is there, the numbers are coming.
Yes.
And as far as, now we are gearing up, rather, we are in fact worried about the third wave. And in different parts of the country, now gradually, I mean, the schools and colleges, they are closing now.
Okay.
Yeah. And but up till now, even in my university, the campus is open, and students are coming, and of course, hybrid kind of thing. We are taking online classes also. But even if the students are coming in, they're also frightened. Rather, if even it's open, they're not willing to come very regularly like that.
Yeah.
The parents also, they're also not very confident about the situation and all.
Yes. Yes, because it's very similar here. You have to wear your mask, but then you're sitting there with 200 people in the lecture hall, and you don't really trust those masks.
That is true. That is true. I wish, see, this third should be the last wave.
Yeah. Let's hope so.
Yeah, hope so.
But vaccination is progressing here. I just had my third vaccination as a booster, kind of. And by now, they actually allow children to get vaccinated too. And so we're hoping to get the virus out of schools.
Okay. So in our case, we had, most of, of my age and all, we all had 2 vaccines. Third, we call it, the booster, we call it, the precaution booster, the precaution vaccine. Yeah. So that is starting from 3rd of January. 3rd of January.
Oh, okay.
Yeah. But so far, the children, for children also for the first time between the age 15 to 18, they are starting, because so far in India, the children have not been vaccinated, but it's starting from 3rd of January. Like
okay. Yeah. Actually, they
but
started
about the age 18. And to all, the seniors and all, they already have the vaccine.
Yeah, that's good, because they are the most vulnerable, right?
Right. Yeah.
But we are huge in number now. That is our strength, I would say.
But we actually had a lot of breakthroughs at people who had 2 vaccinations, and nevertheless they got the virus, but it was less severe.
It's not severe. You're absolutely right. It's just like common cold kind of thing.
Yeah.
And they're all recovering. Here also, in India also, the death rate has really, really gone down.
Yeah.
And the second wave was very killer everywhere, probably in Germany also and in India also. The second wave was very, very killer, that was devastating.
Yeah. And the staff in the hospitals is very exhausted. So we are hoping for the Omicron.
Nobody knew. Nobody knew, how to handle it. That was the thing, no?
Right. So let's hope for the best.
Yeah, hope for the best. Yeah.
Sir, we can start, I guess.
No, start 2 minutes more. You can start. No problem.
Yes, sir.
Okay, we can start. Yeah.
Okay.
Okay, then we are now in the session 5 invited talk. Today we have 2 speakers in this session. May I request Professor Brijesh Pare, President, Association of Chemistry Teachers, to introduce our first speaker, Professor Claudia from Germany.
Okay, thank you. So I welcome all the participants and Professor Claudia Linde. So let me just read out the brief resume, and then you will be able to listen to her. So Professor Claudia studied chemistry and English in Düsseldorf University and absolved her teacher education program. In 2003, she finished her PhD thesis at the University of Duisburg-Essen on the topic photoelectrochemistry and electrochemiluminescence, opening a new scientific field for the teaching of chemistry. She continued to work as a scientific co-worker at the University of Wuppertal. Then in 2016, she became full professor at the University of Tübingen, where she set up a new department of chemistry education. In 2018, she became full professor at the University of Wuppertal. Professor Claudia, her research interest in the development of new experiments, didactical concept and media for teaching, energy conservation, conversions, bilingual chemistry education. She's the writer of a numerous chemistry school book. Chemistry education for so many years. And Professor Claudia, it's my privilege and honor to let you know that Association of Chemistry Teachers India, we have a mandate of propagating chemistry education across India. And for the last 21 years, our association has been doing it very successfully. So it's a great occasion to welcome you to deliver your talk today in our National Convention of Chemistry Teachers 2021. Thank you very much. You are most welcome.
Thank you so much for your kind words, your kind introduction. It's a great honor for me to get the opportunity to talk to you during this conference. I'm going to share my screen. I hope this will work. If you could protest if you don't see anything. It would be a help for me, but by now you should see my title screen, okay? And today I want to give you some insights into the work we've been doing in a program that focuses on energy conversions and which was designed for students of secondary education. Before I do that, I give you a very short introduction about where I am right now and what we do in chemistry education in Germany and at the University of Wuppertal. So compared to India, Germany is rather small. We've got only 80 million people and the country is divided into 16 states. And Wuppertal, where I'm sitting right now, is here where you can see this red arrow aiming at. So we are rather close to the Netherlands, and there's France not far away, and Belgium, and so on. So if we talk about teaching chemistry at school, our children start primary school at the age of 6. And they've got some kind of natural sciences on a very low basis. When they go on to secondary education, they are streamed for ability. We've got different kinds of schools, and one of them, the grammar school, leads to something we call Abitur, which is the leaving certificate to go on to university. And during secondary education, they already have chemistry as a separate subject at school. Those who aim for their Abitur also have chemistry on a rather higher level. And this is actually the group we are focusing on with the experiments that we develop. So I just told you where in Wuppertal I'm sitting, and our university is quite young. It's 50 years old. It was funded in 1972. You can see this is just a picture of a green field. And almost 50 years later, this green field is packed with buildings. And this is actually where I'm sitting right now at this moment. So it's rather green. We've got this campus here, and chemistry is in this modern building. We've got quite a range of different departments of chemistry. You can see this here. Something which might be rather special is food chemistry. And of course, I'm the head of the Department of Chemical Education here. So what does my work group do? And this is the result of what I'm going to talk about today. We are doing curricular innovation research. And this is based on a very simple fact. And this fact is depicted by these two pictures here. Years ago, chemistry education, or generally education, was mainly focused on the teacher, him or herself, as the one who had the monopoly of knowledge. And today, the situation has dramatically changed. students can get information everywhere, and students have totally different environments. They've got different media, they've got different hobbies, they've got different materials their clothes are composed of, and so on. So to put it in a nutshell, our world is constantly changing, and therefore curricula have to change as well and make our students from today fit for tomorrow's world. So what we are doing is we are looking.
Bandra, you also.
Can you hear me? Yep. Okay. So what we're doing is we are looking at cutting edge topics from current research and technology, and we design new simple experiments that show fundamental processes. We don't design high-tech cells, but it's rather didactic experiments that help students understand the basic principles of modern science. We tailor didactical concepts around these experiments and supply this also with concrete teaching and learning media for teachers. So we test and evaluate this in our pupils' lab. It's called Chemie Labothek. This is where students from high schools come to our laboratory, and our PhD students and our students who are enrolled in the teacher education program actually work together with them in the lab, and then we can see if there are any problems with the didactical concepts or learning media. And so in an iterative process, we try to optimize our materials and concepts. So this is basically the general way we approach chemical education, and the topic that is dealt with can be headed by energy and energy conversions. So we've got different foci in our work group. We look at the conversion of solar light into electric energy. We look at, this could be done in solar cells. We look at the conversion of chemical energy, bonding energy in some substrates, and convert this into electrical energy. This would be in fuel cells. We've got quite a range of different topics. I just show you this sketch to make you more curious, and maybe we can talk about this at some other occasion. But today, I want to move on to a program that we developed on energy conversions, and which focuses on 3 different aspects. One is solar cells, the second is fuel cells, and the third is photosynthesis. So what students need to know as prior knowledge is that we actually have different forms of energy: light energy, electric energy, chemical bonding energy, and so on. They need to know that there is the law of the conservation of energy, and they need to know that energy can be converted, different forms can be converted into each other. Other things they need to know is the reactivity series. They should know something about the electromagnetic radiation, the spectrum, and they should know something about bonding energies. And this should be enough prior knowledge to dive into our program. So let's start with the first aspect, which would be the conversion of light energy into electric energy. All the students know silicon-based solar cells, and we've got actually those modules you can buy for school and make some experiments with them. But if you just look at this, it's a black box. You can't construct this by yourself. You can just use it, and you don't really get an understanding of what is needed for this cell to actually work. We know some things about solar cells regarding the efficiencies. We know that, well, silicon is basically easily accessible from silicon dioxide. What students mostly don't know is that the production of solar grade silicon which is suitable for solar cells, is very, very energy consuming. So, that was the wrong direction. What students should also know is about the intensity of solar radiation. Sorry, I didn't translate this heading. And you can see that most of the visible area is this part of solar radiation which I'm pointing at. And in our program, we are looking at an alternative solar cell material which is less energy consuming during the production process. So this leads us to a substance students mostly don't know. It's a white pigment, titanium dioxide. And those of you who may be more familiar also with physics probably know those Grätzel cells, which are dealt with as a new generation of alternative solar cells. And in this first step of our program, we are approaching these titanium dioxide-based solar cells. In the second step, we are dealing with a conversion of chemical energy to electric energy. And those cells have been known for tens of years so far. And again, for schools, you can buy readily prepared modules of hydrogen fuel cells. You can actually put them together, so you can actually have an insight into the components constituting a cell like this. The students know that there's alkaline fuel cells. We have the fuel hydrogen and an oxidizing agent, which is freely and at no cost accessible, which is oxygen from the air. And what students sometimes don't know is that hydrogen is not always environmentally friendly produced. It's not always green hydrogen. You have to look at where the electricity comes from. So the processes are rather simple, so this should be easily graspable for students. And the new question for an alternative we raise is if there are also other cells, for example, and then we introduce biological fuel cells based on microorganisms, for example, yeast, baker's yeast. This would be our second. I'm going into more detail later on. I'm just giving you an overview. And the third station would be the conversion of light energy to chemical energy. And again, we've got something very, very traditional because life on our Earth is based on it. We've got natural photosynthesis, the production of oxygen gas via the irradiation of plants. You probably know this experiment. It's a classical biology experiment. We've got also information about photosynthesis being an endothermic reaction, And students usually know that depending on the concentration of carbon dioxide in the air and the intensity of light, you see different intensities in those lines here. The efficiency of photosynthesis can be quite different. And all in all, or at an average, it is rather low. So this is what students know. And we raised the question for an alternative, and this would be artificial photosynthesis. Is there artificial photosynthesis that we can mimic in the school's lab? For example, also to produce hydrogen. So now this should be the basis of the project we called E⁻⁴, exploring energy by experiments. So you've got 3 E's. That's why this is to the power of 3. And the program is, as I said, for students from secondary education. We try this out in our pupils lab, or we offer this there, where we've got those stations where a classic meets an innovation. And we focus on the energy conversions, which I already talked about. So this would be the general structure that the students go through. The materials they get, you shouldn't be able to read this. It's very, first it's German and then it's very small, just to give you an impression. They get some information about how to set up the classic, and they get information how to set up the innovation. And they can write down their notes. They get some questions that help them to explore the basic principles. And afterwards, we try to bring the innovation and the classic together and focus on the kind of energy conversions that take place. So the classic that they actually experiment with is the silicon cell. You can see the module that I just showed you, but there's also toys, probably tons of toys also in India for kids to play with light and something which our students really like is, I'm just going to show you if the camera is shifting. Yes, it is. You can see this little solar bug here. And I'm going, you can see here, I've got a torch, which actually gives differently colored light. And the students can play with this and irradiate this little bug with blue light, and they see nothing happens. They can irradiate it with green light. They see nothing happens. They can irradiate it with red light. They see nothing happens. But if you irradiate it with white light, whoop, it's moving away, then you can actually see that the white light is actually driving this little solar bug across the table. So with this first step, we can show with this very simple experiment with the torch and this little solar bug that light is not light. That's very short. That red light and green light and blue light and white light must differ somehow, and which this leads us to the wavelength of light, and that light of different wavelengths has different energy. And not every kind of energy is useful for, light energy is useful to actually power or convert light energy into electric energy in a solar cell. So this is the first very simple experiment with a ready-made classic. And we then move on to the innovation. And this is the setup of a titanium dioxide-based photogalvanic cell. I already said solar grade silicon is very expensive, so we try to move on to titanium dioxide. And titanium dioxide can be found in the environment as white pigment. It's a food supplicant. It's also used in suntan lotion and so on. So it's an everyday product. And you can actually put this into a cell which looks very similar to a galvanic cell, which the students know from school. Electrochemistry is compulsory for everyone in secondary education. So we introduce a photoelectrode, which is just a piece of conductive glass and a layer of titanium dioxide. And we inserted this into a container filled with a potassium bromide solution and connect this with another half cell with a platinum electrode dipped in a dilute solution of hydrochloric acid. So this is why we come to from galvanic cells to photogalvanic cells. And if you irradiate this, you can actually get a voltage and a very low current. In order to increase efficiencies, we can then move on to a more compact cell, which would be in a one-pot setup. Here we've got low-cost platinum electrodes. If you've got an electric razor, the foil, which is perforated, if you in Germany, there's some company called Braun. They've got, I don't have any investments in that. If you use them, the basic material is nickel, but it's coated with a very, very thin layer of platinum. So we use those electrodes as low-cost platinum electrodes. It's very nice also for other electrochemical experiments. So here we again have a platinum electrode, the photoelectrode dipped in an electrolyte. And if we irradiate here the photoelectrode, we also get an electric voltage and a slightly higher electric current because of the more advantageous geometrical setup. There's a lower resistance in the cell. So the cell can be made even more flat and compact, and this is what the students actually do. They make this compact cell with a photoelectrode based on titanium dioxide. They take those razor foils as platinum electrodes, some separator, this is just filter paper, and EDTA, ethylene diamine tetraacetic acid, as an electrolyte. And if you irradiate this in the semiconductor, you actually promote electrons from the valence band to the conduction band. So this is the first step, and in the second step, those charges are separated, which then leads to the to the voltage or the electric current. So the electrons that go out of the circuit can actually power a motor or do some chemistry in the best case. In order for the electrons to go out into the outer circuit, the holes that are created once you lift or you promote the electrons from the valence band to the conduction bands, they are stuffed by some donor. It's basically an oxidation process of the donor. And this is actually the driving force why the electrons move out into the outer circuit. So this is basically the same process depicted in a different way. You've got titanium dioxide, which is irradiated by light of a suitable energy. And then you've got electrons, which are kind of free, which you can which can move on into the outer circuit. And the hole which is left in the titanium dioxide can be then reduced or stuffed by a donor, which is then itself oxidized. So you can see with a little bit of electrochemical background knowledge, we can use redox reaction, the idea of redox reaction to understand what's going on here. And we've got the same principle or a similar principle, the generation of electron-hole pairs and their separation in the silicon-based cells. So what the students do, they irradiate in intervals and see only if light is shown on the photoelectrode, then we get an electric current. They can see that different colors show different results. In this case, we need ultraviolet radiation to actually get electric power because the titanium dioxide is white. It doesn't absorb colored light. And this band gap between the valence band and the conduction band is rather big. So we need light which fits this band gap. And this is actually in the region below 388 nanometers. So possibly you could continuate then to the Grätzel cell, which is photosensitized with different dyes. And we show the students that actually this is not just some chemical playground in our lab, but this is serious research done for a long time, more than 20 years by now, because here you see a review article on photoelectrochemical cells. Then the renaissance was already celebrated of dye-sensitized solar cells. And this is still going on, so we can show the students that this is serious research being done, and they make the very first steps in our lab to actually understand what is the basic principle in this. The second station would then be a station which focuses on the fuel cells, and the first one would be a typical alkaline cell. Here you can see our razor foils again, which are just inserted into an alkaline solution. Can be potassium hydroxide, 0.1 mole per liters. You can also take baking soda if you do this at home with little kids, and then you can actually have your conversion of chemical energy into electrical energy. After you've done the first step, which would be an electrolysis, because you need your fuel, your hydrogen at the one electrode, and the other electrode is then saturated by oxygen if we do this electrolysis step first. So this is basically a two-step experiment where we do the electrolysis, and then we actually power a motor by using the fuel we just produced in the oxidizing agent. The biological fuel cells we work this, as I said, work in a two-compartment or in one compartment cell. I'll show you the sketch here. You've got some substrate. It can be glucose, so sugar. And again, it works with oxygen. And we have some separation of the half cells. Protons, which are produced in this first half cell or in this left half cell, which is the anode side, can move on to the other side, to the cathode side. The general equation, which subsumes in a simplified way the process is taking place, would be the reaction of the sugar with the oxygen, supported by microorganisms, which is the baker's yeast. And you can actually see that carbon dioxide, or that a colorless gas is produced, and also water. This would be the overall reaction. And as you can see, this is a very simple setup with low-cost materials. We've got just some kitchen paper or toilet paper, whatever, as an electrolyte bridge. We've got this yeast and glucose suspension in the one half cell, and then we've got a glucose suspension without yeast in the other half cell. We can use iron nails as electrodes. So this is a very, very low-cost setup and shows a biological fuel cell, which actually produces a voltage. Here you've got a picture of the setup. Instead of the iron nails, you can also use graphite electrodes. We took those from pencils. You can buy those LEDs from pencils. Or you can use stainless steel electrodes. Here we've got a setup which is more compact. And if you connect both half cells after some time, when the yeast is starting to work, you can actually see that a voltage is generated in the cell, which is quite nice. If you don't use glucose, you can also use saccharose, and you can see a time delay of the voltage which is being produced, because first of all, the saccharose, which is has to be split into fructose and glucose, and then the enzyme can actually, or no, not the enzyme, the bacteria from the yeast can actually do their work. So this would be an alternative example of biological fuel cells. In the third and last step, we deal with natural photosynthesis, but also with artificial synthesis. And as I already said, you know this probably from biology. When you've got this water plant, Elodia, you can actually see those very tiny little bubbles of gas emerging if those algae are irradiated by light. You can, if you've got lots of patience, you can collect this gas, and it's a long time experiment, and test for oxygen. What we also do is we irradiate basil leaves with light again, those colored torches to show that light isn't light. Light of a special wavelength is needed also for the photosynthesis to work well. Green light is not that suitable because the green dyes don't absorb green light. This would be a nice additional experiment where you can actually then do a starch test with the irradiated leaves to actually show this point. But what I want to show you in small experiments here is the artificial photosynthesis, which can be done or shown in the lab via a very simple experiment. And it's called the photo blue bottle experiment, photo blue bottle. And this would be a model experiment for photosynthesis. What you need, I'm not really going into the molecules themselves. What you need is a photocatalyst. A photocatalyst which is irradiated by light of a certain wavelength. In this case, it's blue light. The photocatalyst is yellow. And it gets into an excited state if it's irradiated. And then a substrate, which is called ethyl viologen, is then reacting with the activated photocatalyst. And as you can see here, pardon? Oh, okay. As you can see here, it's actually a reduction taking place. And I'm going to show you this experiment live. I'm switching again the cameras. Just a second. And I'm taking out. Okay. If you have a look at my video, I don't know if you can enlarge this for yourselves. Have a look at the video. So you don't see me anymore, but you could see two yellow vials. And I'm going to irradiate this. You can see this yellow solution. It's a watery solution of the photocatalyst and a substrate, which is called ethyl viologen. And I'll show you, you should see this yellow vial now, and I'm going to irradiate this with blue light. Now the camera doesn't really show that it's blue light because it's a bit oversteering, but you should see something if we've got 30 seconds of patience. And I'm moving away this torch. You can already see something. You could see that the yellow solution turns blue. Okay, you should be able to see this. Now, if I take this away and shake it, you can see that it turns yellow again. I'm irradiating this again. And actually, I've got a second vial, which I'm also irradiating. The second vial is completely filled with the solution. And you can already make your own hypothesis. The first vial is only half filled. And I irradiated this, and it turned blue. When I shake this blue solution, it turns yellow again. So the process, the reverse process, the color change from blue to yellow might have something to do with the fact that there is air inside the vial. And once I'm shaking this, the blue solution has contact with the air, which naturally contains oxygen. So this should lead students to the hypothesis that the reaction from the blue to the yellow solution should be some kind of oxidation, which in turn should lead them to the conclusion that the irradiation is a process or starts a process which should be a reduction. And you can actually verify this if you've got a completely filled vial and a half-filled vial, and you both make them, the solutions turn blue, as you can see here. And then once you shake this, now I'm shaking the complete setup. That's nice. If you are able to see this, should be able to see this. You can see that this half-filled vial turned yellow again, whereas the completely filled vial stays blue because there's no oxygen inside to start this reverse reaction. So I'm changing the videos again. What we can actually show with this is the blue color is due to this substrate, the reduced ethyl viologen. And if there's oxygen present, you can actually start this reaction, this back reaction, this oxidation. So we've got processes in circles. It started with the irradiation of light. The photocatalyst is then activated. It's in an electronically excited state, from which this is able to actually start this reduction of the substrate, which is then oxidized again by oxygen from the air. A photocatalyst is always regenerated. So we have a third component, which I haven't mentioned so far. It is this EDTA, ethylene diamine tetraacetic acid, which we already used in the photogalvanic cells. And it's just a sacrificial donor, which is oxidized. So we've got these the circular processes taking place, mimicking photosynthesis, where you also have the irradiation of the chlorophylls, and then a whole cascade of reactions, which are also reduction reactions, can take place. The reverse process, the respiration, would be simulated by shaking this little vial. So then we've got basically the respiration, which is simulated by shaking and turning the blue solution yellow again. This is on a rather phenomenological level. We can go into more detail if we have more sophisticated students and look at the molecular structures and so on. But even at this very simple approach, we can already mimic photosynthesis and have a look at what is necessary for photosynthesis to take place. You can extend this experiment by using different colors of light, and then you will see that blue and also white light leads to this blue coloration, which you just saw. So green and red light are not suitable because the energy is not right, not sufficient to be absorbed by the photocatalyst. And you can also extend this experiment to an even more sophisticated version if you actually connect this with a second half cell, where you can then produce hydrogen as an energy storage by actually connecting those cells and by irradiating the photo blue bottle solution for some time. So this would be a more stable, a more stable energy storage. In a way, we could say that this ethyl viologen EV plus would be an energy storage too, but it's not very stable. As soon as I shake it, it's again oxidized. So this would be another way of looking further into artificial photosynthesis and looking at different ways of producing green hydrogen, which is very discussed topic right now. We've got some videos to show this, that actually the oxygen is emergent. It takes some time, therefore we've got this this video which has fast forward, so you can show this more easily. If you want, I can send you those transparencies, so you've got this QR code and have a look. It's also on our homepage. And so there you've got the same processes as I told you before, and you've got also the production of hydrogen as an energy storage. Sorry for these German words. So I see my time is over, but I almost reached the end. I hope I could show you basically what we focus on, how we work. I could give you some impression on the classics that we connect with innovative experiments, and the students actually get this this overview and should say which form of energy is converted into another. And we also talk about different ways that can be found of terms. Something like renewable energy production. Is this scientifically correct? If we talk about production, actually we can only convert energy from one form into another. We can't really consume energy. It's always a conversion of energy. Energy cannot be destroyed or created. And this is also something that we focus on when we talk with our students about these experiments in the lab. So all in all, I hope I could show you that we are trying, and that is well possible, to integrate cutting edge topics into chemistry lessons and into chemistry labs. We deal with these experiments to lead actually students to a sensitization regarding energy supply, because students often don't really think about where the energy comes from that they use to actually load their mobile phones with. And they don't usually think about that every click on a mobile device actually costs energy, in parentheses. We try to show by a series of experiments that energy conversion is always an overriding principle. And we produce a series of digital media, which I didn't show you today for reasons of time, but it helps with time-consuming experiments. You can actually show experiments very shortly if you've got this fast-forward version. And something that I think is very important, that we should also deal and reflect with our students about everyday language, to make them more sensitive to its use, and to possible misconceptions one might get when hearing that energy is produced or consumed. So we try to make them aware that this is something that future chemistry teachers should be aware of and be very critical about. So I want to thank my work group, which you can see here, and there's 4 heads I want to point out, because those are the ones who actually designed this program together with me. And we've got some financial support from our ministry and the chemical industry. And finally, I want to thank you for your kind attention. Thank you.
Thank you, Professor Claudia. Now, house is open for a discussion. If any questions, participants can ask. May I request participants, if any query, you can ask to Professor Claudia. She will explain accordingly.
Very beautiful small experiments, and demonstrating how that the different colors of light have different energy. So very beautiful, really very mesmerizing. This talk from Professor Claudia. I hope everybody enjoyed it.
Maybe I can point out, we've got a homepage with lots of videos and animations. Most of them, or many of them, are German, but some of them are English. And the pictures talk for themselves, so they don't really need a language. So if you want to, you can actually just have a little look about this. We've got also some English publications, so you can, if you want to take more time, because I had to rush a little bit.
I understand. Like next time, the Association of Chemistry Teachers, definitely, and thank you for having accepted our invitation. But please do come for more time, and we will be doing it in a workshop format. And our next speaker, Professor Mohammad Al Saha, is there. I welcome Professor Mohammad Saha also at the same time. So
hello, good afternoon. Thank you.
Yeah. And Dr. Nayan Kamal, please.
Yes, sir. Yes.
Say thanks.
Finally, I would like to thank Professor Claudia for accepting our invitation and repeatedly communicating to us that she will be joining. Even today also, she has sent a mail to me that I will be joining before half an hour. Thank you for your concern. Finally, I can say only one line that it is very interesting designs of new experiment for curriculum involving energy conversions. I think our participants are, since I think I have seen some students also there, definitely all are benefited from your speech. Thank you so much, and we will be in touch, and in future, definitely we will invite you to join in our various occasions. Thank you so much.
Thank you on behalf of Association of Chemistry Teachers India, and from my personal behalf also. Thank you very much, Professor Claudia. Thank you.
Thank you for giving me the opportunity.
Okay, now our next speaker, Professor Muhammad Hussain, you have joined. Thank you for joining. May I request Professor Suresh Arya to take the session? Are you online, sir?
Yes, sir.
Okay.
So myself, Suresh Arya, got opportunity to introduce Professor Muhammad. Am I audible?
Yes.
Sir.
You are audible, Suresh. No problem.
Thank you, sir. So Professor Muhammad is working at Department of Biology, Chemistry, Environmental Science at American University of Sharjah, UAE since September 2004. As assistant professor, he was assistant professor during 2004 to 2011. Then he has worked as associate professor since 2011 to 2016. He is also visiting professor of several organizations. He has completed his Doctor of Philosophy PhD degree in organic chemistry from University of Alberta, Canada in 2002. The topic of his PhD is controlling hydrogen bonding receptors using allosteric modulators. He has completed master's degree from the same university, from American University of Beirut, Lebanon in '96, and from same university he has completed his bachelor degree. Professor Muhammad has received several awards from reputed organizations. He has also guided several postgraduate and undergraduate scholars for their project work. He has published about 50 international journals, papers in international journals. He has also received several. So I wish to over to Dr. Muhammad.
Yeah, just 1 minute. So I, on behalf of Association of Chemistry Teachers, as the president of ICT, I welcome once again, Professor Muhammad Al Saha for having accepted our invitation. And sir, please, the house is yours. Please, you are most welcome.
Thank you very much for the invitation. Thank you for the kind introduction, and I'm very glad to be speaking this conference today. And I hope we'll be able to deliver some of the work that we work with undergraduate students in our institute, which could be applied in any institute with at least the basic chemistry and labs. Let me share my screen a second, please. Is my screen visible?
Yes, it is visible. Dr. Nayan, there is some disturbance, you know.
Yes, sir. Okay, I will meet maybe
Please
some
say
participants.
Sunny, you know, please say ask Sunny, you know, to mute it.
I will mute it, sir. Done, sir.
Right. So today I'm going to talk about the some of the materials that we prepare in our labs are related on or based on supramolecular chemistry. And these are functional materials that can be used for different application. And the work was done in collaborations with people from the American University of Sharjah and from the American University of Beirut, in mostly done by undergraduates in these labs. So supramolecular chemistry gained a lot of attention after the Nobel Prize in 1987 that was given to Cram, Lin, and Peterson, and it was at that time on the release, the press release of the Nobel Prize says that these are given the Nobel Prize for the development and use of molecules with structure-specific interactions of high selectivity. And these specific interactions, as defined by Lin later on, in which he defined supramolecular chemistry as the chemistry beyond the molecule, they are defined as non-covalent interactions. And this is an important point because non-covalent interactions are the basics, and they are important because they are quite dynamic, and they are the basics for the functionality and of biological systems. So when we look at proteins in biological systems, they have their structures in terms of primary structures or secondary, tertiary, and quaternary structures. The primary structures are based on the amino acid sequence with the covalent bonds. But all the other structures which leads to the actual functionality of proteins are based on these non-covalent interactions. So non-covalent interactions includes hydrogen bonding and hydrophobic interactions between groups which are present, of course, in aqueous solutions since it's in biological systems. We have ionic bonding, or also biological or biochemistry called salt bridges, which is the electrostatic attractions between plus and minuses. Of course, the proteins also have the disulfide bonds. These are not considered non-covalent. They are quite dynamic, but they are not considered non-covalent interactions. But these three main ones, in addition to pi-pi stacking, they dictate the biological, they actually crucial for the biological activity of biological compounds, such as proteins, as we said. For example, also antibody antigen interactions. We're talking about these a lot these days with the pandemic and all that. So for the antibody to recognize the antigen, such as the spike proteins on coronavirus, we need to have this correct shape and the correct orientation of these interactions of electrostatic, hydrogen bonding, and hydrophobic interactions. And that's why we're worried about mutations, because it alters these molecular recognition elements. That's what we call them. They are molecular recognition. The antibody will recognize these antigen through these interactions. This is also what is present in enzyme action in biological systems. For an enzyme to be able to act on a substrate, we need to have the correct fit. These are, they're not lock and key anymore as we used to view. These are induced fits, but they need to fit in terms of interactions. They need to fit in terms of size and shape into this. So the question here is, can we use biomimic these biological systems and make synthetic systems which will show these interactions, and we will be able to use these kind of pre-designed binding sites or biological synthetic systems that mimic the function of biological systems, and we will able to get a functional machine out of it. So this kind of what we call host guest system, in which we have a receptor which is designed reacting with the guest to bind and produce in terms of functionality. In an enzyme, we have a reaction that's taking place. Here, what we're looking at, for example, a simple example is a chemical sensor. So we design synthetically a binding site which has molecular recognition element to a certain element. And this binding site is connected to a fluorophore, a form like of a lamp, if you want to think about it. So when the binding takes place between the analyte, sorry, so when we have the interaction taking place between the analyte and the binding site, we have a change in the fluorescence of the fluorophore, and that gives us a signal that this is present in there. The concentration or the intensity or the change is usually correlated with the concentration, so we will be able to measure the quantity of the material that's present in it. So that is a functional, synthetic functional system that's similar to the biological system with the similar elements. And this is what we're going to show in here. How do we develop chemical sensors that will do these functions? Now, what we're working on is fluorescent chemical sensors. And why we use fluorescent chemical sensors? Because in fluorescent chemical sensors, we can use them, for example, for environmental monitoring analysis of, for example, water quality. If we are able to have this signal that's continuously monitored, and it will feed us to a system in which we are controlling the water supply or the wastewater treatment and so on, how is that going and where it's going and how we can control it. It's used in imaging. In medical imaging, we have a lot of cellular processes that takes place in which we have a certain concentration of analyte that is increasing or decreasing based on a certain material. And we can use that for biomedical imaging. It's used in developing molecular machines at the nanoscale, because in the nanoscale, you need to have a self-contained system which can sense what's present in there and react accordingly. And that's you need a sensor that works at that level. So it's self-controlled in a way. So these fluorescent sensors are quite sensitive because we are getting an emission at a very low concentration, so we can have a very strong readable signal. And it's based on the design of the binding site, we will be able to ensure that we have a good selectivity. And because it is intermolecular and non-covalent interactions, then we are able to have a reusable one, meaning that if the concentration increases, we have the reaction taking place where we have a binding happening. When the decrease an amount take place, then the analyte will go away, and then we have the binding site is ready again to bind. Now, in fluorescence, we could have either a non-fluorescent molecule, and when we bind, it increases the fluorescence of the fluorophore, or it could be a change in the fluorescence wavelength. So it fluorescent at a certain wavelength. When it binds, it fluoresces at a different wavelength. And sometimes we have the quenching. So the binding actually quenches the fluorescence. So instead of turning on the light, it actually turns off the light of these compounds. So what are the types of sensors? We are going to look at what we did, and we did use simple binding sites so that we can develop it as we go, and that at least ones which are quite well studied. So here I show you two examples of fluorophores. They are pretty much just based on the pyrene ring, and they are extended so that we have different range of wavelength in which these could be emitted. And these fluorophores are directly attached to chronometers. And chronometers are well known since the 60s that they can bind to metals, metal ions with different charges and different sizes. And that's why we're using two different chronometers, the 18 crown 6 and the 15 crown 5, to be able to bind into cations, ions which has the positive charge. So by changing this the size, we are changing the ability or the selectivity, and that's what we call the pre-design. And we have also the one which you have here, two binding sites. Here it has one binding site, and we'll see that we will have different dynamics of these ones. So the synthesis of these can be done in 3 or 4 steps, and it can be done, as we said, in by undergraduate students, mostly done by undergraduate students. We start from pyrene. We add the tertiary butyl groups on by simple Friedrich-Crafts alkylations. Then we do an oxidation of the double bonds, and then we do coupling with the diamines, which already have connected to it the binding sites. So in here, we showed you the cation sensors, and we have also the anion sensors. In the anion sensors, we have, instead of crown ethers, we have sulfur amine groups, which has on it 2 hydrogens, which are engaged in hydrogen bonding, as we will see later on. These will bind to anions. So these are another ions which are negatively charged. So I'll start first with the cation and the crown ethers. As we said, the size of the crown ether is an important factor, and the shape. And what I mean by the shape is crown ethers all have a similar shape, but the groups attached to it will affect the shape. If we have a group here, such as if the benzene ring, that will limit the flexibility because these oxygens are connected to the ring and they are conjugated to the ring. So the flexibility is more on this side. If it were just alkyl, then it will be more flexible. So the cation size and charge are the other factors which are important. So it's a combination of the size of the binding site and what also the properties of the analyte that we're looking at that will affect this interaction that takes place. So for example, if we take the crown ether 18.6, for example, with a large cation, the cation will not fit into or inside the ring. It will fit kind of onto the top of the ring. So it will bind to it will be more on the top of the crown ether ring. But if we have a small size one, it will fit inside. And that affects how these interacts with the system. Because if we focus on these, for example, 2 oxygens here specifically, the ones which are directly linking the system or the binding site with the fluorophore, we see that if we focus on these oxygens will have lone pairs present in either the p orbital or the sp2 orbital. So if we have the large group is coming to bind, it actually binds from the top and it will be interacting quite a bit with the p orbitals. It will still be interacting with the p2p orbit, the sp2 orbitals, but will have quite a bit of interaction with the p orbitals, which means that it will affect the conjugation of these oxygen atoms with the ring. On the other side, if we have the small one going into the ring, it will interact more with the sp2 orbitals. These will have different change in the signal of the fluorophore because the electronics between the binding site and the fluorophore, the changes upon the binding are different. So how do we monitor those? How do we know that the binding is taking place the way it's taking, and how do we know that the reaction or the signal is coming out? One way to follow up the binding is to go actually through by NMR. We do what we call NMR titrations. We take the monomer and we add the cations into it. I just want to know that these done in organic solvents or a mixture of organic solvents like DMSO, acetonitrile, or chloroform. And because to be able to do the NMRs and to have a strong binding, because in water, these will not have very strong binding that will reflect that. So when we do these here, we look at the changes, the chemical shifts that takes place in the hydrogens which are on the benzene ring and the hydrogens which are on the crown ether. And when we compare those, as we go up, the percent amount of the metal is increasing. So with these electrostatic attraction between the oxygen and the positive charge leads to the downfield shift of these hydrogens in the ring and on the crown. And from that shift, we can actually tell what's the binding site and how the interaction selected for one over other or prefers one cation over another. Now, once we go look at what happens electronically in terms of the absorption and the emission of those. So when we look at how does the emission of these fluorophores change by adding the metal in there, we see that once we add a metal such as barium, which has a double charge and it's a large atom, that we have a decrease in the emission that takes place of the original fluorophore. At the same time, we have a new peak showing up at around 525. And when we do the titration though, and we follow the emission or the fluorescence using the single charge such as sodium, which fits inside the crown ether. So the barium will fit on the top, the sodium will fit inside. We see that we only have a decrease in the emission. We have no new peak showing up in here. And that's, as we will see later on in a minute, when you have barium with the crown ether, since it's big and it's doubly charged, we actually have two crown ethers sandwiching it. And that sandwiching of the two crown ethers with the two molecules leads to the formation of this peak, which is what we call the axial peak of the pipe. And I will show you in a minute what I mean by that. So this is more obvious when we go into the dye-substituted fluorophore with the two crown ethers. And again, when we use barium, here we see an interesting and a really nice way of looking at these dynamic intermolecular non-covalent interactions. The barium, as we add it in, as we go up to around 1 equivalent of the barium added, we see that the emission of the fluorophore decreases. At the same time, a new peak shows up at 520. That's up to 1 equivalent. If we continue adding after that, then we start seeing the reverse. Then this emission starts increasing again, and this emission starts decreasing. So what's happening in here? We're still adding barium, we should have more effect. Here, if we look at the emission, if we look at the intensity of this peak and we monitor it, and we just plot it against the molar equivalence of the barium added, we see that the emission decreases up to about 1 equivalent, starts increasing, and maximizes about 2 equivalent, and then kind of levels off after that, no more increase. It doesn't go back to the original was, but it increases to about 80% of what it was in before. So what I believe is happening in here, and what we can see this by NMR too, is if we think about the molecule as we have these crown ethers as the rings, and this is the fluorophore in the middle. Once we add the barium and we still have barium less than 1 molar equivalent, we will need 2 crown ethers to bond. So we end up with a barium sandwiched between 2 of those. And this leads to a system in which we have the crown ethers can rotate freely around it. So we end up with this kind of interaction. So at 1, we have something like this, where the 2 fluorophores are on top of each other. They actually self-quench. That's why the emission decreases, because they quench each other. They form what we call the aximer, which is the peak that we see in here at 520. That's indicating that we have the formation of these sandwiched that's taking place. Now, as we keep adding in until we reach 1 molar equivalent, then we end up with now a 2 formation of a sandwich form, where we have 2 barium with the 2 molecules connected together, and that's we have the minimum quenching, the minimum emission, that's the maximum quenching. As we add more, then the equilibrium will shift now towards each crown ether having its own barium attached to it. And once we reach the 2 equivalents, both crown ethers has 1 barium attached to it. In this case, we're breaking away the sandwich and the emission is going up. So we're starting with a molecule by itself, high emission. When we have binding of 2 of the molecules with the 2 of the at 1 molar equivalent, that's the minimum emission because it's self-quenched. Then we increase, and then we reach back to where we have the molecule bond with the 2 barium atoms, and that's emitting. And that's a dynamic system, as we said again. It's quite affected by the amount of the compounds present in there and how it changes. That's similar to biological systems. If you have inhibitors, you have substrates, the enzyme will adjust, react, and goes back to before, as it was before, ready to react again as the concentration changes. Here we see that if we compare the barium with other ions, we have barium, calcium. Here they have similar behavior. Both of them are doubly charged. So the charge has an important effect here because it leads to the formation of these sandwich bonds. We have the potassium, which is singly charged, but has a little bit of a dip in there. And the reason for that is potassium is larger, it's too large to fit inside the crown. It still can bind to two crowns, but it's not strongly bound because it doesn't have only one single charge, and that's why we don't see as much of an effect. And then the sodium fits in, and the lithium is actually too small to have a major effect on these emission. Again, the main factor affecting the emission here is actually the charge, because that leads to the electronic changes that take place. Now, once we go from the 18 crown 6 to the 15 crown 5, we see the effect of the size decreasing now will change the preferences, especially for the singly charged one. So with the doubly charged one is still preferred. Barium has the highest effect, followed by calcium has the highest effect. But now once we go to the singly charged one, we see that lithium has the highest effect, not sodium anymore. And the reason for that is lithium fits inside in here very snugly. It has a stronger binding to it, and that's why it has more effect on the electronics. And in this case, we're looking at the absorption, not as much on the emission that we see for these ones. Now, we switch from the cations to the anions. We have the same fluorophore, but now we have the binding site can form hydrogen bonds. And these hydrogen bonds, depending on the anion, we can have the formation of the two hydrogen bonds to one or to two atoms, as we will see later. So in this case, we also have one binding site or two binding sites. And we see when we look at the absorbance here, once we add the anion in, such as the cyanide, which is quite toxic, as we've seen in previous talks before. And the absorption changes quite a bit with clear isospastic points indicating we have from a strong binding that's taking place with the new between the cyanide and these hydrogen atoms. And then if we look at the emission, we also see very strong effect. In this case, we have kind of shift on the fluorescence. So we have a decrease in the fluorescence about 400 or 500, and a new peak showing up about 550. And that increases with the amount of the cyanide present in there. And this is, if we compare the different anions, for example, for the cyanide, we have a linear increase up to about 1 molar equivalent. And then after that, it levels off because it has a very strong binding between the cyanide and these hydrogens. So the other ions which has a similar effect are the carboxylates. We have the acetate and the benzoate, because these can form strong also two hydrogen bonds, because the carboxylate has two oxygens that can form two hydrogen bonds at the same time. CN, of course, is a strong base too. And we have the fluorine, which have a strong binding, but it's the emission effect is less on this. And we can see here it's a little bit of change of the fluorescence. This is just the compounds with 5 molar equivalents of these anions under UV light to see that we can even visibly see the change in the fluorescence or the emission. Now, once we go into the di substituted or with the molecule which has two binding sites, we even see a stronger effect, especially from the fluorine. We have very strong effect, similar to before. We have clear isospastic points that are showing up. And then when we look at the ratio of binding, we also clearly see that it's 2:1. This is what we call job plots that gives us the ratio of the binding of the fluorophore with the receptor, the sensor with the anion. Now, once we look at the fluorescence, we see clear and strong change. We have a complete quenching of the fluorescence of the original anion and a strong increase of the fluorescence so we have 450 decreasing and 545 is increasing. Actually, if we plot the intensity here, or we follow it over the equivalents, how many equivalents of the fluorine we're adding, we see clearly when we have 2 molar equivalents, the emission is almost all quenched at 450. And now we start seeing the increase or the formation of, so as we add more fluorescence, more fluorine in there, we have more binding that will take place, and we have an enhancement of the emission that takes place now at 550. This is, of course, based also on the new V. We know that it's a new system that is forming, and because of the binding of these ones. So if we compare or we look at the different anions, we see again now fluorine is quite strong, similar to acetate, benzoate, and the cyanide. These are the strongly basic ones, strong hydrogen bonding, and we can also see a visible change in color for these ones. Originally, the receptor has a blue emission, and when we have those in there, we have a yellow emission that's under UV light again that we can see these ones. So now we are moving from the cations to the anions. We've been looking at charged species where the electrostatic attraction is very important in here. But can we do this with molecules which are neutral? They don't have a charge. Indeed, we can, and we have done that with other molecules too. That I will show you in a minute. But the molecules that we have shown so far have two hydrogen bonds that can bind to these. Can we have more directionality in this? Here is another example. We have 4 hydrogen bonds instead of 2. They are more directional, and they are bound to a denser fluorophore. Now, this shows the urea, which has 2 and 2, that can bind to a molecule which is able to bind to 2 hydrogen bonding sites. So here, when we study this molecule which has the bis urea and the densyl, we study it with different anions, and the anions which shows us the strongest enhancement in the emission are the oxalates and the phosphates. And the oxalates are important anion for biological systems. They are actually present in a lot of kidney stones products. They contribute to the formation of kidney stones in there. The oxalates, the high level of oxalates in urine indicates the possibility of this. So when we study those in a DMSO mixture, we see that the intensity increases quite a bit. It's about 2 times or 2 to 3 times of the phosphate of the oxalate, about 2 times for the phosphate enhancement in the emission of those. And once we compare those to other anions and to other dicarboxylates, so we have oxalate compared to malonate and to succinate, we see the oxalate has the highest emission, although these ones also have 2 carboxylates. They don't cause as much of an emission. We also have the similar thing if the oxalate stands out among all the other ions that we tested it. So why is that? Because the oxalate fits better. The binding site of this system fits the size and the orientation of the oxalate as compared to the other ones, although they have similar functionalities and charges, such as the malonate and the succinate. But the malonate and succinate are too big to fit into this binding site. The oxalate fits in there. We have hydrogen bonding with these ions, and that can be clearly seen by NMR. These are the NH peaks, which have the star on them. As we add the oxalate in there, we see that these peaks start shifting to the left downfield because they are bound, hydrogen bound. And then we see that at one point, and when we have to one equivalent, they totally disappeared. And the reason for that is when they are strongly hydrogen bonded in a system, they can undergo chemical exchange easier, and then they change to the deuterium. We can't see them anymore. But we also see the effect even further away from the binding site. We see it all the way up to here for the hydrogen on the amino group here on the methyl groups. This will start shifting upfield instead of downfield because once we have hydrogen bonding, the system now is more electron rich. We have here these 2 peaks or these 2 hydrogens, HB and HC. These, before we bind, they are overlap. They have formed like a triplet. Now, once we have the bonding taking place, this HB, it's kind of locked in a place. They are not rotating around this bond anymore, and they start shifting and separating from each other. So the interaction that's taking place at the equivalent or the binding site, it's not only there, it transfers further away, and that's why it affects the emission of this fluorophore, because the electronics are changing. in the whole system. So now we shift gear from anions and charged ions to non-charged molecules, in neutral molecules. Melamine, which is this molecule in here, has been taking a lot of attention the last couple of years because of, not couple of years, actually a couple of decades. It's been discovered as been added to dairy products and pet products in order to falsify the amount of protein that's present in there, because they look at the amount of nitrogen, and this has too many nitrogens in there, so it falsifies the amount of proteins. But this has serious effects, especially on kids. It leads to the formation of crystals in the kidney and lead to kidney failure, and several cases reported for kids or pets dying because. So what we did here is we prepared a molecule, a sensor again. We have a carbazole now with 2 barbituric acids, and this provides hydrogen bonding and which fits the melamine and a size or a cleft that is correct size and shape. So we propose that that's going to happen is we have hydrogen bonding taking place between these 2 molecules. In that hydrogen bonding, due to the conjugation with the carbazole, will lead to the change in the emission of the carbazole in these molecules. So we studied this system first in organic compounds. And so we studied this system in, hello, can you hear me?
Yes, please continue.
Sorry, yeah, because I had a little bit of disconnection. Okay, so we studied first in DMSO, and when we look at the change in the emission, and here we had only minimal change in about 10% decrease in the emission when we added the melamine into the solution. The melamine is not very soluble in organic solvents other than DMSO. So, but in order for this to be useful, we need to be able to use it in aqueous solution, because if it's added into pets products or food items, then it is an aqueous solution. So we then study it in a mixture of DMSO and water at 50-50 ratio, and here we see a huge decrease, about 80% or 90% after at 200 micromolar concentrations, about 10 molar equivalents of the melamine added. But we also noticed that the emission at 0 with no melamine increased for this molecule. So we said, okay, well, let's study it again at 99% to see if that's, we will be able to still see an emission, because ideally you want to be able to do it in water, but the receptor is not very soluble in water. So you dissolve it first in DMSO, then you add water. So we did it in 99% water and 1% DMSO. We still have a change, a decrease is not as efficient as in 50-50 because the hydrogen bonding is not as efficient anymore. But then an interesting thing is we saw is that again, if we look at the emission of the sensor alone, it increases as water is added in there. This indicates that the fluorophore here, in this case, acting in opposite way that what you expect. It has what we call an emission or aggregation-induced emission or fluorescence. Usually, as we've seen in the previous slides, that when you have fluorophores binding or aggregating, they self-quench. In this case, in the last 2 decades also or 3, they have observed that some of these actually, some of fluorophores are not fluorescent unless they aggregate, they become more fluorescent. And in this case, we studied this molecule alone by just changing the amount of water it present in solution. We look at its fluorescence. Here, the molecule alone in DMSO and under UV light, and we see that there is no visible fluorescence. As we start adding water in, so we're going from 100% DMSO to 99% water, we end up with an increase in the fluorescence, which stabilizes at about 60 or 70% of water added in there. And we can see visibly the emission under UV light that is shown there. With that, we thought, okay, well, maybe we can use aggregation as a process here to determine melamine, and we have a better signal in this case, since it's an aqueous solution. Now, one thing which is known about melamine, it actually binds strongly to cyanotic acid, and they form a network even in aqueous solution, and they precipitate out. They aggregate. If you have high concentration, they actually see a visible result. So we said, okay, if we have these in solution, maybe then we can increase the aggregation of our sensor, and then that will give us a better signal than we have in just the solution itself, and that will give us an easier way to monitor the presence of millimeter. And indeed, we tested that. To be able to test it in high amounts, we use even 96 well plates and measure just the emission in there. And we see that by going into spiked water with the melamine, we add it in there, and we add in the same time cyanotic acid. So we have cyanotic acid at high concentrations present in there. We have our sensor present in there, and then we add the melamine. And as the concentration of melamine increases, we have the emission of the molecule increases. Actually, now we are going into a turn-on sensor instead of turn-off sensor, which is much more desirable because you're turning on the light instead of turning it off when you have melamine, and that is linearly coordinated with the concentration. So, okay, that's great. It works in water or in 99%. Let's try to see if it works with a spiked milk. We take powdered milk, spike it with melamine, dissolve it in water, and we look at the emission, and indeed we also have an increase. It's not as high, but we still as measurable and linear to the concentration of melamine in the milk products or the spiked milk that is present there. So this shows us that there is a possibility and there's an ability to be able to use this. It's still at the concentrations which is slightly above the recommended or the accepted levels of melamine in this, but with fine tuning of this, we will be able to produce a much more efficient way of getting the dose. Now, I think I'm running out of time. It's probably have another 5 minutes, so I try to speed it up a little. Now, we have seen so far sensors in which we have 1 or 2 binding sites, and we're looking at the fluorescence and the emission. Now I'm going to switch gears to a system in which we have instead 1, we have multiple binding sites, and it can also be pre-designed with these molecular regulation elements, and it can bind to more than 1 gas at the same time. And these are the porous organic polymers. We form polymers pre-designed from certain blocks, which has ability to bind to things such as iodine and metal ions. Now, why iodine, why metal ions? Iodine, especially in the gas form, is emitted from a lot of nuclear power plants. And this is our radioactive iodine. And there need to be a process in which you can take this away from the air or the emission before it actually goes into the environment and causes harmful because it's radioactive. And of course, the heavy metals comes with a lot of from industrial wastewater, and also we want to be able to remove those. And we can also detect them and remove them at the same time. So we prepared polymers, porous polymers, from blocks that has a melamine unit and anthracene, which is a fluorophore also. And this unit provides us with heteroatoms that have a lot of lone pairs that can bind well to the metals and also bind well to the iodine, and a large conjugated systems which are known to also bind well to iodine. And we use aldehydes, monoaldehyde or bisaldehydes, to join these by Schiff-based reactions, and we form the aminal. And we end up with 3 different polymers in there. All of them has the fluorescent unit present in them, and they have a lot of nitrogen. They are nitrogen rich, they have heteroatoms, and we'll have also, this one has the sulfurs on the top of the nitrogens, which also provides more lone pairs to bind to these ones. And then we look at how much of these can hold or take of iodine from the gas phase. We take the polymer, put it in with iodine sublimed in the atmosphere, and we look how much iodine it absorbs. We see a visible change in color. I'll show you a better picture than this. And we are able to absorb about 300% of its weight. So 3 grams per gram, 3 grams of iodine are absorbed into 1 gram of this polymer. It can absorb it from the gas phase, and it can absorb it also from solution. Here we can see we have about 1 milligram of solution with 1 milliliter of a polymer at different concentrations of the iodine in cyclohexane. And over 48 hours, or even 72 hours, we almost have complete absorption of the iodine into these polymers. Now, the same time though, because these are fluorescent, when you absorb the iodine in there, you are quenching the fluorescence of these molecules and of these polymers, and this is actually linear quenching over a certain range of concentration. So we can measure the amount of iodine present in there. So these polymers can act as hosts to grab away the pollutants that we don't want, and at the same time, it tells us if they are present or not. The same thing happens with the other two polymers. They are quite efficient, and we see here clearly the changing color as iodine is added in there. But these binds much better to also metals and with high selectivity to iron. The emission decreases quite a bit for iron as compared to all other ions that we detected or measured in there. Now, with these polymers are able to hold in iodine, I just need 3 more minutes. I'll be done. With these, we'll be able to hold in iodine. Iodine, again, this is a non-covalent interaction. Its absorption is a physisorption because of this interaction of iodine with these large surfaces and interaction. It can actually release the iodine. And if it can release iodine, then we can use iodine because iodine is known as an antiseptic. So we can use it as a process to deliver iodine as a drug delivery system, if you want, or antiseptic, especially to clean surfaces and to kill bacteria. Now, we've prepared a different type of polymers for those. We didn't need to have the fluorophore in there, but we have large two molecules, one with a larger surface area than the other one, and we tested them for this. They absorb iodine again, similar to the other ones. They function in the gas phase. They function in the cyclohexane with different extents. But we also can see them that they release almost all the load of iodine from this one is released by just putting them in ethanol over a period of about 3 hours. They will have a full release of all the iodine that's present. And we can actually recycle those. After they release the iodine, we can dry them, use them again. And we see we did at least 4 cycles. It kept about 50% of its original ability to hold in the iodine. So what we can do with that iodine, if it can be released? Well, we can use it to kill bacteria. Since iodine is a strong antiseptic and it's not soluble in water, if you want to use it, usually they use it with other alcohol. But here in this case, we have a slow release of iodine that can take place. So we tested it with 3 types of bacteria: E. coli, Pseudomonas, and Micrococcus. And these we planted those on a petri dish, on agar petri dish, and we added as a control just the polymer itself without any iodine, and we added the loaded polymer, the iodine-loaded polymer in there, and we incubated overnight. And we see clearly for the 2 polymers that we prepared that we have inhibition ring that's forming around these ones, which has the iodine in there. And here, even for the second polymer, we see it even more clearly, especially for the Micrococcus one. So we have higher activity on the gram-positive one versus the gram-negative one. So in here, we are forming polymers with a lot of binding sites, pre-designed with, depending on the block structure that we use. They can hold iodine, they can release it when we need it to. And these can be applied, for example, with, as we've seen earlier, with wound dressing material with hydrogels, and they can release the iodine in there, help to keep the wounds cleared from bacteria, and that can go in there and causes infection. So I hope that by the end of this lecture, I have shown you that we can use molecular recognition elements, non-covalent interactions of hydrogen bonding, electrostatic interactions, to pre-design a functional material that can be able to act as a sensor or as a host or as a drug delivery vehicle for things such as iodine as an antiseptic for bacteria that can grow on surfaces. At the end, I would like to thank the people who worked on this, my co-workers, Dr. Rinia, Dr. Ruth, and the undergraduate students who worked on these projects from our group, Aya, Muhammad, and Abdurrahman. on our collaborators, Dr. Bilal Skafarani Group from American University of Beirut and Dr. Osama Qadiri from American University of Sharjah and their students. Also, we have 3 undergraduate students who work on this project, actually 2 undergraduates, 1 graduate student, master student, and the postdocs from Dr. Osama. And we thank the American University of Beirut and of Sharjah for the funding. And thank you very much for listening to us and for the invitation and giving us the opportunity to present at this conference. Thank you. If you have any questions, I'm right.
Suresh sir, over to Suresh sir.
Sorry?
Over to Suresh sir. Professor Suresh Arya, are you online? Okay, anyway, thank you, Professor Mohammad Hussein. If any question, floor is open for discussion and question. Any question from the participants?
Hello, hello?
Yeah.
Is there a question?
Any questions from the participants? I think there is no questions from participants. Thank you, Professor Mohammad Hussein.
Thank you very much.
I can tell you at the end only that it is really a very interesting discussion about supramolecular chemistry. Here, basically, you have highlighted design and preparation of fluorescent chemical sensors, which is one of the most important topic in chemistry. I hope our participants are benefited with your speech. Thank you so much for accepting our invitation from the Department of Chemistry, Sikkim Manipal Institute of Technology, and Association of Chemistry Teachers. I would like to thank you for joining with us. We will be in touch in future. Maybe again we'll invite you to join in our different events. Thank you, sir. Thank you so much.
Thank you.
Thank you very much for the invitation.
Thank you, Professor Muhammad Al-Sayad. On behalf of the Association of Chemistry Teachers, as a president and on my personal behalf, and thank you very much for giving a wonderful talk. And please keep coming and just get connected with us. And Association of Chemistry Teachers will get back to you soon, for some more programs and your talks.
Thank you very much for the invitation. Thank you for giving me the opportunity, and thank you for your time. Have a good day.
Thank you.
Good luck with the rest.
Okay.
Thank you.
Okay. Bye. Thank you, sir.
Okay, our next session.
Bhattacharya ji,
technical session 6. Technical session 6. I have seen Professor VP Singh sir in online.
Bhattacharya ji, namaskar.
Namaskar sir, namaskar. Thank you so much. Thank you so much.
2-4 minute late ho gaya sir main.
No problem, sir. No problem. I thought that you will be joining.
I'm in the office. I sent message to Gupta also.
Yes,
that I'll
sir,
be
yes,
joining,
sir.
but I was doing my section officer and the other officer. They are sitting here by my side.
Okay.
So we are doing some confidential work.
Okay.
But I'm now connected, so I'm happy to see you. And I must congratulate you for everything nicely planned and organized. I have been to your university, sir, in DST NCSTC program.
Okay.
I think it was 10-15 years back.
Okay.
We'll see you together.
Okay, thank you, sir.
So
Okay,
you
then the technical session 6, I request Professor VP Singh, sir. Sir is on screen now, everybody has seen, and Dr. Santanu Gupta to take over the session. And here we have 1, 2, 3, 4, 5, 6, 7, and 9, 10 approximately papers are there. They are going to participate. Sir, please take the session.
Okay, Bhattacharya, thank you. So as per the list provided, Gupta ji?
Yeah. Yes,
okay.
sir.
Okay,
I'm here, sir.
namaskar.
Yeah,
Good
namaskar.
morning this afternoon.
Yeah.
So we can just take up this first one. We can call the first presenter R. Tope. R. Tope, Dr. Tope.
Dr. Tope.
Dr. Tope. So we can invite him or her.
Hello. Sir, he's here.
Dr. Tope. Okay.
Now,
Dr. Tope.
Dr. Tope, please, you please share your slide.
Hello. Am I audible?
Yes, yes, you are audible.
Yes.
Okay, sir. Good afternoon to all.
Good
First
afternoon.
of all, I thankful to the organizer for giving me an opportunity for the presentations. Here I will present the research paper on for synthesis of novel iron chromate with magnesium oxide nanoparticles for efficient photocatalytic degradation of xylene orange dye. Before I start my research papers discussion, I will explain about me. I am Dr. Dr. Tope from HPT Arts RIT Science College, Nasik, Maharashtra, India. Here, whatever the synthesis I have done, it is related with the perovskite oxide and metal oxide, and whatever the oxide I have prepared, it is a core shell type of oxide. So why we require the core shell type of oxide and what is the application I have given, we will see here. Here for that, first of all, I will go for the synthesis of iron chromate, and for that I use a hydrothermal synthesis method. In that, a simple iron nitrate, that is a salt of iron I use, along with the chromium nitrate, and a surfactant I use for that in a particular Teflon autoclave. In that, along with these, I added sodium hydroxide having the normality 1.5 normal. And then this Teflon autoclave kept in an oven for 24 hours. After that, I filter it, wash it, and dry it at 80 degrees Celsius. And further that, I calcine it in muffle furnace at 800 degrees Celsius for 3 hours. And then we get the iron chromate oxide or perovskite. This peroxide is characterized by using different analytical techniques, that is FTIR, UV DRS, XID, SAME, EDAX, TEM, SCD. This iron chromate gets converted into the modified metal oxide by using magnesium oxide. Similar method I use here, only the one change is there. Here the reactant, that is the precursor we use, that is a magnesium chloride along with the iron chromate. And another, whatever the procedure I use for the iron chromate, which is similar to the for the modified metal oxide also. After the preparation of this modified metal oxide, again I characterize this in using a different analytical techniques. Here the characterization I have done for the iron chromate and modified iron chromate is the FTIR first one. In that, if we see, the A shows the FTIR of iron chromate and the B graph shows the FTIR of modified iron chromate. And in that, we found that whatever the iron chromium oxygen bond is there, it is present here nearly 950 to 400 per centimeter. And it indicates that the formation of a component or presence of iron, oxygen, chromium oxygen, and magnesium oxygen bond. After that, we go for a band gap energy, because for a photocatalytic activity, always the band gap is one of the important parameter. So here, using DRS technique, we have seen whether the band gap changed or not, and we found that in the first graph, here the iron chromate I have taken, it shows nearly 500 nanometer, and due to this the band gap is nearly 2.5 electron hole. And then we go for a second graph, that is iron chromate with magnesium oxide, and we found that whatever the wavelength shifting is there, it increases, and due to this wavelength shifting increases, the band gap becomes decreases, and due to this, the iron chromate along with the magnesium oxide gives a good photocatalytic activity as per the UV-DRS technique. Then we go for the next analysis, that is the XRD. Here the A pattern gives the iron chromate XRD and B pattern gives the iron chromate with modified magnesium oxides XRD pattern. Here we found that whatever the XRD analysis is there, this XRD analysis gives the idea about the formation of iron chromate. In that, these iron chromate XRD data is matched with the JCPDS data, and we found that it shows a cubic type of structures having a slightly hexagonal structure because of magnesium oxide present in that. And along with this, we've calculated the particle size, and it nearly 90 nanometers. It indicates that the presence of nanoparticles, some particles are nanoparticles. After that, we go for the same analysis. Here I have taken the three same analysis. First one is related with the iron chromate. Second one is related with the iron chromate with magnesium oxide, and third one is related with the iron chromate with zinc oxide. If we see whatever the morphology they have given, it's just like a flower, like, or just like a agglomeration presence on that. Here the ADAX is also given. This ADAX analysis gives the presence of iron, chromium, and oxygen in the iron chromate. Similarly, in the B, presence of iron, chromium, oxygen along with the zinc, and third one in that the presence of iron, chromium, and zinc, magnesium in the given compound. It indicates that formation of the core shell, that is FeCr2O4 along with the magnesium oxide. But whether the core shell is obtained or prepared or not, it is confirmed by using TAME analysis. And here the TAME analysis I have given. The picture B gives the idea about the TAME analysis of iron chromate, and the picture A gives the analysis of iron chromate along with the magnesium oxide. Here I have shown the iron chromate which is present, and on that the shell is present because of magnesium oxide. And we confirm that the formation of iron chromate along with the magnesium oxide core shell particles. Here along with this, whatever the ACD pattern is given, this ACD pattern is well matched with the XRD pattern, and we confirm that whether the formation of iron chromate with magnesium oxide or not. In this way, we analyze the iron chromate and the iron chromate along with the magnesium oxide. Here, our aim is not only to synthesize and characterize the metal oxide, modified metal oxide, but our aim is to give some application for that. And hence, here I have given the one application for such a type of catalyst, that is the photocatalytic application for dye degradation. And here we use a dye, that is xylitol orange dye. Already we have seen that the UV-DRS gives the idea about the whatever the compound or whatever the oxide we prepare, it gives a lower band gap, and that's why we go for a photocatalytic application. And for that we use a xylitol orange dye. This dye, why we use? Because whatever the xylitol orange dye is there, it shows a various properties, that is antimicrobial property, mutagenic property, and it is used to prevent the fungal growth and all these things. But along with this, it is also used in a textile, in paint, printing ink, then masking tape, clear plastic tape, surgical tape, and black electrical tapes, etc. But when it is in an excess form and when it goes in a water, then it becomes harmful to the human being due to the various toxic properties. So to minimize such a type of toxic property of these dye, we use the photocatalyst, that is iron chromate along with the magnesium oxide. For that, we optimize the reaction condition to get the better result for the degradation, and hence we optimize the dye concentration, we optimize the amount of catalyst concentration. In the first figure, I have shown the concentration variations for a dye, and we found that whenever we use 0.4 gram of iron chromate core with the magnesium oxide for 30 ppm, it gives a better result as compared to the 10 ppm, 20 ppm, 40 ppm, and 50 ppm. It means it requires less time as compared to the other, and it shows a maximum percent of degradation. That's why here it indicates that at 0.4 gram, the 30 ppm up to the 30 ppm dye solution, we can easily degrade by using a catalyst, that is iron chromate with magnesium oxide. After the confirmation of dye concentration, we go for the amount of catalyst, and here we optimize the amount of catalyst by having 0.2 gram. In the first, we have taken the 0.2 gram, then 0.4 gram, 0.6 gram, 0.8 gram, and 1 gram. We found that whatever the degradation rate is faster, it is faster for a 0.4 gram. And here I have shown in the figure. It is due to the excess amount of catalyst when we add. It may be gets coated on a particular dye, and due to this it lost the catalytic activity. Hence, the 0.4 gives a better result as compared to the other amount of catalyst. After the confirmation of amount of catalyst, we go for the comparison of photocatalytic activity with the different photocatalysts, and we found that whatever the iron chromate along with the magnesium oxide, it gives a better result compared to the other. After that, we go for the electrolytes, because number of electrolytes are present in a water, and due to the electrolytes, it may affect to the particular photo degradation. Here, the number of electrolytes I have taken, and according to the electrolytes, whether it will be affect to the degradation or not, I confirm here. And we found that whatever the chloride is there, then sulfate is there, then phosphate is there, it will be affect to the degradation. So it indicates that whatever the electrolytes is there, it may change the percentage of degradation. Here, for the confirmation whether the degradation is occur or not, we use UV visible spectra, and here I have taken the UV visible spectra at a different time interval, and we found that for the iron chromate along with the magnesium oxide, after the 50 minutes, we get the nearly whatever the absorbance is there, it minimizes maximum as compared to the only iron chromate oxide. In the iron chromate oxide, after 50 minutes, there is no minimization of absorbance at 494 nanometer as compared to the iron chromate with magnesium oxide. Here we confirm that whatever the dye solutions or whatever the dye we have taken, whether it gives a fragmentation or not. When it gives a fragmentation, whatever the lambda max is there, it gets diminished. And here I have shown in the figure second, after the 50 minutes, it diminishes. And to confirm whether the fragmentation is occur or not, we use LCMS analysis. Here I have taken the LCMS analysis before the dye degradation and after the dye degradation. Before the dye degradation, whatever the mass for a particular dye is related with the 475, and when we degrade it, we get the different fragmentation of that dye, and the possible fragmentations we have confirmed by using the LCMS, and we get the idea about the possible fragmentations. Here I have given the possible fragmentations for a degraded dye. Here the possible fragmentation we get in a different way. After the complete dye degradation, whatever the fragmentations are there, they gets converted into CO2 and water molecules. It indicates that whatever the degradation of xylene or orange dye is there, it is complete because of LCM. It confirmed by using the LCMS. In this way, we have confirmed the dye degradation by using LCMS analysis, by using UV visible spectrum before the dye degradation, after the dye degradation. These indicates the here after the confirmation we go for the recyclability of the catalyst, and here the recyclability of catalyst we perform 4 times, and we found that very less amount of or very less percent of degradation vary in a number of times because of leaching and because of loss of catalyst after the number of times reusability. Due to this, only the loss will be there, but there is no loss, there is no any change in the degradation.
Dr. Tope, please conclude because there are 8 more participants are there.
Yeah, okay, sir. Here I have prepared the synthesis. I have prepared the core shell metal oxide by using hydrothermal method, and after that I characterize this by using different analytical techniques, and after that I use this oxide for the degradation of xylenol orange dye. Thank you, sir.
Thank you. Thank you, Dr. D.R. Tope, for such a wonderful presentation. If there is any question, just for within 1 minute, please, if someone wants to ask, please ask. Yeah. Okay. So our next presenter is Gobin Bagaria.
Gupta sir.
Yes, sir.
Can I have your number, WhatsApp number?
Yeah, sir. 7797 89 3308.
08. Okay, so that we can share the core sheet, no?
Yes, sir. Share it through WhatsApp. That's sufficient.
That's why I am asking this one.
Thank you.
Thank you.
So our next presenter is Govind Bagaria.
Govind Bagaria, okay. Welcome, Govindji.
Please share your side.
Govind Bagaria.
Are you there? Dr. Govind Bagaria? Okay, then the next presenter is A. Agase.
J. A. Agase.
J. A. Agase. Dr. J. Agase, please share your slide. Madam, your slides are visible. Please start.
Yes, sir. Hello, am I audible, sir?
Yes, madam, you're audible.
Yes, okay.
Just raise your voice a little bit.
Yeah. Okay. Respected dignitaries and my dear friends, I am Dr. Mrs. Jyoti Agashe, working as Associate Professor in the Department of Chemistry, HPT Arts and Arvate Science College, Nasik. And the topic here for my today's presentation is the 1-pot 3-component synthesis of 2-amino benzobromine derivatives by using nanocrystalline cerium carbonate catalyst. This is about the short introduction about catalysis. Catalysts are an important mineral and they are thermodynamically stable and important material in industry. They uses both acid, base and redox properties. It is an important raw material in various industries such as pharmaceuticals, modern electronic industry as well as glass industry. There are different types of catalysts like metal carbonates, metal oxides, dope metal oxides, bimetallic oxides, composite oxides as well as peroxide. And this today's work is about metal carbonates. We have synthesized the metal carbonate and studied their properties in organic reactions.
Ma'am, keep on speaking, please. We can
Yes,
see your slides.
Yes, sir, there is some problem with this made, I think.
No, it is visible. We are able to see your slides. You keep on speaking.
Yes, okay, sir.
Keep on explaining.
This is about the synthesis of sodium carbonate catalyst. So here we have synthesized the sodium carbonate catalyst by hydrothermal method by using sodium nitrate, glycerol and triethanol amine as chosen as a surfactant, and they are mixed together in presence of water and sodium hydroxide. It is stirred for 30 minutes and transferred into the autoclave for about 24 hours. After that, the product which is formed is filtered, washed and dried, and then it is calcined for about 450 degrees, and the product obtained is the nanocrystalline sodium carbonate. UVIR, then XRD, same EDAX, same etc. So this is the FTIR spectrum of the sodium carbonate. It shows the specific frequency for carbonate in the range of around 1400 to 1430, which indicates the formation of the metal carbonate. Similarly, second one is the X-ray diffraction analysis of the sodium carbonate, which shows the hexagonal structure of the product which is formed, and it is compared with the JCPDS data found to it is about 23108. After that, we have done the analysis like SAME and EDAX. So SAME is the technique which is used to study the morphology of the compound, and here the same analysis is so this is the same and EDAX pattern of the nanocrystalline sodium carbonate. So same pattern it is found here, and EDAX analysis which is used to study the elemental composition of this sodium carbonate. Similarly, the TEM and SCAD pattern is also studied, and the TEM analysis, it shows the hexagonal nature of the sodium carbonate, and the particle size was found to be about 27.67 nanometer, and it is similar to that of the XRD. After that, we have studied the BET surface area, and it is the important property to study the organic reactions for this particular catalyst, and it was found that the BET surface area for this catalyst, it was found to be maximum 173.49 centimeters square per gram. Similarly, pore volume and pore diameter of the catalyst was also calculated. So this was about the different techniques which we have used for the characterization of the synthesized catalyst. After the characterization, we have studied the important property of this catalyst, that is in organic reaction. Here we have prepared the benzochromine 3 carbonitrile starting from this sodium carbonate as a catalyst. This benzochromine 3 carbonitrile, it is very important compound in as it shows a different biological properties, like it acts as an bronchodilator, vasodilator. It is useful in as anti-tumor, and it shows various neuroprotective properties, anti-diabetic, etc. And here at the end, the different reagents are given according to the literature survey. The various catalysts which were used before for the preparation of this benzochromine, they are listed here. And we have synthesized this particular benzochromine carbonitrile using our synthesized metal carbonate catalyst. So here the procedure is given, which is a one pot 3-component synthesis in which we have mixed together the naphthol, then aldehyde, which are various substituted aldehyde, malonyl in presence of our catalyst sodium carbonate and methanol is chosen as a solvent, and the reaction mixture is heated at about 80 degrees in the oil bath, and the product which is obtained, it is characterized and tested with the help of the TLC technique. And after that, here we have used the different substituted aryl aldehydes. So here the list of different aryl aldehydes which we have used here in this particular synthesis, they are shown in this particular table. And for each the starting compound, that is the aldehyde, the time required for the reaction as well as the percentage yield which is obtained, it is also recorded. Similarly, for each of the product, we have recorded the melting point and it is compared with that of the standard melting point. Then optimization of this reaction we have studied with the help of different techniques in which we have chosen different types of catalysts and carried out the same reaction like potassium carbonate, zinc carbonate, tin carbonate and sodium carbonate which we have prepared, and it was found that the sodium carbonate, the reaction which is carried out in presence of the sodium carbonate, it gives the maximum yield within a very short time compared to that of the other catalyst. Similarly, the percentage, that is mole percentage of the catalyst is also selected here. We have carried out the experiment by choosing the different types of catalysts starting from 0.1 mole to 1 mole, and it was found that with the help of 0.5 mole of the catalyst, it gives maximum yield and reaction also takes place within a short period. Similarly, here the solvent selection was carried out using different solvent. So here we have selected different solvent and we have varied the temperature range and using methanol, then DMF, ethanol, acetonitrile, etc. And the temperature variation was also carried out. And again, it was found that when we use methanol as a solvent at 80 degrees, then it gives maximum yield and the reaction time is also very low compared to that of the other solvents. Then recyclability of the catalyst is one of the important property of our catalyst. That is, this catalyst, as it is an organic catalyst, it can be recovered from the reaction mixture, and we have used the same catalyst for next 3 to 4 runs, and it was found in every time that the yield obtained for the reaction, it was remain practically same. So the good yield was obtained using the same catalyst which we have used for 3 to 4 times. The product which is obtained here, that is benzochromate, we have studied the NMR and CMR of this particular catalyst. Conclusion, we have successfully synthesized metal carbonate and confirmed their catalytic activity by various methods. And also we have developed an efficient and recyclable catalyst for simple organic reactions. Thank you, sir.
Thank you.
Thank you.
Thank you, Dr. J. Agassi. If there is any question, it's open to the floor. Anyone can ask question to her. Okay, in that case, we can. I think there is no question, so we can proceed to the next speaker, Dr. Gajanan Dongare. I think, yes, sir, you are here. I can see you. Okay. Sir, you just, you share your slide, and okay, I think, yeah. You please share your slide, and video though is not required.
Okay, sir.
Yeah, yeah.
Yeah,
Sir,
am
it
I
just,
audible?
yeah, you are
And my slides are also clearly observable.
Yeah, sir, please make it full screen. Make it full screen. That full screen sign is there at the in the Power PPT down below. Yeah, right. Side.
Yes, yes.
Make it full screen.
Okay, sir.
So now it is fine.
My research topic. Hello, sir.
Yeah, yes, sir. It's visible. You can start speaking.
First of all, I am thankful for the organizer of the Sikkim Manipal University and the National Convention of the Chemistry Teacher NCCT and 2021. My research topic. Okay. The thesis spectral biological process. My thesis, synthesis, spectral, and biological thermal decompositions and the kinetic studies of the metal complexes with new hydrazone. The sections which have been covered for the experimental material method, synthesis of hydrazone, ligand, general synthesis of the metal complexes, result discussion, IR, spectral studies, NMR, C13 and mass, magnetic and electronic spectral studies, same studies, and thermal and biological studies. So here, my research topic, the introductory parts of that particular thing, heterocyclic aryl hydrazide bases are find enormous application in the pharmacology, antibacterial, antifungal, antidepressant, anti-analgesic, antiviral activities. The chip bases have been developed for the chemical sensor photoilluminations application extensively during the past 2 decades. Coordinating the ability of hydrazide chip bases are attractive application due to the coordinate to the metal ions through its bidentate, tridentate, and their coordinating functionality like NO, ONO, N2O4. The next material and methods which have been used here, all the chemical AR grades and the elemental analysis have carried out at the Punjab University, elemental, and that is on the Carlo Arba 11108 and elemental analysis. FTIR also present in our department have been recorded. FTIR spectra were recorded and Bruker Advanced. C13 H1 also recorded Bruker Advanced spectrophotometer. Mass spectrum also recorded and QTO spectrophotometer. UV visible spectrophotometer also available in department and recorded the UV visible electronic transition spectra of the compound in which ligands and metal complexes. The Shehud magnetic susceptibility also given ideas about the whether magnetic susceptibility of the compound to know the exact numbers of the electrons. Then thermograms have been also recorded on in our department, Sant Gadge Baba Amravati University, Amravati, India. Main part of the synthesis of the ligand is very difficult now because the reactions require much more times and the very difficult to reflux and require 8 to 10 hours conditions. After that, of the yellow compounds which have been obtained, we have taken the 3 grams of 0.03 mole of the 3-methoxysalicyldehyde, and then it is mixed, reacted with the 4-oxo 1-carbopiperidine hydroxides in the ethanolic solution by adding the 2-3 drops of the H plus catalyst. We got here a yellow compounds of the hydroxides, 2-hydroxy, 3-methoxybenzylidene, 4-oxypiperidine, 1 carbohydrazide ligand having a such type of the moieties. The tridentate moiety O, N, and this N, this particular thing is very important. This is the ketoenol formation of the ligand, keto in the solid and the liquid in the enol forms, in which we clearly observe these 2 oxygens and this 1 nitrogen formation of the tridentate linkage with a very specific one. This is the 3D views of the ligands and the MEP, electronic potential, molecular electrostatic potential with surface lucent of the ligands I have made for the clearly observable of this carbon. This is the nitrogen, and these are the red colored by the oxygens. Next, general synthesis of the metal complexes, of the newly synthesis of the complexes of the hydrazone, carbohydrazone. In the ethanolic conditions, these 2 mix, reflux, and we got here a colored complexes of the chromium complexes with a trivalent natures. This is a 3D views of the metal complexes through trivalent, and these are the looking a divalent. Also made a MEP structures of that molecular electrostatic potential of a surface lucent structure of the chromium and the ions here. We have analyzed this compound. This one, microanalytical analysis of this compound, having got the C14 CH17 N3O4. This is the molecular formula, and this elemental analysis you have carried out and found that these 2 are the experimentally and the calculated values are nearly same, and they confirm the structures. For more confirmation of the ligand, we have the ligands are subjected to IR and the NMR studies. Then it is clearly observable. 3410 use the OH, phenolic OH, and the frequencies of this NH are observable here, 2994. And more on the remaining that also coincide with the theoretical values, and NMR studies also we have carried out for the confirmation of the exact structures of the compound. The C13 also carried out for the also to determine the carbon skeleton of the ligand molecules. These are the spectral values of various carbon atom from C2 to C13 carbon atoms. Remaining mass spectrum also recorded 291.50. These are the electronic studies and the magnetic and solution conductivities of these compounds from the chromium to zinc complexes, in which the molar conductance also reveal that the low conductivity, it means the non-electrolytic condition, non-electrolytes, the magnetic susceptibility of a compound, which shows the various structures. All these are the octahedral except the zincs, that is the square planar structures in this compound. Some values of the absorption maximum as quoted here in the nanometer, also centimeter inverse, and their spectral assignment also clearly. Hello? Hello? Am I audible, sir?
Please continue. Mute करिए.
Hello. Then ligand pair parameter also a good obtain the good results, and we show the particular we would say here I have to say that interelectronic repulsion is less than the Raka parameter. And the Raka meter, it suggests that the covalency is present near about 75, 85 and the 68 and 67%. So I have also performed this scanning electron microscopy studies of one ligand and another zinc metal. So it clearly observed that ligands structure in this like a rod structures, a cylindrical rod structures, and that is destroyed after the formation of the zincs, and it is varied from the ligand. It suggests that the complex air formation taken place. And this is under that is a 10 kilovolts applied the voltage, and you will get the picture at a 100 micrometer. Here also 10 micrometer are also you get a nano size particle of that. Then TG study of the metal complexes also have been carried out, the ligands and the complexes, chromium complexes. These complex of the chromium have been taken as a representative to know exact contents of the compound for the confirmation of the structure. Here, first of all, figures, we suggest there is only one peaks are obtained experimentally. That means one organic compound, organic moiety is losses at a 370 degrees Celsius. That means nothing in that compound without a carbon, nitrogen, and oxygen, which are the organic compounds which are here. In the second thermograms, 1, 2, and 3 losses are observed. That is the first of all the 100, near about 100, there is loss of water, then chloride 250 to 240, and then organic moiety, that is starting degradation from 300 degrees Celsius and left the metal oxides of that. Okay. Then this is the thermal data of a ligands and the metal complexes. Here 370 observed here, and the experimental and the theoretical values are closely related to each other, and we got here the organic moieties, and then remaining chromium, manganese, ferrous, cobalt, and nickel, copper. These are the complexes I have seen. From that study, it revealed that the thermal stability in order of this nickel is lowest one and zinc is the highest one. So these are the trends which are in this order: nickel, chromium, ferrous, and successively goes on increasing with in this sequence order. We are, for our interest, biologically studies have been carried out for the application purpose. This is a y-axis inhibition zone, and the x-axis, that is the complexes, and the standard drugs which are correlated with here as a positive control. Standard drugs as a positive control, and these are the subjected to screen various strains of the pathogens. Aspergillus niger, Candida albicans, these are the two fungal, and remaining the bacterial, positive, 2 positive and 2 negative. E. coli, S type E positive, and these are the 2 negative bacteria which are gives a reports particularly against the standard drugs. It reveals that manganese gives us a very good activities, whereas zinc also gives activities against these biological activities. These are the some references which have supported references from starting my guides. Honorable Senior Professor Dr. A.S. Aswar, head of the department, Santa Gadgi Baba Amravati University, has published in 2000 paper 2010, and from that we here up to the 10. Okay, these are about my synthesis of the hydrazide and their metal complexes, divalent and tetravalents of the successfully have been done, and some paper elsewhere, and the Taylor Francis have been published my paper. Okay, thank you, sir.
Thank you, sir. Thank you very much. It's a very beautiful presentation. And
okay, thank you, sir.
Yeah. So the question answer session is there. It's open to the floor. Anyone can ask questions from the audience.
Okay.
So just wait for a while if there is any question. Okay, so thank you very much.
Okay, thank you, sir.
Thanks for the presentation. Nice presentation. Okay. So our next participant is Dr. Shanay Naha.
Yes, sir.
Yeah, yes. Dr. Shanay Naha, you please share your slide.
Okay, I'll share mine.
And then start your presentation.
Thank you so much.
Okay.
Actually, I cannot share because SAD yet not.
Yeah, sir, please unshare your slide. Yeah.
Yet not been done.
Professor Gajanan Dongare, please unshare your slide. You just close it. Close.
Further close your screen, I think.
Yeah, yes, sir. That's
you need
close
to close your screen also.
Yeah,
yes.
Close your screen.
So Shanay Naha, can you display your slides, please? Shanay Naha. Okay, screen sharing is shown. We have to see your slide. Okay, you are there. You are there. Okay, you can start, Dr. Shanay.
Yes, sir. Am I audible?
Yes, clear, very clear. In Delhi also.
Thank you so much. Thank you so much. Yeah, myself, Dr. Shanay Naha. I'm appointed as Assistant Professor in the Department of Chemistry, National Forensic Sciences University, Tripura. First of all, a very good afternoon to everybody, whoever presented, and thank you for inviting me for this talk. So my topic is actually lysosome targeted dual indicator for irreversible in vivo imaging of hypochlorite and H2S redox dynamics in cancer cell. So before we get into my presentation, I will show you the chalk line of this entire presentation. It will be consist of introduction, followed by objective, why I did this in research and all. Then whatever the findings I got, and rest I will summarize my entire research. So first of all, the hypochlorite and H2S is very, very important in our cellular system. Though hypochlorite is known as one of the most stablest reactive oxygen species in the environment, and it is very, very harmful in natural science, but it is very, very important in our body to run the entire body system, just like proliferation, differentiation, and apoptosis. And inside the body, there is always a continuous redox couple is going on between H2S and hypochlorite, which is like this. So H2S has both two side of way. One is for the apoptosis pathway. If it gets to GSH, then it land up in production of ROS, which is detrimental to our body. And it has been published in Antioxidant by T. Corsello. So the effect of excess generation of ROS is really, really detrimental, which leads to an oxidative stress, which is not at all deserving condition for our body. And ultimately that cellular activity entirely gets hampered, and because of that we can land up to any sort of a disease, including cancer. So actually to balance that, we need an in situ production of reductant. But having said that, H2S is also not that great to our body if it presents excess or before that. You can see in the next image that there is a limit. Below that, it is actually a detrimental to our body. Even we can die by excess production of H2S. So from this slide, it is very, very understood that both the things are very, very essential to our body, but excess or less will be detrimental to our body. So on that, I have a plan to develop some receptor to understand or to identify whether any body system or cellular system is excess or less of the redox system. Basically, I want to identify the redox couple if the cell is, or if any body cellular system is excess of hypochlorite or H2S either. So for that, I have designed a synthesis process for a molecule which has been identified by the technical proper spectroscopic techniques, followed by the detection limit, which can be detected in naked eye. It means my process is to not to use any instrument for the real-time sample. Rather, it can be used by any layman. And to understand entire process, I have to do that. I had done that DFT calculation and followed by real sample analysis. So let's get into the results and discussion. So this is the one-step synthesis process. That is, this molecule is very, very novel, though it looks simple. Naphthalimide moiety is very, very well known for its fluorescence part, and morphine is very, very targeted towards the lysosome. It is well established. So by developing that molecule, I have tested all this molecule for the solvent effect and the solvochromic effect. And for that, I have tested this for all the anions, which are mostly detrimental to our body. And if you can see in the colorimetric aspect, the H2S and hypochlorite are giving color change. But if we keep under the UV light, only hypochlorite is giving you the turn on emission. By understanding or getting this result, I have put forward that this is the fluorescence and UV visible spectroscopy against this entire photograph. So you can see entirely hypochlorite and H2S is giving a very, very absorbing band around 500 to 600. And only hypochlorite is giving emission band near around 550, 560. So these are the primary or very mandatory parameters which I have kept all constant for all my experiments. That concentration of the receptor I have kept in 25 micromolar, and all the analytes are in 15 micromolar in water. And most importantly, this molecule can work in water condition. That is most important. So after getting among the selectivity of hypochlorite and H2S, I wanted to know that whether this molecule is very, very selective to hypochlorite or any other reactive oxygen species. In that case, I got only hypochlorite as the selectivity. And that can be understood by the UV visible and fluorescence spectroscopy. Rest, I went for what is the concentration and what is the identification limit of my receptor. And while doing that, I got that things that this molecule is requiring 2 equivalent of hypochlorite to get its saturation, while it need 1 equivalent of H2S to get saturated. And after that, I got the limit of detection for hypochlorite in 10 nanomolar, whereas in case of H2S, it got 18 nanomolar. And this 2 equivalence and 1 equivalence is also depicted in the transition point spectra. So it is well understood that the molecule can consume 2 equivalent of hypochlorite to get its saturation. So from these concepts, I have tentatively developed a sensing mechanism that how this molecule can absorb 2 equivalent of hypochlorite and 1 equivalent of H2S. While doing so, I got this results that the hypochlorite can oxidize this receptor in 2 nitrogen position, I would say tetrameric nitrogen. And where in case H2S has a reducing property, which can reduce the nitro group to NH2 group, which is aptly supported by the HRMS spectra. While in case of oxidized molecule, we are getting M-1 peak. In case of reduced molecule, that means NO2 to NH2, I am also getting M-1 peak. So as I got told that if we get a theoretical practical data, we have to support by a theory. So I have did with DFT calculations, and in between middle is our main receptor, left hand side is the oxidized molecule, and right hand side is the reduced molecule. So why we are getting fluorescence on for the hypochlorite, that is aptly depicted, that you can see we are getting a reduction in energy band, and which is invariably going to 455 nanometer. So though it is not exact, but I'm able to convince that this molecular orbital gap, this energy gap between the HOMO and LUMO of the main molecule and the oxidized molecule, it's definitely getting reduced. While in case if it is reduced, the gap getting increased, that's why it is not able to produce any fluorescence. Because for fluorescence, we need a stable, fast state. After getting this, I tried to do in the cell imaging. So first I tried to examine whether this molecule having a toxic effect on our normal body cell or not. So I tried this, and you can see even after 25 nanomolar micromolar level also, it is not exceeding more than 80%. So after that, I tried this confocal imaging of endogenous imaging of hypochlorite. It means that these cells are live. Once I feed with PMA, this molecule is able to produce in situ hypochlorite, which is excess. It means that I told in the initial slides that oxidative states. So once the cell gets oxidative states, this will give fluorescence like this, that green one. And once this oxidative stress is get reduced by hydrogen sulfide, you can see the barely any green fluorescence. So these experiments exactly depicting which has been presented from the log. So here I comes to the conclusion. That first conclusion is that I have successfully designed this fluorometric and colorimetric sensor for this semi-aqueous medium. Second, it got color change from orange to green because of hypochlorite, and for H2S it was intense pink in 20% water DMSO medium. Third, we got a very excellent nanomolar level selectivity along with very 0.76 quantum yield. Fourthly, that this molecule are able to detect by a traditional detecting spectroscopic techniques. Those are mass spectroscopy, visible and UV visual spectroscopic. Last but not the least, that this molecule is very susceptible or very biocompatible towards application for real-time samples. And I would like to say that this molecule is under progress for the real-time applications. Thank you for having me, and thank you for your presence and patience.
Thank you, Sanay. It's a beautiful presentation.
Thank you so much, sir. Sir, you are not audible actually.
Any question to Sanay, please?
May I ask question? May I ask question?
Yes.
Please, sir, please.
Yes,
Can I?
First, you
Yes, sir.
introduce yourself and then ask the question, please.
Sanay,
Yes, sir.
can I ask a question?
Definitely, sir. You are. Please go ahead, sir.
Yeah, your anion limits is not so high.
Which
How
limit,
the selectivity is coming? On what basis you are telling that your sample is selective?
My sample is
You have not incorporated many anions here, which are most close to OCl minus, as per your hydrogen bonding formations.
sorry, sir. This is not hydrogen bonding. This is oxidative reaction. This is chemodecimetric.
Okay.
Actually, so
Yeah.
if we have a chemodecimetric reaction, in that case, if you are having hydrogen bonding anion, so it is not relevant. First of all. Second of all, I have taken all the nascent oxygen or nascent atoms or say molecules. You can see that is nitrous on dot, then O2 minus, which is very reactive. Those actually, whatever the things I have taken here, that all are very short-lived species among the reactive oxygen species. So actually, my propaganda is like that. The molecule is showing selectivity or giving color change on the basis of reaction, not because of the hydrogen bonding. It is not permanent. Sorry,
Okay.
it is not temporary. It is permanent. So if I use any hydrogen bonding aspects or any anions or any analytes, that will not give any results. That invariably you can see cysteine is not giving any results, though it has.
Okay. So if it is a chemical result, then if I consider azide, okay, azide is a very good free radical generator. Okay.
So it is
why
free
you are
radical.
not,
Sorry,
why
sir,
you
I
are
think
not considering this
because
free radical generator?
sir, because the free radical generator azide that has been used to generate these free radicals.
Yeah.
That is not a, you cannot say free azide as a reactive oxygen species. I am telling that these all are the reactive oxygen species.
Okay. Okay. I think we can proceed to the next presenter, please. We are running time.
Thank you so much. Thank you so much.
Please.
Okay,
Sorry,
thank
sir.
you, Pranay.
Thank you so much.
Bhojraj Chetri. Next one is Bhojraj Chetri.
Hello, sir.
Bhojraj ji.
Wait a second, sir.
Okay, Sanay, please. You just close your screen. Close your screen, please. Sanay Naha. Bhojraj ji, are you there?
Sir, I did it.
Yes, sir.
Bhojraj ji. Sanay, please close your screen, sir. Share. Your name is still being shown here. Sanay Naha.
Actually, sir, I did it, sir.
Okay. So let the Bhojraj come forward. Bhojraj ji.
Yes, sir. Sir, is my screen visible, sir?
Okay, an important medicinal plant of Sikkim
Yes, sir.
Himalayan region. That is Fraxinus floribunda.
Very good evening, everybody. Myself, Bhojraj Chetri, and I am pursuing my PhD degree from Sikkim Manipal Institute of Technology under the supervision of Professor Dr. Noin Kamal Bhattacharya, Professor Dr. Sangeeta Jha, and Dr. Archana Monidas. The topic for my presentation is an important medicinal plant of Sikkim Himalayan region, Fraxinus floribunda, or review. Sikkim is a very small hilly state in the eastern Himalayas, and it is bestowed with abundant natural resources. Although Sikkim covers only 0.2% of the geographical area of the country, it harbors more than 26% of the flowering plants, and approximately 242 medicinal plants are available in Sikkim. Several ethnic groups of people of Sikkim have vast knowledge of herb medicines and are practicing through many generations for curing different diseases. It is estimated that more than 35,000 plant species are being used in various human culture, and approximately 80% of the world population rely on traditional medicine for primary health care. Plants are rich in wide variety of primary and secondary metabolites, and the plants containing the secondary metabolites such as tannins, terpenoids, alkaloids, and flavonoids, which have been found to have antimicrobial properties. Now, because of the resistance that pathogens like E. coli, C. albicans build against the antibiotic, there is a great interest in the search for new antimicrobial drugs from nature. So, isolation of active constituent from the natural sources responsible for the antimicrobial activities may contribute greatly to the success in the antibiotic discovery. Fraxinus floribunda belongs to the Oliaceae family of kingdom Plantae known as Lacouri in Sikkim. It is mainly found in Sikkim, Khasi Hills and Eastern Himalayas. Fraxinus floribunda is a medium-sized tree which grows up to 10 to 15 meters tall and with a trunk up to 50 centimeters in diameter, and it has a gray bark. The leaves of these plants are odd pinnate, whose leaflets has 3 to 5 pairs. The flowers is pedicellate, small, white, and polygamous, and also the fruits are winged and one-seeded. Now, if you look at the traditional uses of this plant, traditionally the stem bark is crossed and the pipette paste are applied externally on the bone fracture, joint dislocation, and sprains, and they are bandaged for 3 to 7 days. The stem bark is made decoction with a few amounts of sugar, and they are administered orally for the body ache. The freshly collected stem bark is also heated over the hot oven, and they are placed on the affected area of gout to relieve pain. Stem bark juice of about 50 ml twice a day are given to treat stomach disorder in sheep and goats. And also for cattle, paste of bark is applied to treat broken legs and arms. Fraxinus florimunda has been accounted for its wide spectrum for biological activities, including anti-inflammatory, anti-nociceptive, antioxidant, hepatoprotective, free radical scavenging, and anti-diabetic activities. Several in vivo and in vitro studies has been executed to describe its medical properties and to investigate the mechanism of action. Aurenica Subbai et al. Has reported antioxidant potential, anti-inflammatory and hepatoprotective from the bark of Fraxinus florimunda through various thermal processing. The powder specimen was extracted through 4 different methods: normal boiling, boiling in autoclave under pressure, succussion in succulent apparatus, and cold percolation below -4 degrees Celsius. And this method of extraction process was repeated for 3 successive times in order to observe the retention of bioactivity of compounds in the extract. Now, the antioxidant activity of the bark of the extract was determined using following methods. DPPH scavenging assay. It is 2,2-diphenyl 1-picaryl hydrazine. DPPH is a stable free radical that can be used to measure the radical scavenging activity of antioxidant. Here, the IC50 was calculated with the percentage inhibition versus concentration graph. IC50 value is the effective concentration that could scavenge 50% of the DPPH radicals. Inhibition percentage was calculated with the formula absorbance of DPPH solution by control minus absorbance of DPPH solution by plant extract divided by absorbance of the control into 100. Other methods such as ABTS, nitric oxide scavenging assay, metal chelating, etc. was used for the determination of antioxidant activity. Anti-inflammatory activity of carrageenan induced per edema, also known as acute model, was performed by the method described by Winter and Porter. In this method, first, the acute inflammation was produced by injecting 1% solution of carrageen into the plantar surface of rat hind paw at a dose of 0.1 ml per 100 gram. Then the Worcester albino rat were divided into 3 groups of 6 in each. 0.9% solution of NaCl at a dose of 0.1 ml per 100 gram was administered to group 1, that is control group, and for the control group 2, takes drug sample of bark of Fraxinus florimunda was administered. And for the group 3, standard drug aspirin at a dose of 100 mg per kg was also administered. Then after 30 minutes, carrageen solution was injected to the animals to the entire group. The paw edema among different groups was compared, and the percentage inhibition of the paw edema was determined by the formula BC minus BT by BC into 100, where BC is refers to the paw edema of the control animals, and BT refers to the paw edema of drug-treated animals. Nagaranjan et al. Isolated different coumarins, 8-acetyl 7-hydroxy-6-methoxycoumarin, 8-methoxycoumarin, fraxitine, 2,5-dihydroxy, 6-methoxy-acetophenone, and scopolamine from the alcoholic extract of the leaves. And these are the different isolated coumarins that I have given. And Raj et al. Investigated the influence of fraxin and fraxitine, which was isolated from the bark of Fraxinus florimunda on the activities of mouse, liver, and lungs cytosolic glutathione S-transferase, that is GST. It was reported that flaxsetin enhanced the GST activities in both liver and the lungs tissue. Sudarshan et al. Extracted the powdered leaves in methanol in Soxhlet apparatus. Here, the methanol extract of the leaves was tested for the free radical scavenging activity using DPPH radical scavenging assay, lipid peroxidation assay, and hydroxy radical scavenging assay. It was found that the chloroform fraction of the leaves extracted when undergone for column chromatography on new pentacyclic triterpenoids like beta-amyridine was isolated, and it was further reported that the methanolic extract showed the potent free radical scavenging activities in vitro methods like DPPH, lipid peroxidation, and OH radical scavenging activities, and the concentration ranges from 20 to 320 microgram per ml. Thus, to conclude, medicinal plants have become an utmost important for curing different severe diseases in day-to-day life. Due to its lesser side effect and effectiveness, better cultural acceptability, compatibility with the human body, medicinal plants are now accepted fact. Sikkim, also known as land of traditional faith healers, and approximately 242 medicinal plants are available in Sikkim. Fraxinus floribunda is one of the important medicinal plant, and it is traditionally used in treatment of fracture, dislocation, anti-inflammatory, etc. Many journal studies shows that extracted compound from the leaves and bark of the Fraxinus floribunda using different solvents showed significant activities against the tested microorganisms. Fraxinus floribunda is one of the important medicinal plant, and further investigation can be carried out from this plant, which may lead to non-expensive plant-derived medications against the growing epidemic. These are the references from where I have prepared my PPT. And lastly, thank you so much.
Thank you, Bhoj. It's a very nice presentation.
Thanks, sir.
If there is any question, please ask. Okay, thank you, Bhoj again.
Thanks, sir.
Our next speaker is Sunita Singh. Madam Sunita Singh, are you there? No. If then the next speaker is Veer Singh Barde.
So Sunita Singh is absent, no?
I think so, sir. Just
Okay.
I'm calling her name again.
Okay.
I think because she is not there in the group.
Sunita ji, if you are not there, then we have to proceed further. Veer Singh Barde. Veer Singh Barde, are you there, sir? Veer Singh Barde.
Neha Gupta present next.
The
Sir,
next
Neha
one-
Gupta is there.
Neha Gupta. Okay, we
can call her.
Okay, we can call her, sir. We can invite her, and then wait for the others. Neha Gupta is the 9th number in the list, no?
Yes, sir.
She's at the 9th number.
Yes, yes.
So, okay, welcome, Neha ji.
Hello, sir. Can you see my slides, sir?
Okay. You know, your slides are visible now. You can start. Your voice is little low.
Oh, sure, sir.
Okay. So you can adjust your mic your side. No?
Sure, sir.
Okay. Please. Please,
Good
Neha.
evening. Okay, sure.
Good evening.
Good evening, everyone. I am Neha Gupta. I am a research scholar in the Department of Chemistry here at SMIT. The topic of my presentation today is the light-driven reverse combustion of carbon dioxide to fuel for prospective carbon dioxide recycling, which is a review of this field. And I hope that you all will learn something new after this presentation. To begin with, we all know that the emerging carbon dioxide emissions have caused a global human crisis, and that we need to suppress and mitigate these carbon dioxide emissions in order to control and limit their accumulations in the environment. And there are various ways in which we can achieve that, one of which is the conversion of this carbon dioxide, excess carbon dioxide, to fuels of valuable fuel. This can be categorized into two main categories. One is the conversion of carbon dioxide to industrial fuels, in which the entire carbon dioxide molecule is utilized, and it is also known as carbon dioxide fixation, which is shown here in the left hand side of this diagram. And another one is the reduction of carbon dioxide to industrial fuels, which is also known as the reverse combustion of carbon dioxide, which is shown here on the right hand side of this diagram. A major hurdle for this process is the fact that the reduction of carbon dioxide is in fact a non-spontaneous process, and thus we require external energy input to drive these reduction reactions. There are various ways in which we can achieve carbon dioxide reduction by using various methods such as chemical reduction, photocatalytic reductions, photoelectrocatalytic reductions, and electrochemical reductions. A common problem in all of these processes is the simultaneous formation of various products, which stems from the low selectivity of these methods. And this not only suppresses the efficiency of the process, but also leads to the addition of tedious product separation steps. This problem can be overcome by using enzymes as catalysts to drive these reverse combustion reactions for carbon dioxide. And as we all know, enzymes are highly selective molecules, and we can use specific enzymes to drive carbon dioxide reduction to get specific products. And not only that, utilizing enzymes also ensures that the reactions are operated under mild reaction conditions and less toxic wastes are generated. And as mentioned earlier, enzymatic reactions lead to fewer byproducts. This is a representation of carbon dioxide reduction to methanol using a cascade of three different enzymes, namely formate dehydrogenase, formaldehyde dehydrogenase, and yeast aldehyde dehydrogenase, which lead to formation of specific products, that is formate, formaldehyde, and methanol respectively. As you can also see that for each of these reduction steps, we require one molecule of NADH, which is consumed and converted to NAD+, which is its oxidized form. And this NADH is a cofactor which here provides the reducing equivalence for the reduction of carbon dioxide. One of the problems is that these NADH cofactors are highly expensive, and since they are stoichiometrically consumed during these reactions, a widespread use cannot be practical due to their high cost. To overcome this problem, what can be done is that this oxidized NADH can be reduced back, NAD+ can be reduced back to NADH, and then this reduced NADH can be fed into the reaction to be consumed for further enzymatic reduction steps. This process is also known as NADH regeneration, and NADH regeneration occurs via two different mechanisms. Firstly is the direct regeneration, in which NAD+ is converted to NADH via two single electron transfer steps, which leads to the formation of 1,4 and 1,6 NADH isomers and also a dimer. Now this 1,6 NADH isomer and the NAD2 dimer are both enzymatically inactive, and they cannot participate in the enzymatic reduction of carbon dioxide. For indirect regeneration, we require an additional catalyst, which is also known as a mediator, which collects the electrons and transfers 2 electrons at a time so as to surpass the possibility of forming unwanted isomers and only forms the 1,4-NADH isomer, which is the enzymatically active form. It is also worth mentioning that till now, this rhodium metal based mediator is the only mediator that has been found to exclusively form the enzymatically active form of NADH, that is 1,4-NADH, and thus is the most widely used mediator for NADH regeneration. NADH regeneration, as similar to carbon dioxide reduction, can be carried out in various methods, but here I'll be focusing on the photocatalytic reduction. Here you can see this is NADH regeneration cycle, photocatalytic NADH regeneration cycle, which is coupled to the enzymatic reduction of carbon dioxide. As you can see here, on the irradiation of light, the photosensitizers or the photocatalysts, the valence band electrons are promoted to the conduction band, and these electrons via these mediators are transferred to the NAD+, which is then converted to NADH and then consumed in the enzymatic reduction process. And as the valence bond electrons are promoted to conduction band, there is a formation of vacancy in this valence band, which needs to be stabilized or fulfilled, which is done using separate molecules which are known as sacrificial electron donors. And these sacrificial electron donors are typically organic molecules such as triethanolamine or EDTA. So this entire process is basically mimicking the PS1 in the natural photosynthetic cycle, in which the plants harvest solar light in order to convert carbon dioxide to carbohydrate by using cofactors and enzymes. And as I just mentioned, that the formation of vacancy in the valence band needs to be stabilized. This is needed to prevent the backflow of electrons from the conduction band of the photosensitizer or the photocatalyst, or the backflow of electrons from the mediator or from the cofactor itself, all of which will lead to a decrease in electron transport efficiencies and significantly cause reduction in carbon dioxide reduction efficiencies. And as these sacrificial electron donors fulfill or stabilize these valence band vacancies, they themselves are converted to their oxidized counterparts and thus are rendered useless and are converted into waste during the reaction. And this process hinders with the green aspect of this entire process of carbon dioxide reduction, and thus we need to look for more safe and greener options, one of which is we can use water oxidation to gain these electrons, which can then stabilize the vacancies in the valence band. This brings me to the final topic of my presentation, that is the biocatalytic photosynthesis with water as electron donors. And as you can see, this when we couple the splitting of water with that to the regeneration of catalyst and the reduction of CO2 via enzymes, this whole process is in true sense mimicking the natural photosystem, and in which the water splitting catalyst plays the role of photosystem 2, and the cofactor regeneration cycle system plays the role of photosystem 1, and the redox enzymes, enzymatic reduction of carbon dioxide, plays the role of Calvin cycle. To explain with the help as a driving force for water oxidation, and on water oxidation, the electrons thus gained can be transported to this biocatalytic compartment with the help of an external circuit, and on gaining the electrons, the NADH can thus be regenerated and CO2 can be reduced as explained earlier. So to conclude my presentation, I would like to say that the conversion of CO2 or the reduction of CO2 by applying enzymes when they are coupled with photocatalytic regeneration of cofactors can be a very promising technology for recycling this excess carbon dioxide in future. Thank you.
VP Singh, sir? Yeah, sir, I think the 3 other candidates, they are absent. We can just
Yes, we
call
can.
them once again.
So one absent is Govind Bagaria, and the other one is Sunita Singh, and then Veer Singh Barde. Is anyone there? Otherwise, it is time.
Sir, yeah, sir, please, you please conclude. Yeah.
Okay. So it was nice to see very good work by the presenters, and they are well prepared. They have done a lot of work. So Bhattacharya ji, namaskar, good evening.
Namaskar, sir, namaskar.
So it was nice. And I must also thank you for giving me this opportunity. So we'll share the report.
Sir.
I asked Santanu Gupta ji for his number, but there is something I missed because it is showing only 8 numbers. No? So Santanu Gupta ji, can you please?
Sir, 77 97
89
89
08
3308.
Oh, that 33 is missed. Thank you. Thank you so much. So I'll share the score sheet and thank you so much. And all presentations were very good and they were within the time limit also. So I think I must congratulate Bhattacharya ji, you as convener of this conference. Okay, thank you. Thank you so much. So thank you everyone. We had a very good time and this session, technical session was very good. Anything else you want from my side, sir?
Okay, sir. Thank you. Thank you so much, sir.
Thank you.
Thank you.
Thank you. Okay.
Yeah, the session is now handing over to Subeksha. Please continue for the next session.
Okay, so I can leave, sir. Bhattacharya ji?
Yes, sir. Yes, sir.
Okay, thank you.
Yes, sir. Thank you. Thank you for joining with us and accepting our invitation as chairperson for this particular technical session. We will meet, sir. We will meet definitely.
Okay.
Yes, sir. Thank you, sir. Good evening, everyone. Now we shall begin our technical session 7. The session will be chaired by Dr. Ramesh Sharma, SMIT, and Dr. Joydeep Biswas, SMIT. I kindly request the both of them to please take over the session.
Thank you, Subeksha. Nayan sir, am I audible?
Yes, sir.
Audible.
Okay. Okay, we welcome the participants to the 7th technical session of this conference. I would like Jaideep sir to please take from here.
Yes, sir.
Okay, sir.
Okay. So shall I proceed for the technical session 7?
Yes, sir. Yes, sir.
Okay. So good evening, everyone. So we'll proceed with oral presentation 48, B. Ramu. B. Ramus.
Ramu sir, I believe is present.
So finally, अभी सुनो ये
Sir, please go ahead and present, sir.
Yeah, Ramu sir, please make it full screen and continue. Ramu sir, are you there? Yeah, Ramesh sir. Ramesh,
Yes, sir.
There is maybe a technical problem from his side, Ramu.
Yes, sir. Then we'll move on to the next candidate. He can join when his problem is sorted out.
Yes. If Ramu sir can hear us, right, please unshare your screen. We will proceed and then we'll come back. Hello. Okay, we'll proceed to the next oral presentation 49, Prakash More. Prakash More. Okay. Next is oral presentation 50, Sarabjit K. Makkar.
I believe he is present.
Yeah.
I think I've seen the participant list.
Sarabjit K. Makkar. Yeah, Dr. Sarabjot.
Hello.
Yes.
Yes, sir.
Yeah. Could you please share your screen
Yeah, sure.
and continue?
Yeah. Okay, so my screen is visible to you?
Yeah, it is visible. Make it full screen and continue.
Yeah, sure.
Yeah, it's okay.
Yeah. Okay. So shall I start, sir?
Yes.
Yeah. So basically the amphiphilic polymers I would be talking in today's session. So this we have used for a bilirubin detection. So sir, how many minutes do I have?
So around 8 to 9 minutes and 1 minute question answer.
Okay. Yeah. So this amphiphilic polymers, they find a wide range of application in the areas depending from the materials to biology, such as drug delivery, catalysis, etc. But what happened actually is amphiphilic block of polymer where one block is a hydrophobic and the other is hydrophilic. This has been extensively investigated. But the problem is that they are basically the synthesis of such amphiphilic copolymers is challenging because you are making one block in a controlled manner, okay? And then the generation of a second block could be constrained due to the incompatible solubility of these amphiphiles in a common organic solvent. So instead, what we can do is we can synthesize an amphiphilic homopolymer, okay, where 1:1 ratio of a hydrophilic to hydrophobic unit could be exactly maintained along the long polymer chain. So what we are doing here is we are starting with the amphiphilic monomer, where 1:1 ratio of a hydrophobic to hydrophilic unit is there. Okay, and then we are basically polymerizing it. So in literature also we have find very few amphiphilic polystyrene homopolymer, and they have used it for some capturing. But what we did basically is we have synthesized a styrene based monomer, where so we have started with a alkyne, this simple click reaction, alkyne azide click reaction. So this is a one step process, but we are making this azide by further three steps, and styrene, alkyne styrene by 2-step method. So this monomers, when we are doing a click to make a styrene based monomer, and this on polymerization will give a protected polymer, and this further on deprotection will give you a glucuronic acid pendant on a styrene part. So this is the whole deprotected polymer. So basically why we chose glucuronic acid is that in our body also, this glucuronic acid basically is hydrogen bonding with the bilirubin. So to make it more soluble, and because bilirubin by any is a very hydrophobic molecule. So basically this is getting conjugated with a glucuronic acid molecule to make it water soluble, and that's how the body is eliminating the bilirubin out from your body. So what we are doing, we are using the same chemistry that our body is using. So here also, in order to detect a bilirubin, what we did, we also have we have this designed a polymer having a glucuronic acid unit, and this then we are using as a surfactant. So this is basically acting as a surfactant in a mini emulsion polymerization, and this is the first report where we have used this deprotected polymer as a surfactant in a mini emulsion polymerization of a polystyrene nanobeads. And this is incorporating a sensor moiety, which is OPV, which is a dye. And we chose this dye because there is this absorption emission overlap, so energy transfer is possible. So that's why we have used this OPV. And then a mini emulsion polymerization. So what we got basically is a polystyrene, OPV incorporated polystyrene nanobeads, and this is functionalized with the glucuronic acid moiety. So this glucuronic acid will act as an anchoring unit, and OPV will act as a sensing site for a bilirubin. Okay, so this is the detailed synthesis of the styrene based monomer, and this is by LCMSMS and proton NMR, and this is the characterization of protected polymer. So here you can see the molecular weight of 16,000 was achieved, and here also the broadening in the peaks of proton in NMR also shows the formation of a polymer. And then deprotection also we have confirmed by this contact angle study. So here when we took protected polystyrene, this 121 is a highly hydrophobic environment. And as soon as we deprotected it, it is getting transformed from 121 to 26 degrees, which is nothing. So this transformation from hydrophobic to hydrophilic can be easily seen. The same was confirmed by its proton NMR also we have done, but here I'm showing FTIR. Yeah, so this deprotected polymer can be used as a surfactant. So in literature, we have checked that the HLP calculation they are doing. So in order to check their surfactant property, so if your HLP is near 9 to 12 or 12 to 15, it is acting as a surfactant in oil and water emulsion. So here our unit was coming out to be 14. So this is this is acting as a this is a very theoretically it is, yeah, it can act as a surfactant for mini emulsion polymerization. Also we have checked its CMC using DLS and the surface tension, and the surface tension also it is equivalent to bridge S100, which we are using it for a mini emulsion polymerization. Okay, so finally we used it, means after finding out that okay, it can act as a surfactant in a styrene mini emulsion polymerization, we basically put a actual polymerization using this surfactant in a mini emulsion polymerization. And what we got is we have made a different series of a polymer having this CA, and we have chose OPV5, which have appreciable dye content and the solid content and zeta potential. Okay, so I have left this bilirubin study here. Maybe, okay, fine. Yeah, sir. Okay.
Okay, okay, ma'am. It was a nice presentation, and thanks for completing in time. So the house is open for any question, any queries. Any short 1 or 2 questions? Okay, if there are no questions.
Okay, thank you so much, sir.
I would like to thank you for your presentation.
Thank you, sir.
Ma'am, can you unshare your screen?
Yeah, sure, I did.
The next presentation, OP51, Amar J. Solanki. Amar J. Solanki. He is not there. We'll move to OP52, Diksha Patania. She is also not there.
Jaideep sir, call Ramu sir again once more.
What?
Ramu sir, can we call him once more?
Okay. OP48, B. Ramu. Are you there, sir? B. Ramu. No, sir, he is not there. He came. Ramu, B. Ramu, can you hear us? No, there is an audio problem from his side. Shall I proceed, Ramesh sir?
Yeah, I think so, sir. Welcome to him at the end once more.
Okay. So OP53, Vishal Datta. Vishal Datta. He is also not here. Moving to OP54, Sonu Chaudhary. No, he is also not here. And final, OP55, KS Lokesh.
Dr. Lokesh, I think, is present.
He is there. Dr. Lokesh, can you hear us?
Yeah, good evening, sir.
Yeah, could you please share your screen?
Yeah, am I audible?
Yes.
Yes, sir. Yes, sir. You are very much audible.
So please share your screen.
Is it visible?
Not yet.
Not yet, sir.
Yeah, now it is.
It's visible.
Yes, sir. Make it full screen and continue.
Okay, sir. Okay. Good evening, sir.
Good evening, sir. Please continue, sir.
Yeah, this is Lokesh from Vijayanagara Sri Krishna Devaraya University in Karnataka. I am going to present my research work related to novel uranium phthalocyanine anchored with functionalized multi-walled carbon nanotubes as an efficient bifunctional electrocatalyst for clean energy production. So we are preparing a novel uranium phthalocyanine for the clean energy production like oxygen evolution reaction, hydrogen evolution reaction. So my content of research is as follows, where I am giving the importance of hydrogen and oxygen for fuel cell application, So why organic based catalysts are required? Why we need to replace the precious and less abundant materials with organic based catalysts? Then I am going to discuss the preparation and characterization of the novel catalysts, and then the catalyst is used for OER application as well as HER application. Then I will conclude my talk. So most of the energy, whatever you are using for different applications like industries, automobiles, or domestic purpose is meant through fossil fuels such as coal, natural gas, and oil. So the problem with these fossil fuels, which are known for their high energy efficiency, is the release of greenhouse gases and less abundance. So they are the cause of pollution, and due to the emission of carbon dioxide, there is increase in climate or with change in climate. So in order to replace these fossil fuels with less precious or alternative energy systems, we have different alternative energy systems like wind, solar energy, hydropower energy, geothermal energy, and right now more focus has been given to electrochemical energy systems. When we are talking about the alternative energy systems, it is the cost and efficiency which matters to a bigger extent. We need to reduce the cost and we need to increase the performance of these electrochemical energy systems for their commercialization. In this aspect, the electrochemistry plays an important role in the discovery and development of electrochemical energy systems. So the electrochemistry is harnessed to address possible solutions to both of these issues. First, it is used to develop a low-cost alternative energy catalyst. Then we can investigate the production of chemical fuel stacks, which can be used for the conversion of energy and storage devices. Among the various electrochemical energy systems, especially in the field of electrochemical energy systems, fuel cells have attracted and they are found to be highly efficient energy systems because of high energy density, low temperature operation, and zero carbon dioxide footprints. That means they will not pollute to the atmosphere. These fuel cells requires hydrogen and oxygen as fuel and oxidant. Presently, platinum carbon is used for the electrolysis to produce hydrogen from water, and iridium oxide catalyst is used as benchmark catalyst or standard catalyst to produce oxygen during the water electrolysis. The reaction that is taking place at cathode is the H+ ion reacts with an electron to produce hydrogen molecule or hydrogen, and at anode where oxidation of water takes place to produce oxygen, and the overall reaction involves the electrolysis of water to give hydrogen and oxygen, This hydrogen and oxygen produced from the electrolysis is fed to the fuel cells, for conversion of chemical energy to electrical energy. So in case of water splitting reaction, it is carried out in to produce hydrogen and oxygen. So the various ways in which the hydrogen and oxygen are obtained by water splitting reaction are either using solar cell devices, photoelectrode device, electrical energy device, pyroelectric device, thermoelectric device, triboelectric nano generator device. These are the different devices which are used to produce hydrogen and oxygen by water electrolysis. So out of this, electrochemical generation of hydrogen and oxygen by water electrolysis has attracted and efficient in nature. So in order to commercialize this water electrolysis, we need to replace the benchmark catalyst with easily synthesizable, simple and highly efficient and durable catalysts. So one of those such catalysts are phthalocyanines, where they have structure similarity to biological compounds like hemoglobin and chlorophyll, and their structure can be modified for better efficiency. So organic compounds are well known for their structural diversity, and properties can be tuned by simply adding or attaching new functional groups to the peripheral ends of the molecule. Even a small change in the functional group affects or changes the properties of the organic compounds, and in turn their application can also be changed. So phthalocyanin is one such molecule whose properties can be tuned or changed by adding or substituting different functional groups as well as metal atoms. These phthalocyanins are semiconducting in nature, and they have two-dimensional structure with 18 pi electron conjugated system. So this is the structure of porphyrin which exists in most of the biological molecules, and phthalocyanin is having somewhat similar structure like porphyrin. Inner structure of phthalocyanin is similar to porphyrin. In phthalocyanin, various metal atoms can be attached at the central core, and the hydrogen atoms can be replaced with the metal atoms, whereas the substituent or functional groups can be attached at the peripheral hydrogens present in this molecule. So when you change either the functional group or when you change the central metal atom, their properties does vary. In addition, these phthalocyanin molecules are highly thermally stable, chemically stable, and absorb light radiation in the range of 500 to 700 nanometer. They are electroactive molecules and shows redox properties. They also show photocatalytic behavior. So we have synthesized a novel uranium phthalocyanin with oxybridging and imine linkage. So here we have reacted salicylaldehyde with the bromoaniline to get imine linkage, where we have given on the side the reaction conditions. This hydroxy group containing imine linkage compound on reaction with nitrothalonitrile, nucleophilic substitution reaction takes place, and we will get a thalonitrile ligand 3. This thalonitrile ligand on tetramerization at high temperature, we get the phthalocyanin compound with oxybridging and imine bridging. This phthalocyanin was characterized using various techniques to know its purity as well as its formation and structure. Even the precursors and the thalonitrile ligand was characterized by NMR spectroscopy, mass spectroscopy, etc. to know its purity as well as the structure. The form phthalocyanine also characterized with various spectroscopic techniques and thermal gravimetric analysis to know the various optical thermal properties. So the synthesized uranium phthalocyanine showed a B band for N to pi star transition at 343 nanometer, whereas the Q band.
Excuse me, sir, could you please finish it up? Yeah, Dr. Lokesh. Dr. Lokesh. Dr. Lokesh. Ramesh sir.
Yes, sir, I think you may be having network problems. We'll wait for a few minutes for him to get back online.
So I think we should proceed to the next one. Ramesh sir?
Yes, but I think there's only one speaker. B. Ramu is only there, I think. The rest are, maybe they are not there. So I think we can wait for 1 or 2 minutes to see if Dr. Lokesh can get back online.
No, he is not there online.
He must have lost his net connection, I think. So, shall we call B. Ramu, sir? Sir?
Yes, sir. Call.
You can call him from there.
Okay. OP48 B. Ramu, are you there, sir? No, sir, he is not online. Let me call one by one. Prakash More. He is also not there. Amar J. Solanki. No. Diksha Patania. Absent. Vishal Datta. Absent. Sonu Chaudhary. Absent. Ramesh sir.
Yes, sir. I think now we can end the session now, I think, today.
Okay.
But I think we should mark Dr. Lokesh's presentation. He
Yeah.
had more or less covered his topic, I think.
Yeah.
So we'll consider it as completed. Okay, sir?
Yes, sir. Definitely. Okay, so we are end of the today's. So thank you all the participants. Now over to Professor N.K. Bhattacharya.
Okay, thank you, Dr. Ramesh Sharma sir and Dr. Jaideep sir. Should we wait another 5-10 minutes since time as mentioned in the schedule, it is there?
Yes, sir, we can wait.
I think we can wait for Dr. Ramu to come online.
I think
He
he will
was
come back, yeah.
going on and off, so I don't know what. Maybe he's having network issues.
Otherwise, tomorrow I think we will not get time to adjust if anyone comes. Constant presentation is there. Anyway, for participants, the tomorrow's joining link that will be accordingly given in the WhatsApp group. And just now I have given in the chat also here. You can copy from there also from tomorrow's joining link. And we will start at 9 o'clock tomorrow, the technical session 8, followed by the invited talk. Then again we'll enter into technical session 9 and onwards.
Yeah, NKB sir, I got a mail from Dr. Lokesh that he is having network issues, so he will not joining again.
Okay. I think then we can conclude, since I don't think, since already information given that you please join well in advance. That means session started from 5:30. I think you requested to join everyone before 5:30, right?
Yes, sir.
Okay, that's why I don't think we can conclude. Yes, thank you, Dr. Ramesh Sharma and Dr. Jaideep Biswas for sharing this session and all the participants. Now we are at the end of today's program. As I mentioned, that tomorrow will start at 9 a.m. I request everyone to join. Tomorrow we'll be having 3 invited talks and remaining all the technical session. That means paper presentation by the participants, and we will have the valedictory session at 6:30 in the evening. Thank you all. I think you can leave from the meeting. And
good night, everyone. Yes.
Yeah.
Good night, everyone.
And we'll see you tomorrow.
Yes.
Thank you, sir. Thank you, sir.
Thank you, everyone. You can